Good morning, and thank you for joining us for day 2 of the $1 Million International Quantum U Tech Accelerator. We had a great day 1, and I'm looking forward to an even better day 2. I'd like to welcome Colonel Timothy J. Lawrence, Director of the Air Force Research Laboratory, Information Directorate, and Commander, Detachment 4 at the Rome Research Site in Rome, New York. Colonel Lawrence oversees a staff of over 1,200 civilian, military, and on-site contractors. The Information Directorate executes an annual budget of approximately $1.8 billion in the areas of command control, communications, computers, intelligence, and cyber. One of the game-changing technologies that the Directorate is pursuing is quantum networking and computing. We would not be here today without the unending support and leadership of Colonel Lawrence. I now welcome Colonel Lawrence to kick off today's events.
Good morning, or to my Australian friends, I should say good evening. It's my pleasure to be here today to kick off day 2. Just like to give a shout out to 2 individuals today. First one is Dr. Welsh, who's the director of the Air Force Office of Scientific Research. Without her and her support, this event would have happened. Just to lay the context, she was only in the job for a week, going through COVID, having to work remotely from her home. I came up to her and I just said, would you like to spend some money and do it in something that will be extremely value added in putting together this tech accelerator? And so only a week on the job, I explained to her why it would be value added, and she agreed. The other big thing is that she said, not only am I going to fund the program, I'm also going to give you my support in getting together with folks that are part of your judges panels today. So we met weekly, and she said, have you thought about this person? Have you thought about that person? And going through all of that together, the team was put together and the event occurred. So just huge shout out to Dr. Welsh for what she's doing. Because of her leadership, you are all here today going through this competition. Next, and he mentioned yesterday a little bit that Admiral Selby and I were classmates at MIT. I have to show this book for those of you out there, and I know everyone knows this book. My biggest regret at MIT is that I didn't have Admiral Selby autograph this book. That guy smoked that class. He could solve the Schrödinger equation for the helium atom in 20 minutes and used only one piece of paper at that time because we didn't have a lot of the computational math you get from computers. We had to do it by hand, but Admiral Selby, was inspirational in quantum mechanics. And to all of you out there, thank God that he is a sponsor and not a competitor, because he would beat you with his own quantum mechanics idea. But no, he's a tremendous friend, and the Navy needs these systems, and without them as a partner, this event would be nowhere near the level that it's at. So today we're going to be talking about sensing and communications. And I'm a judge. So if I look at all the duties that Dr. Hayduk said, being a judge for this, it's really got my game on. I read your white papers last night, and holy cow, to see the Hamiltonian again. So I'm a bit nervous because you guys and gals have wonderful ideas. So it's going to be tough on me working with my other judges to make a decision for who wins. But again, to get to this level, from my eyes, you're all winners. And if there's other ways that we can collaborate, even if you don't get a grant, maybe you have a postdoc that may want to come work for the Air Force Research Lab or the Office of Naval Research, we're here. Because as you know, our world needs smart people working in this amazing technology. So that's all that I had, and can't wait to kick it over to the competition, and I'll see you on the other side as a judge. Enjoy the rest of your day and evening, and we'll see you soon. Take care. Thank you.
Thank you, Colonel Lawrence, for that great welcome. For those of you who are unable to join us yesterday, we have a few housekeeping items that we'd like to run through. You missed some great pitches, as I said, and all of those pitches can be found on the Innovare YouTube channel and the event webpage. I just want to say a moment and again, congratulate the 36 teams who have been selected to pitch at this $1 million International Quantum U Tech Accelerator. Before we dive into the sensing pitches, I want to go over these housekeeping items, which are pretty simple. All of the pitches will be 10 minutes, followed by 5 minutes of questions and answers by the judges. We will be sharing your virtual posters to support each pitch. If you are unable to navigate your own poster, we will move through your poster for you. When you're ready, we will start the start button at the top of the screen for the 10-minute timer. The timer will turn yellow for a 2-minute warning, and at 30 seconds, it will turn red. There will be a prompt that pops up in the middle of the screen at the end of the 10 minutes, and that's when the judges will start their question and answer. After every few pitches, we'll take a short break. I would now like to introduce our judges for this session. Dr. Matt Squires, Air Force Research Laboratory. Dr. Jerry Borsick, Naval Research Laboratory. Dr. Lali Chatterjee, Department of Energy. Dr. Mitari Ojari, National Geospatial Intelligence Agency. Dr. Yvette Weber, United States Air Force. And Dr. Carl Williams, National Institute of Standards and Technology. And with that, let's get on to our first pitch. I'd like to welcome Professor John Close from the Australian National University. Please unmute yourself for a mic check. And when you're ready to begin, we will click the Start Presentation button on your screen for you to begin the 10-minute presentation.
Okay, thank you. Can everybody hear me?
Yes, sir. Thank you.
Excellent. Thank you. All right, I'm looking for the start button here. Okay. Whoa, that is very small. Can we make that larger? All right, we have a problem here. Can we make that a little bit bigger? All right, evidently that's not working. That's all right, I'll have to avoid that. I'll use a poster instead. So it's a great pleasure to be here this evening. Our ultimate goal is to produce and field deploy quantum augmented inertial navigation systems for GPS contested scenarios. The work that I'm going to describe to you today will be carried out in a collaboration between the ANU Quantum Sensors Group, we have 22 years of experience in cold atom research and producing inertial measurement units or inertial measurement systems for civilian and defense applications. We're very well hooked into the UK, US, and Australian defense community. Our partners in this will be Q Control, who are a Sydney company. CEO, Professor Mike Biersick. Many of you may know Mike. He was graduated with a PhD from Harvard and then was a postdoc at NIST. GPS, which I have pictured here. GPS is an asset, a space asset that our defense forces have become reliant on, not only directly for situational awareness, but also in terms of the civilian supply chains that supply our defense forces. They are also highly reliant on GPS. GPS, however, is a vulnerable asset. It's vulnerable to electronic countermeasures such as spoofing and jamming. It's vulnerable to solar weather. It's vulnerable to direct missile attack. There are critical scenarios where onboard inertial navigation is the only viable option or only viable alternative to GPS. Some of those are where GPS, of course, is contested or denied. Others, for example, submarine, simply can't receive GPS and are reliant on inertial navigation. The problem that we have with inertial navigation is that the errors increase as a function of time, as the mission continues in time. Those increases in the uncertainty in position are driven primarily by in-run bias drift, long-term drift, unstable scale factor, and a variety of other imperfections in the classical sensors that we use. It's long been known, or for many years now, known that that quantum sensors have much stable scale factor, much lower long-term drift, and when fused with appropriate classical sensors, high bandwidth classical sensors, can produce a inertial sensor which can reduce errors enormously in inertial navigation systems. The way these devices work is we call some atoms, we release them into free fall, and we monitor the position of the atoms as a function of time. As the atoms move around in those laser beams, we can measure acceleration. The idea then is to fuse them and deploy them as inertial measurement units or part of an inertial navigation system. The difficulty, however, the problem, however, is that real-world platforms such as here we go, such as aeroplanes, ships, and the like, those platforms move around. They roll, they move, they accelerate laterally, and the atoms move around in the laser beams. And that produces variation in the power or the local intensity that the atoms see. It can produce two-photon detuning in the beam splitting pulses or the pulses that provide beam splitters and mirrors, phase shifts because the atoms are moving, and so on. What this does is it leads to loss of fringe visibility in these systems. That loss of fringe visibility is a loss of sensitivity. The one way of removing those, one way of removing the motion of the platform is to mount your inertial sensor on a gimbaled platform. This has been done in a French collaboration where they measured gravity on a ship-based sensor. Gimbal platforms work. They're large, they're heavy, they're high size, weight, and power, they're mechanical, high maintenance, and they're expensive. We're opting for a more modern system here, where we will use quantum control of composite pulses to give us immunity to the lateral motion. With this, what we're aiming for is a strap-down inertial navigation system rather than a gimbaled inertial navigation system. Composite pulses have long been known in the NMR community as a way to give immunity to imperfect pulses. Tim Freegard in the group at Southampton have explored this for relatively simple pulses and some extremely nice work. What we will do, however, is we will look at composite pulses that are highly optimized where the optimization is done subject to a cost function. That cost function is, oopsie, I think I've done the wrong thing here. That cost function is, here we go, my apologies. That cost function is the full gate infidelity for the system. I'd like to show you some results, some initial results that Q-Control have obtained. What they've done here, or what we've done in this collaboration, is we've modeled the laser beam where you can see here, I'm sorry, these figures are very small, but we've modeled the laser beam so that we have amplitude noise on the laser beam, and we also have a distribution in atom momenta in the cloud. The distribution in atom momenta gives two photon detunings, a distribution of those, and the amplitude, the variation amplitude here models any lateral change any change in intensity due to lateral motion of the atoms in the beam. Okay, these have been modeled. I apologize for the very small size here. The original presentation was much larger, so I'm sorry about that. The system has been modeled for realistic conditions where we have We have realistic temperatures, realistic momenta, realistic atom masses, and amplitude noise and phase noise and the like. And what you'll see in the graph below here is composite pulses that have been optimized for these noise sources. The composite pulses, so on this axis is time, and on this axis, this is actually the two-photon detuning. This one here is the relative phase of the beam splitting pulse, and this one here is the relative amplitude of the beam splitting pulse. So the pulses have been optimized to minimize gate infidelity. What you'll see here, for example, this is a plot, very small, my apologies here. This is a plot of the infidelity on this axis here, the y-axis, versus on this axis, the momentum of the atoms. And you'll see that the gate infidelity for a primitive pulse, this is a simple pulse, increases very rapidly as we move away here in momentum. For the Q control pulse, it is flat. Similarly here, as a function of laser amplitude, the primitive pulse increases very rapidly. Here, it is flat. This has been modeled both for beam splitter pulses and for mirror pulses. In the final or the complete interferometer, for a full interferometer model with beam splitters and with mirrors, what you'll see here, under realistic noise conditions or lateral motion of the atoms due to motion of the platform, what you'll see is that the primitive pulses give us an amplitude or a fringe visibility, which is roughly 10 times smaller than the optimized composite pulses from Q control. So these are initial results, and these are the sorts of directions we will go in. Now, what in fact we will do in this collaboration is that we're going to trade complex mechanical systems for software-enabled quantum control solutions. We'll develop error-robust quantum control to take account of lateral motion of the beams, and we will test. Importantly, we will experimentally test these results on our in-house flight simulator programmed with real-world information on acceleration and rotations from air, land, and sea vehicles. Now, where this is going is our goal here then is to implement quantum control for lateral accelerations. In the future, we will do this both for Raman pulses and Bragg pulses, including higher order Bragg pulses. In the future, we'll look at beam rotation or beam gimbaling, if you like, optical gimbaling to remove rotations from these systems. These are the first steps that we'll make in strap-down quantum augmented inertial navigation. Thank you.
Thank you, Professor Close. The paper is now open for 5 minutes of questions from the judges.
So this is Carl Williams. I'll ask a quick question. Amazing initial data there. So the real issue, it appears, and you please correct me if I'm wrong, appears to be that how stable the laser beam is going to be, and whether there's coupling of the laser beam because you have it fixed mounted to the platform, and the noise and the vibration of the platform causing speckle or other oscillations in the beam. How are you going to monitor the beam itself?
Well, we could use a pickoff to monitor any beam noise of that kind and potentially feedback to correct it. So that's something at the moment in these models that we're not considering. We're really considering just amplitude, phase noise, and two-photon detuning noise, which is not on the laser itself. It's more a function of the fact that the atoms are moving around in those beams. But there's no reason why we couldn't monitor, as perhaps you're suggesting.
John, this is Matt Squires. Great presentation. So it sounds like you're trying to optimize out the motion of the atoms in the laser field,
Yep.
Not necessarily phase shear and some of the other effects that tend to wash out, signal contrast. Can you just speak to that? Is that where your beam steering would also have to?
When you say phase shear, Matt, do you mean in the atom cloud, or do you mean is that what you mean by phase shear?
Yeah, across the atom cloud, when you have rotations, you get a phase shear across your cloud. And,
Yes,
and some people have done
yes,
imaging on that phase shear, but
yes,
it's
yes, Matt. Two possible responses to that. One of them, of course, is that phase shearing gives rise to spatial fringes inside the atom cloud. One way of getting around that is you actually image the spatial fringes, and you can use that information as well. So this is one way. This does wash out. Visibility, but only if you use a single pixel detector. If you image, then you can extract that information. The other one, though, Matt, the beam steering or beam rotation, you'll know that for Earth's rotation, a tip tilt mirror has been used by Holger Muller, by Achim Peters and others to so that you hold the direction of the beams constant when the Earth rotates. Now, if your platform rotates, we're probably going to have to do something rather similar to that, but we may have to rotate upper and lower beams. So it's sort of an optical gimbaling in some way. This is really, in terms of this project, we'll concentrate on lateral accelerations and quantum control, but we have an eye to beam gimbaling and rotating those beams as well to see if we can, it's really cleaning up the magnitude of the K vector in that point for beam rotations rather than anything else, so that we get good mode match at the output beam splitter. So I hope that answered the questions. We can use the spatial fringes if we image, and we can optically gimbal perhaps to clean up the K vector if we're running into problems with the spatial coherence of the cloud.
Thank you.
Thanks, man.
Any other questions? So I guess I'll ask a follow-up. Or does someone else have another one? So I will ask, what size beams do you need in order to do this? So
really good question, Matt. So in the probably testing in the lab, we won't use really fat beams. We'll probably use just regular beams that we might be able to get with 1-inch optics, that sort of size. But when we come to field deploy, it probably makes a great deal of sense that we would use shorter drop times and we would use wider beams so that you have some degree of passive immunity to some of these effects, just simply because you've designed this system so that the variation in amplitude in terms of where the atoms are probing the beam is lower. If you use really tight beams, you're going to have a much bigger effect that you're going to have to get rid of. So that will be part of the design process. Once we've tested all these results, we've fed it into our inertial navigation modeling team, and we design a sensor that we would then field deploy. But at this point, we'll probably use regular sized beams to test on the flight simulator in lab.
So let me follow on with that, John. This is Carl again.
Yes.
So what is your probe time and your repeat rate for your sensor, and how do you get continual variation in your system?
Okay, so that's where fusion with the high bandwidth classic and high dynamic range classical sensor comes in. So the atomic devices are relatively low bandwidth. You might be able to run a few pulses a second, maybe at most. This sort of rate, and the atoms are providing the low drift system, which when fused with the classical sensor is going to give you high bandwidth, high dynamic range, and low drift. In very much the same way that with an atomic clock, you fuse an atomic system, which might be pulsed, with a classical oscillator that has great short-term sensitivity, perhaps long-term drift. So it's the fuse sensor which gives us the combined properties of that we need to do inertial navigation.
Thank you, Professor Close. We're going to have to end it right there as we are out of time. But thank you very much for your presentation. Up next, we have Marcus Doherty from the Australian National University. Please unmute yourself for a mic check. When you're ready to begin, we will click the Start Presentation button on your screen to start your 10-minute presentation.
Hello, everyone. Can you hear me?
Yes, sounds great.
Right. Fantastic. Okay, so hopefully I have some better luck than my colleague John, and I can utilize my slides here. Let's give it a try. Well, it seems like the luck is with me today. Apologies, John. So let me just reset this. Okay, so what I'd like to talk to you today about is what is quantum microscopy? And then the second thing is, what is the innovation that my lab has done, which now unlocks quantum microscopy for a diversity of defense applications? And then the third thing I'll talk about today is how we intend to demonstrate the principles of those applications in this funding round. So what is quantum microscopy? So it takes the extreme sensitivity of quantum sensors and combines it with a microscopy architecture, such as a scanning probe, which is some of the highest resolution microscopy architectures you could desire. So you have this newfound sensitivity with what can be atom scale spatial resolution. Furthermore, as it's a quantum sensor, you can detect and image phenomena which you cannot otherwise image using classical imaging techniques. So let me provide an example of what quantum microscopy is, and this is particularly relevant because this is our arrangement of quantum microscopy, and that is a quantum sensor known as the nitrogen vacancy center in Diamond, which is an ideal qubit system that exists within Diamond, that's attached to the end of a scanning probe, which is scanned over a sample. As it's scanned, quantum measurements are performed of its electron spin resonance. And for example, we see in the bottom right-hand corner here, its spin resonance is changing with a magnetic field. And that shift in resonance is how we detect that local magnetic field of that probe. Because the NV center is atomic scale and the diamond that it can exist within is in the size of 10 nanometers or so, then we can get extremely high resolutions. An example of this is this imaging of domain walls in a magnetic racetrack memory. Now, the NV Center also has multiple sensing modes, and this is the key to the defense application. So not only can it sense something like a magnetic field, but it can also sense electric fields, as well as mechanical fields, as well as temperature fields. And it's the combination of these different sensing modes, and thus producing different types of images, that allows comprehensive characterization of a variety of things at a nanoscale. So this is things in advanced materials and biochemical engineering required to drive defense technologies and also drive medical technologies and newfound biotechnologies. But it's also about new nano and atom scale device engineering. For example, two-dimensional electronics, which require significantly less energy and can perform different functions to conventional electronics. In particular, hybridization in a variety of different devices on chip into one two-dimensional platform. And then the third one is something a little bit different, which is then using the microscope to read out non-perturbatively digital memories, such as read-only memories or flash drive type memories, which is particularly relevant to intelligence and security services. So before I talk more, I can talk about what quantum microscopy has done. And so what it has been used for so far has been things like imaging current flow in graphene. And what we can see here is the resistance due to the presence of either line or point defects in a graphene sheet, which obviously impacts the performance of that device. In the middle, we see the imaging of a superconducting vortex, demonstrating the capacity to look at novel materials using quantum microscopes. And on the right-hand side, we see the measurement of temperature and thermal conductivity in a gold nanostructure. In that small table at the below, I list the various sensitivities of this device. And these are, in real terms, things such as individual electrons in terms of an electron charge or an electron spin, and various millikelvin temperatures relevant to things which are happening either in the scale of an electronic device or in a living system. But one thing you'll notice from all of that is that there's none of those electric field applications or electrometry applications that I mentioned at the start. And that's because there's been a key limitation in quantum microscopy, and that is how to measure and image external electric fields, which are outside of the diamond, the host, the NV center. This is the key innovation of our lab. We've been able to demonstrate electric field imaging using these diamond quantum microscopes at the level of imaging a single effective electron charge. And we've achieved this via doing a variety of different technical solutions around integrating it into a scanning probe system, implementing a special quantum heterodyning technique called Q-dyne, which increased our quantum sensitivity, and then also designing and doing a great deal of material science around perfecting the electrometer and making sure we can get rid of screening effects that prevents us from sensing external charges. And on the right-hand side there, you'll see these images of the electric field produced by a 30 nanometer nanostructure, a metallic nanostructure, as well as the response of our system to voltages, etc., which were applied to this nanostructure. So by adding electrometry to magnetic field sensing and then also thermal imaging allows us to now do a variety of things. The first one is measuring and reading out information stored in a digital memory, one containing nanoscopic structures. You can think of a flash memory or one of these EEPROM memories where charge is held in the different floating gate memory cells in order to encode information. By taking a scanning probe microscope, a quantum microscope, we can scan over the top of the exposed memory and read out the charge on each of those transistors and therefore read out that digital encoding. That is the first objective of the project we intend to execute. The next one is investigating two-dimensional materials suitable for two-dimensional electronics. And here we combine the different sensing modalities to do a full comprehensive suite of characterization of things like charged dopants, things like scattering of currents, and also the thermal transport within these two-dimensional structures. And this provides an unprecedented means, and the only means I'm aware of, to truly understand what is limiting the performance and how these devices are performing at the atomic scale. This will then obviously lead to new devices, new materials for defense technologies. So what is our plan? So our plan is to combine the different sensing modalities of quantum microscopy and uniquely enabled by our capacity to do nanoelectric field imaging using quantum microscopy, to then implement and prove those two key applications, one in reading memory non-perturbably, the other in doing nanoscopic device and material characterization for defense technology. We'll leverage the two existing microscopes that we have in order to ensure this is cost effective and fit within the budget of the project. And at the end of it, we'll have done those proof of principle demonstrations, which will then allow defense to assess the suitability for this microscopy to a broader range of defense applications. And it will also yield new techniques and knowledge about how to perform such quantum microscopy in those variety of applications and how to extend the electrometry technique, as well as new knowledge about how about two-dimensional materials, how they function, and the defects that limit their performance. Thank you.
Thank you. Paper is now open for questions.
So this is Carl Williams again. The technical explanation is quite well. We understand the imaging is important. Can you give us a few more examples, of course, in this open environment, of the potential defense applications of the technology and where this might be going?
Yeah, so the way I see the microscopy is it's very much a critical enabler to defense science and technology. So in a sense is that it's about new materials, new nanotechnologies, new biotechnologies, new devices. So their primary role I see as being in defense, an enabler to defense industry and defense science and technology. There is also these additional roles, such as this reading of memory. And so with further, with further exposure, we can also think about other things that could be done, where now that we are seeing increasing of use of nanotechnologies or nanoelectronics, that quantum microscopy can be an important toolkit when trying to reverse engineer those sorts of technologies as well.
Hi, this is Jerry Borsig. Could you comment more on your most recent comment about reverse engineering and how this tool can be applied to that?
So an example is the one I showed about the read-only memory, where so that an example there is that there is being firmware encoded in that read-only memory in order for that device to function. And by being able to directly read out that visual information encoded like memory, you can reverse engineer what has been encoded to make that device work. Did that answer your question?
Yes, thank you. It's not quite what I think of being reverse engineering in that way, but that's okay.
So the other one, of course, is being able to comprehensively characterize and image nano devices. And so that's more of an engineering style of reverse engineering, which I imagine you're alluding to.
Hey, Matt, it looks like you're trying to speak and we can't hear you. I think you're muted.
Can you hear me now?
Yes, Matt.
Okay. When I'm thinking of some of these materials, a lot of them are looking at defects. Are you able to see down to the single atom size? I think you were talking about single atom defects in the graphene, but you could clarify that.
Yeah, sure. So whether or not we can see individual defects really depends on what type of defect it is. So if it is literally just a geometric defect which doesn't have an electrical or a magnetic signature, then we can't see it. But to give you an idea of what we can see is that if it's a defect that is paramagnetic, so there's a local electron at that defect with an unpaired spin, then we will be able to detect a single spin and therefore be able to image the presence of that defect. Likewise, with a charge, if it is a charge trap, so an acceptor state, and that charge is localized there, then we will be able to detect that as well.
So for your microscope, do you use just single MVs?
Yes, so for ours, which is the scanning probe variant, so that is where a nanoscopic piece of diamond is scanned over the sample, we utilize a single MV center. The advantage of that technique is it gives you the very high spatial resolution.
Okay, I think we've reached the end of our time here. So thank you, Professor Doherty. I would now like to introduce Professor David Simpson from the University of Melbourne. Please unmute yourself for a mic check. And when you're ready to begin, click the Start Presentation button on your screen, and then you can start your 10-minute presentation.
So can everyone hear me okay?
We can hear you. Yes, thank you.
Excellent. All right. Okay, so thank you very much. Before I start, I just wanted to thank the organisers of this meeting, and in particular the judges, for this opportunity to pitch at this wonderful event. It's a pleasure for me to be able to talk to you about some of the work that our team is doing. So in particular, I'd like to talk to you today about the opportunity that presents itself in trying to advance the current state-of-the-art diamond-based magnetometers. And so these magnetometers have been identified as an emerging technology for defence, and they're being actively explored for GPS denied navigation, magnetic anomaly detection, trace chemical detection, and RF sensing, for example. But when we develop these new type of magnetometers, it's important to consider what are the operating principles we want out of this technology. So here I've identified 5 important points to consider when we're developing this technology for these types of applications. And so first of all, we really want magnetometers that offer high dynamic range. And this is important because we want these magnetometers to work in the Earth's magnetic field, whilst at the same time detecting these very small magnetic anomalies. At the same time, we'd really like high bandwidth in these devices. So most magnetic signals that we're interested in detecting happen around the DC area, but they can extend all the way up to kilohertz. So it would be nice for a magnetometer to cover that range in particular. Importantly, if we can engineer systems that operate at room temperature, this would be fantastic. If we think about the current state of the art, which is squids that fly on the back of the aeroplanes, as you can see here, these operate at cryogenic temperatures, and this often leads to an increase in the size, weight, and power of these sorts of systems. And finally, if the magnetometer can have some versatility and either be used as a vector magnetometer or a scalar magnetometer, this would also be particularly advantageous in these applications. Now, if we can combine those 4 points that I just talked about and still arrive with a sensor that can deliver sub-picotesla per root hertz magnetic sensitivity, then we have a game-changing sensor on our hands. And at the moment, there's no single technology solution that covers all of those 5 points. And if we talk about where diamond-based magnetometers sit, we've achieved 4 of these points, but we're yet to achieve this sub-picotesla per root hertz magnetic sensitivity, particularly at DC. And that's exactly where this pitch and where our proposal is heading. So the opportunity that we see is that the community to date has really focused on the production of diamond using 100 substrates. And when we grow diamond on 100 substrates, we engineer these defects, these NV defects that we just heard Marcus talk about. They get engineered in 4 different orientations. And this is fantastic from a vector magnetic field point of view because we can probe the field in 4 different directions. But when we're talking about magnetic sensitivity, our sensitivity takes a hit when we have these 4 different orientations. And so it's been shown recently that if we switch to diamond materials grown on 111, that these NV centers can be grown in an aligned direction. And so this is really the focus of the proposal here today is to explore those substrates. There are additional benefits to 111 material, and I'll talk about those in a little bit more detail. So if I talk now about our scientific approach to this problem, so we've heard from Marcus about the NV center, so I won't talk too much about that, other than to say that we use the magnetic sensing component. So we're using the Zeeman splitting of the paramagnetic ground state to do the bulk of the sensing work. What I do want to talk about is the magnetic sensitivity of these systems. And the sensitivity can be described by this equation here. And there are 3 really important parameters when we're talking about the sensitivity of diamond-based magnetometers. The first is the line width of the NV transition, and that's this blue circle here. The second is the spin contrast or the readout that we receive from these sensors, and I've touched on that in the introduction. The third is the fluorescence intensity that we get back from these systems. Now, this is proportional to the number of NVs that we can engineer into the material, and it's also proportional to how well we collect the light emitting from these NV centers. Now, in this proposal, we aim to address each of these key points to really drive down this magnetic sensitivity. And so I'll tell you how we aim to achieve that. So the first thing we're looking to do is reduce the line width of the NV transitions. The way we plan to do that is to grow isotopically pure 111 diamond. And we're going to do that at our state-of-the-art fabrication facility located at the University of Melbourne. Now, we recently received funding from Defence Science and Technology Group in Australia, and we've recently achieved Australia's first isotopically pure carbon-12 material. So we have the capability to do that. Importantly, we've also received $1 million to increase the fabrication capability of this centre. So we'll receive a second state-of-the-art diamond reactor, which will be specifically focused on quantum grade material. And we hope to be able to use that reactor in this proposal. I've mentioned the fact that we can expect gains from the spin contrast. So when we move to 111, we expect to recover that factor of 5 that I talked about before. And in terms of the photon collection efficiency, we've published work recently which has looked at structuring the surface of diamond. So if we create these diamond waveguides on the surface, we see a factor of 10 increase in the intensity from the NV being let out of these surfaces when compared to a flat surface, for example. So this factor of 10 also comes into increasing the sensitivity of these systems. Now, in this proposal, we aim to develop these novel materials, but we need a way to characterize their performance. And so that's going to be carried out in our state-of-the-art sensing labs that have been established over the past 10 to 15 years. And so we're well set up to analyze all of these, all the sensitivity parameters and the noise characteristics of the sensors. In terms of the team that we've established for this project, so we have a very interdisciplinary team and complementary team. So we've got experts from the University of Melbourne, RMIT University, which is down the road, and also Defence Science and Technology Group. And our aim is to really develop novel diamond material that can be used for sub-picotesla magnetic field sensing. I've articulated the pathway that we expect to get there, and the outcomes of this project will be benchmarking this new novel material with the current state of the art. We'll determine whether 111 diamond is the direction that the field should be going. And the information that we obtain from this study will really help inform the NV theory models that we have for this system. In terms of the capabilities, we have everything we need. We've got the diamond fabrication facilities, the isotopic engineering capability. We can characterize the materials. We have prototype engineering experience, and we have detailed spin bath modeling expertise within the team. The impact of this potential technology on defence, I touched on this earlier. If we can really reach this goal of sub-picotesla per root hertz, then we can start to open up new opportunities beyond GPS-denied navigation. We can really start to look at magnetic anomaly detection, RF sensing, and persistent magnetic field monitoring. So all of these become possible with this type of material. In terms of our track record, we've got a long history in terms of magnetometry and quantum sensing. So I've listed our team's contributions in that area in the references section of this poster. And I'll also note that we've also worked together over the past 10 years to deliver the world's first diamond-based quantum technology. So we were the first to commercialize the diamond single photon source, which was also based on this NV technology. So we have the capability to take the technology from the bench to the market. Now, I might leave the key challenges for the discussion and move to future work. So our team really sees this Accelerator program as an opportunity to continue to drive the sensitivity of these extraordinary sensors down. So at the moment, they're sitting at about 50 picotesla per root hertz. And we hope within this 12-month period to drive that down to, as I said, sub-picotesla. If we can do that, then we really start to open up these new application areas. And we hope that this Innovair program provides the pathway to work with our collaborators in the US to start to achieve some of these goals. So with that, I thank you all for your attention, and I'm happy to take any questions you may have.
Thank you very much. The paper is now open for questions. And as a side note, Matt Squires, we were having trouble hearing you. You were very faint. So if you're able to speak up, that would be great. And hopefully we're able to hear all the other panelists as well. So questions.
So I'll start again. This is Carl Williams. David, very, very interesting and novel things. I mean, both the carbon-12, high purity carbon-12, as well as the one-on-one service. So you're solving some really hard technical R&D problems. But what the question I have is how confident are you that in an operational moving environment that you're solving the right problem? And can you kind of address that? Because again, your platform is going to be on a plane or something else.
Yep, absolutely, Carl. So that's a great question. So in this particular proposal, we're not engineering the solution in terms of the how these would be deployed, but we're certainly working with partners who are. So Lockheed Martin, for example, have released a dark ice magnetometer that they're deploying on ships based on this technology. So there are field deployed systems based on NV that are out in the field now. And so we're partnering with some of those people. So I think what we're trying to develop here is to see whether this material pathway will lead to a more efficient sensor. And if it does, we can immediately deploy this material in these field deployable devices that already exist. So it wouldn't be us per se building the complete sensor solution. We'd certainly be looking to partner with others to test those sorts of questions out.
So you mentioned the growth method in terms of reading out your spin contrast and saying if you follow the 1-1-1 orientation, you expecting to get a better readout. But is that really the case? Don't you still experience sensitivity degradation even with the new orientation because you still have the 4 components to still read out?
No. So with the 1-1-1, you can tailor your growth condition such that the NVs are grown in only at a single orientation. So that's the real advantage of this material. So with 1-0-0, we just get a random distribution of these orientations. But due to the growth dynamics and the plasma dynamics of the growth, when we're looking at a 1-1-1 surface, these NVs preferentially align along a single direction. And so what we're looking to achieve is maintain that alignment through a relatively thick layer of diamond. And if we can improve that, if we can do that, then we've got a really sensitive magnetometer with a single orientation. So this would be more for a scalar magnetometer application. Does that answer your question?
Yeah.
Can you hear me?
Yeah, I can, Matt. Yep.
Okay. So I think that's the follow-on question is you had mentioned that diamond in your introduction, the difference between diamond and vector magnetometry. Can you explain a little more about can you make this to be a vector magnetometer, or is it purely a scalar magnetometer? And then many times, at least some of the atomic sensors have dead zones. Would this have a dead zone in its sensing capability?
A dead zone meaning what?
When the magnetic field's out of a certain angular range, it wouldn't be able to sense that level or sense the magnetic field.
That's a good question. I haven't thought about that too much. In terms of the vector magnetic field difference, so there's certainly, so NV systems are perfect for vector magnetometry. When we work with these 1-0-0 surfaces, we get an inbuilt vector magnetometer. The issue we have at the moment is that the sensitivity we're getting out of those systems is not at the spin projected limit. So we're still orders of magnitude away. And the question is that a materials problem, or is it a fundamental engineering challenge to read out the sensors at that level? And so what this proposal is really doing is looking at the materials challenge, simplifying the situation so that we've only got one orientation, and asking the question, how good can diamond be, and can we get to this spin projected limit? If we can answer that question, then we can take what we've learned from this study and try to reapply that in terms of the 100 case. But it's really about understanding what are the fundamental limits of this sensing technology itself. If that kind of answers your question.
Thank you, Professor Simpson. With that, we'll call the paper to a close, and I would now like to welcome Dr. Paul Lapata, Principal Director of Quantum Science, Office of the Undersecretary of Defense, who will be speaking during this 10-minute break. Thank you. We'll be back shortly.
Hello to all the participants of the $1 Million International Quantum U Tech Accelerator. Esteemed guests, Dr. Roper, Dr. Neil deGrasse Tyson, Rear Admiral Selby, Dr. Welsh, Colonel Lawrence. If you are aware, quantum science research, in fact, is not new to the DoD. DoD labs and organizations such as AFRL, AFOSR, ONR, and the Army Research Laboratory have been funding some of the leaders in basic research of quantum science for more than 30 years, both internally at DoD labs and externally at universities, federally funded R&D centers, and industry labs. DoD funding for basic research efforts have led to many of the breakthroughs that have inspired the field today. As I mentioned, quantum science is one of the top 11 modernization priority areas in the Department of Defense. If you look at the U.S. National Defense Strategy, it provides three main lines of effort: force modernization, international engagement, and business process modernization. It is noteworthy that this event works towards all three of these lines of effort: improving the state of quantum science research, engaging with the international researchers, and taking advantage of this innovative approach to bring in new and exciting ideas. It's my hope that this event will discover some new researchers who have never before been involved in any DoD or Air Force research efforts. Quantum science is not just a defense priority. With the National Quantum Initiative and commercial and international interests in the field, there's a great deal of excitement in quantum science and quantum technology within the US and around the world. Your participation in the Innovare Advancement Center's quantum challenges and activities will help advance our shared understanding of the basic principles of quantum science and point the way towards new opportunities to take advantage of quantum technology down the road. The DoD Quantum Science Research and Development Program is diverse and cross-cutting. It ranges from basic research efforts that explore the edges of what is possible, to early prototypes, and ultimately to the development of technology that will have a mission impact across the joint forces. I tend to break up quantum science into four broad categories: atomic clocks, quantum sensors, quantum computing, and quantum communication. Part of my job is to develop and maintain a quantum roadmap for DoD that addresses all these four areas, working with the services, joint staff, and combatant commands to ensure that acquisition plans, future warfighting concepts, and other plans are commensurate with DoD's quantum science roadmap. A continued commitment to basic research in quantum science is definitely part of this roadmap. And opportunities like today's Tech Accelerator are how we accomplish this. I look forward to following the Innovare Advancement Center's activities and commend AFRL's leadership, the Griffith Institute, Oneida County, State University of New York, and all those who had a hand in making this exciting collaboration a reality. Breakthroughs in quantum science today will be felt for many years to come. Thank you. and good luck.
Welcome back. Our next presenter is Andre Luton from the University of Adelaide. Please unmute yourself for a mic check. When you're ready to begin, click the Start Presentation button on your screen, and that will start your 10-minute presentation. Professor Luton.
Thank you very much. Can you hear me?
Loud and clear. Thank you.
Terrific. Well, thank you very much to the organisers for giving us this opportunity to pitch our idea. One of the motivations for this pitch was the fact that we really wanted to demonstrate explicitly the value of quantum sensing. And to me, this value is best demonstrated in a domain where there is both a definitive need for the technology, but also at the same time in a circumstance where the current technology cannot deliver a solution. We believe that just such an opportunity exists in the domain of high temperature sensing. As such, this project will really develop and deliver a proof of principle demonstration of an inherently accurate primary thermometer. And by a primary thermometer, I mean one that's really free of the need for any calibration, and that will deliver in situ measurement of extremely high temperatures. In fact, you know, the ultimate physics limit of this system is potentially operating up to the melting point of sapphire around beyond 2000 Kelvin. So you might ask why it's important to do high temperature thermometry, and the answer is that accurate and stable thermometry at high temperatures is really difficult. In fact, current high temperature thermometers are hand-built devices that require frequent calibration. Indeed, they even require calibration after being heated up and cooled down, or after being shaken or vibrated. Instead, this project will deliver an atomic thermometer that can break through these restraints and thereby demonstrate a real-world benefit of quantum sensing. The project also intends to establish the operational limits of this type of atomic thermometer. And depending on the accessible temperature range as determined, we can see some diverse applications, for example, in monitoring combustion in jet engines or elsewhere, hull temperatures in aircraft or spacecraft, as well as giving accurate data for annealing and tempering of alloys. Our approach requires only a simple passive device to be in contact with the element that's in contact with the temperature that's of interest to be read. And this can be read out remotely and without the need for any power or mechanical connection to the sensor head. If we can see the atomic cell, then we can measure the temperature. So I've got a little bit of a video showing the idea of, that we're essentially going to make a transmission measurement through a cell of moving atoms. And it's really the fact that in 2019, the International System of Measurements decided to change the definition of the Kelvin and the degrees Celsius, so that now it essentially focuses on measuring the average energy of the molecular motion of the substance, rather than a much more complex definition that relied on a particular material sample. And the conversion, the exchange constant, if you like, between energy and temperature is the Boltzmann's constant, which has now been defined as a fixed value. So this new definition, where essentially temperature is related to the kinetic energy inside the substance, has really suggested a simple and elegant method to create a primary thermometer. The idea is to effectively measure the absorption frequency of an atom, and that will be modulated by the longitudinal motion of that atom with respect to the direction of the laser beam. And if we use that Doppler effect and do a precise laser spectroscopy of an absorption line of an ensemble of atoms, then we can essentially back out the velocity distribution of those atoms. And this really connects the absorption line shape to the velocity distribution. We can then use statistical mechanics to link that velocity distribution to the thermal energy in the system. And so those three steps really allow us to determine an accurate value. Perhaps in a slightly more numeric form, if we start with considering an ideal gas with a pure maximal Boltzmann velocity distribution, and first consider ideal atoms that essentially interact with laser radiation just as a delta function, an infinitesimally narrow resonance, then we would in fact observe a Gaussian-shaped absorption feature, and that has an E-fold line width given by this expression here. And we can see that if we make an accurate measurement of that E-fold line width on the left-hand side, then essentially we can relate that to temperature with an ensemble of either very accurately measurable parameters or defined parameters. However, real atoms, unfortunately, the real world is a little bit more complicated, and real atoms show a more complex line shape, one which reflects both their natural broadening, the fact that they have a finite lifetime, as well as this external motion. And so the actual function we see in an absorption line width is the so-called Voigt function, which is a convolution between this natural line width and the Gaussian line width. So that's no big problem for us. We're capable of doing nonlinear fitting. The key parameter is that we now need to understand very well what that natural line width is. And as long as we understand that the excited state lifetime of the atom, we can back out temperature from that system. Okay. So we've been doing this measurements already, but around room temperature. And I wanted to show you, essentially the setup that we have for doing this. So I apologize for that. So the essential setup is that we have a laser that we can tune very accurately. It's referenced back to a frequency comb so that we know what the frequency is, and we scan that over the absorption line of some cells. We see here a picture of those cells inside a large copper block, and we essentially measure the transmission function through those cells with high accuracy. Those cells are then mounted inside some magnetic shields and then installed inside a vacuum system with a bunch of optics on the top. And so we're effectively able to measure the temperature remotely of those cells inside that vacuum chamber. The intention with this project, and it's specifically because of this project that we will head in this direction, is that we'll take those cells and put them into a very high temperature furnace and measure the temperature inside that, something that hasn't been done before. So what does the data look like when we back that out? Essentially, the plots down here show you indeed what we see. In this case here, we see a couple of absorption lines. Well, they just disappeared off the top of the plot. There we are. So there's a couple of absorption lines. If we fit those absorption lines with our theoretical Voigt function, what we see is off resonance, we see some ripples in the transmission at about the levels of 30 parts per million. And within the resonances, we see some other structures which relate to the fact that the absorption function is actually not quite a Voigt function, associated with the fact that we're probing that atomic system and do elevate some of the atoms into the excited state or induce optical pumping. But our colleague, Tom Stace from the University of Queensland, has modeled this in depth and has corrected that to second order. For the off-resonance structures, these are associated with, sub-part per billion unwanted reflections that are in the system that give rise to etalons. We can measure those and allow for those in the fitting algorithm by measuring what's going on off-resonance. Once we correct for these multi-order atom-light interaction structures and also allow for these etalons, we have obtained residuals that are shown on the bottom panel that are down at the level of a couple of parts per million, which are consistent with photon shot noise. So we've really pushed the transmission measurement down to the fundamental quantum limit. So one might ask, what are the ultimate limitations in this system? And these limiting our accuracy at the level of about 100 parts per million, which is about 1/10 of a degree out of 1,000 degrees, and precision at the level of 6 parts per million in measurement if we integrate it over an hour, which is just a few millikelvins at that temperature. We've identified those limits. They're coming from the fact that the probing laser is not as pure as we like, and also these etalon structures. And we've identified the pathway to overcoming both of those by developing a new highly agile and narrowband probe laser that is only 5 hertz wide, but capable of tuning over 10 to the 12 hertz per second and tunable over 30 gigahertz while we have complete knowledge of that. So in summary, the funding that would be provided through this scheme would allow us to explore a new regime for this experiment in the high temperature domain. And it would really allow us to demonstrate the power of quantum sensing in a regime in which it's much more than just a breakthrough metrology technique, but is really very useful. So I hope we were able to do this together.
Thank you very much. The paper is now open for 5 minutes of questions.
Good morning.
Good morning.
My question relates to the use of this high temperature sensor. Could you expand more on the defense applications for this sensor?
So I think that there are a couple that sort of immediately spring to mind. So one would be in understanding essentially the temperature distribution inside, for example, a jet engine would be a really interesting regime in which one can be confident in an environment where there is high vibration and high temperatures that with a standoff detection, one's able to measure, effectively the temperature distribution inside there. Another possibility that strikes me is in material process control. So in order to get maximum alloy strength, it's very, very important that one has a very good understanding of the temperature during both the initial production of the material, but also through the annealing and tempering processes. And so I can see that in both of those immediate applications, that sort of materials area, but also in sort of, monitoring complex systems, there's some possibilities there.
Thank you.
So you mentioned the collisionary effects in the cells. How do you actually intend to address those? And looking at the system that you show, it's quite a large system. And in terms of practicality, where do you see that going actually?
Thanks very much for the question. The first question is excellent, but I'll deal with the second one first because it's a little bit easier. We can certainly imagine that the sensor itself, could be certainly smaller than a cubic centimeter. Essentially, one of the advantages of working at high temperatures is that the density of the gas is higher, and so one can use a very, very small cell. The complexity of the system that you've seen here is really because we were trying to push in the accuracy, but the sensor itself is merely just the little gas cell. On your first question about collisions, you've actually touched on one of the very important points for our system is the use of alkali vapors rather than molecules means, in fact, the mean free path of the atoms is larger than the cell itself. And so the interatomic collisions, which are exceedingly difficult to model in any analytic way, are actually absent in our system. So some of the competitor products have made use of methane or water or carbon dioxide as the material for doing thermometry. But by using an alkali, in this case it's cesium, we have a big advantage because we have effectively eliminated collisions, and the very strong absorption cross-section of those atoms also means that you can build a very small cell.
Andre, I had a question. This is Matt Squires. Can you hear me?
G'day, Matt. Yeah, very well. Good to see you.
Good to see you too. You talked about darkening of sapphire, and that certainly happens at elevated temperatures. I'm wondering if there's a trade-off with your vapor density. You haven't touched on that at all, but can you just comment on the darkening and at what temperature you expect that to come into play and how you would mitigate that?
So I guess that's an open question, and one which I think this project's really going to address. We have some reasonable confidence that you can get to 1,000 Kelvin before we have a problem, like to do with the cesium going into the sapphire. And there's certainly clear data to 1,600 Kelvin for sodium within sapphire, but we're not clear on the absolute limits in relation to cesium. In terms of density, we're certainly going to operate in a regime which we're not used to so far, where essentially it's all vapor. At the moment, we operate in that regime where there's both solid and vapor. And the challenge with being in that regime is that there's a very strong change in the density as a function of temperature. So we're operating in the regime where essentially it's a gas phase.
So this Carl Williams, I'll ask a quick question. Again, quite elegant. Can you talk a little bit about the thermal contact issue? Because of course you need to transfer this, and this part of why you put in copper, I assume, and everything else. But how does the thermal contact issue limit or your potential thermometer?
So if you're asking about the thermal contact between the gas and the sapphire itself, then essentially it only takes 2 to 3 bounces of an atom off the surface in order to thermalize. But I guess you're asking a question more about the practicality of making a good contact between the sapphire and whatever you're interested in actually.
Yes.
And my apologies, but unfortunately we have to cut it off right there. Thank you very much, Professor Luton, for your great talk this morning. Up next, we have Philippe Bougie from the Institut d'Optique Graduate School. Please unmute yourself for a mic check. And when you're ready to begin, you will click the Start Presentation button on your screen, and then you can start your 10-minute presentation.
Okay, hello, can you hear me?
Yes, very well.
Okay, very good. So let me try to... I'm trying to click on Start, but doesn't seem to work. Oh yeah, it's working now. Okay, well, thank you very much for giving the opportunity to expose our view of how to use a quantum advantage on inertial navigation, and especially how to reach GPS-denied navigation with quantum sensors. So the question we want to address on that topic is, can we navigate without the GPS? Okay, that should be working. And so as was exposed earlier, the most common way to navigate today is to use external references. So if you have a view to a beacon, or the best beacon being actually satellites with extremely well-known position, you can actually triangulate your position by using, for instance, the distance measured with your GPS receiver from different satellites. So this works very well. The accuracy is as good or even better than a few centimeters. But of course, if you don't have the direct view of these beacons, these satellites, there is no way you can actually get your position accurately. And this is especially hard if you have clouds, if the GPS is attacked, or if you are underground or underwater. In that case, you need to rely on inertial navigation, which means that you need to basically measure the acceleration vector, so the acceleration plus the direction in which you are moving, and this is usually done with a 3-axis accelerometer plus a 3-axis gyro. And as was said earlier as well, there are usually strong biases in these systems. Like, for instance, for accelerometers, the best bias that you have for navigation grade accelerometers are of the order of 10 micro G, 10 to the minus 5 meters per second square. And this leads to typical errors in position of about 100 meters at a typical period of 1 hour and a half. And it can be even worse if you look at the impact on gyros, basically. So the challenge here is to be able to navigate without an external view and reach a position error in hours, which is much better than that, the level of a few meters, for instance. So for that, we want to basically exploit the use of quantum sensor, and more particularly atom interferometers that will be realized by using ultra-cold atoms and lasers to manipulate them. This is not a new concept or a new technology. Atom interferometers have been developed now for more than 20 years. And nowadays we have very good gravimeters, very good accelerometers, even very good gyros, even commercial ones that can actually be transported to many places. The picture here is an example of a gravimeter that has a performance at the level of 10 to the minus 9 G, 1 nano G, and which is currently working on a volcano the Etna in Italy to record the mass variation in the volcano itself. So the challenge here is really to use this technology and like transport it into a more transportable devices for navigation. So why are we so keen on using this atomic sensor? So this small cartoon is explaining a little bit about sensors, but since you already heard a little bit, I will jump straight to the end of it. So you, to make these atom interferometers, you use cold atoms that behave like matter waves, and you apply a series of laser pulses. I need to pause it here. And in that case, you have an enclosed area that for an interferometer, and the interference fringes at the exit of this interferometer will be sensitive to the phase difference between the two arms of the interferometer. And this phase difference can be directly affected by inertial quantities like acceleration or rotation. That's how you basically make an accelerometer or a gyrometer. In that example, the lasers are vertical, and the sensitivity of this interferometer will be mostly to the vertical acceleration along the laser beams. If you apply some fairly simple rule of thumb of what is the sensitivity of the sensors, you find out that the minimum acceleration will be basically proportional to the ratio between the laser wavelengths and the time between the pulses squared. And with a typical time of 100 milliseconds, you can reach a sensitivity of about 10 nanometers per second squared, or it's equivalent to basically 1 nano G. So that's the sensitivity, but if you look at the scale factor, the only quantities that are actually here are time and wavelengths, and they are well known and very stable. That means that those sensors can be exact. You know exactly what you are measuring, and long-term stable, which is exactly what you want for navigation. So this is maybe the best candidate for long-term navigation without GPS, although there are lots of challenges, and the biggest challenge is basically to apply those sensors in a mobile environment. Why is that? Because in any type of vehicle, like a plane or a boat, you have rotations, you have vibrations, and these vibrations will basically put some phase shift on your interferometer. And if you just like plug your system strap down on a boat or on a plane, you don't see any fringes, or basically you're not able to retrieve any information out of these fringes. This can be actually easily sorted out by the fact that you know very well your sensor, even though you don't have any signals to look at it, and by hybridizing the classical sensor to this quantum sensor. Basically, you record at high data rate the acceleration noise of your system. You're able, basically, by coupling them, to reconstruct the fringe. This is an example of the method how to reconstruct a fringe, and you recover even if you were not able to get it at first sight. You can recover the fringes. So these are experiments that were performed in a plane some years ago, and the fringes were recovered after we were basically doing the experiment in the plane. But the challenge here is, of course, to have real-time compensation and real-time hybridization that will allow to get the signal while you are moving, basically. So that's the challenge of the program we want to propose here. So there are three aspects to it. The first aspect is really to develop a compact 6-axis sensor. So when I speak about 6 axis, that's a 3-dimensional acceleration measurement and 3-dimensional rotation measurement in a single compact system. You need all these aspects to be able to actually infer the position from the inertial quantities. This can be done in a first way, in a sequential way, where you apply a different configuration of atom interferometers by changing the laser pulses and changing the laser configuration. And at each time, you can measure 1 or 2 quantities. This is an example of the first experiments that were where we were able to record actually a 3-dimensional accelerometric quantities with a single device by just changing the orientation of the laser beam used for interrogation. What's interesting on that picture is that by using this 3-axis accelerometer, we're able basically to integrate over a few hours the acceleration, which here was not moving. We were just changing the orientation, and then thus at a level which is far below the level of commercial grade accelerometers. Of course, this is good, but we can do better if we are able now to not only record one quantity at a time, but all the inertial quantities, the 3 acceleration and the 3 rotation, with a single device. And this requires to change our paradigm of making atom interferometers by now not using sequentially a sequence of single beams that split in a coherent way the matter waves, but using at once a configuration of 3 beams in the 3 dimensions that will actually engineer a matter wave in 3 dimensions. This is something that we have studied theoretically and that looks very promising. By using the proper configuration of laser and frequencies, you're able really to engineer the matter wave in 3 dimensions the way you want. These are 2 examples of what you can do. And by doing that, we can actually make engineer some loops of interferometers that will be sensitive to some quantities, but not only can we actually make a single one, we can actually at once create many interferometers. It is shown here on the picture. We have 4 interferometers that all are sensitive to different quantities. And by retrieving this information in a single measurement, we have all the information about the interferometer. And the last challenge that we want to do on that is to implement these systems to actually connect it to a classical navigation unit that will give you the high data rate for navigation, and test it with all the algorithms in order to get the proper recalibration between the inertial navigation unit and the quantum sensor. Thank you very much.
Thank you. The paper is now open for 5 minutes of questions.
This is Matt Squires. Can you hear me?
Yes, loud and well. Hi.
I'm wondering how you do the simultaneous readout and you distinguish between the different axes. I'm just wondering how you distinguish what is your readout method? If it's fluorescence, I'm trying to understand that.
Yeah, so in 2 dimensions, so like the scheme that's here, you can actually rely only on fluorescence. You just have a series of different pulse configuration, as you usually do for clocks or even for sensors, and you're able to retrieve all the quantities. Otherwise, you can use an ultra-cold sample of atoms in that case, and use a CCD camera detection in which you will have a clear view on all the outputs of your interferometers.
Follow-up question, as you split off into multiple axes, does that reduce your the number of photon, or not, the number of atoms that are available to each axis, and that atom number determines your fringe contrast? Can you comment on that?
So you're completely right. I mean, if you make 3 or 4 interferometers at a time, you have 3 times less atoms for 1 interferometer. It's not a big problem so far. Well, first, for navigation, the sensitivity does not need to be at the nano-G level. So, and this is something you can easily reach. And usually the signal-to-noise ratio you have of those sensors is of the order of 100, so 10 to the 4 atoms, and you're able to have many more atoms available for interferometry. So it's not a limitation.
So I know you mentioned for the 2D that you potentially can use fluorescence as your readout scheme, but what readout scheme are you actually using? Because it's not clear I understand that.
Well, so now we have not worked yet. We did not start working yet on this 2D concept. It's so far it's only theoretical studies. What we are using with our current devices, the one, for example, which is doing the measurement sequentially, is fluorescence. But we also have CCD cameras used on devices as well. But the fluorescence is the most easy way to get the signal so far.
Philippe, this is Carl Williams.
Yeah.
So let's go back to and briefly describe how you're going to get to 6 axis all at once. So is it going to be different interferometers? Or are you going to be pulsing in different directions? So, because you've described some of the approach, but how do you get to fully to all 6 axes?
Okay, so let me maybe try to shine this again. If no, it's not working. Well, if you if you use the three dimensions, so like you have Bragg or Raman diffraction beams in the 3 dimension at once, but with a slight different frequency between them, so that the detuning or the resonance for each beam is slightly different. So in that case, you can really select which states, which momentum states you couple with one laser and not the other one. And so from that, you can actually take a single cloud of atoms, for instance, and decide that you will diffract with the 3 beams in the 3 direction only forward, for instance. And then in the second pulse, you can actually decide by changing the frequency to send them backward or to diffract them in the other direction. So you can make a cubic interferometer in some sense, where each phase represents one loop of interferometry at once. And then, of course, you have to look at all the outputs of this cube in order to retrieve the information.
This is Matt Squires again. So you've talked mostly about the accelerometer portion of it sounds like a Raman interferometer. Yep. Are you going to be also looking at the gyroscopic phase output?
Yeah. So well, so far, if you use like a small cloud of atoms and no beam, you don't have any. Well, very little sensitivity to rotation, because for that you need a transverse velocity with respect to your interrogation beam. So that's what we can achieve with this 3D configuration, because then you really have a loop in which you have sensitivity to acceleration for the 2 beams you're using in this 2D picture, for instance, and then the loop itself gives you sensitivity to rotation. So that's what we will look at exactly.
Thank you very much, Philippe. We'll need to end our paper right there, but thank you once again.
Thank you all.
Thank you.
Our next paper will be given by Antonio Sergio Sambra from the Federal University of Ceará in Brazil. Please unmute yourself for a mic check, and when you're ready to begin, click the Start Presentation button on your screen to begin your 10-minute presentation.
Okay, can you hear me? Can you hear me?
Yes, we can.
Okay. So let's see here. Well, good morning. Our project that we're going to present today is entanglement enhanced nonlinear fiber optic gyroscope for quantum navigation. Well, in this project, we are studying a nonlinear quantum fiber gyroscope. It's a rotation rate sensor. But the difference between this gyroscope and the classical one is that you are going to use entangled photons in a configuration using a nonlinear fiber optic setup in order to obtain a higher sensitivity of for the measurements of the rotational phase. The idea is to improve signal detection and go into the quantum limits of linear counterparts and to operate below short noise limits. We are gonna using entangled particles. And the idea here is to achieve a limit in quantum mechanics that's associated with the number of particles or photons you are looking for. Okay. So well, the interferometer, it has a very big revolution in the field of metrology. So you have possibility to measure differences in path length of less than 1 wavelength. In this case, the fiber optic gyroscope, it's fundamental for the initial motion, initial rotation systems. So in general, we can classify these interferometers in 2 types. The first one is resonator fiber optic gyros, and the interferometric fiber optic gyros, IFOGs and RFOGs. These resonator interferometric gyroscopes surpass the precision of the mechanical systems, and they are a key component in modern navigation systems. So in this kind of system, we're gonna study using a, we're gonna use a Signac geometry for the fiber, okay, which is in this geometry here, which is a fiber. We have here a coupler, and this length. So the input laser is going to the first fiber, and it split in two ways. So we have light going in one side and light going in the other side. So the difference in phase is going to be crucial for the recompose of the light in here. So for a rotation gyroscope, so there is an addition of phase for one direction of the light. So you can detect this difference and measure this effect with high degree of precision. If you are looking, for example, in the case of rotation of a system, for example, if you are talking about Earth rotation, we have something like 15 degrees per hour, okay, and for these gyroscopes, you need considering different applications, you may need, for example, 10 to minus 6 of this rotation rate, for example, for geophysical application, and depends on the application. It's going to be a problem. It's a limit in the system. One can say that the precision of optical interferometers is improving with the use of entangled photons. It will be a way to go to the Heisenberg limit, where the precision scales inversely with the total number of particles. In this case here, of course, the ring laser gyroscopes, they got some limitation. Yeah, and the idea here is to explore this limit and go beyond. Okay. Okay. In our configuration here, the idea of this project is to generate these entangled photons in a Mach-Zehnder interferometer and control the dephasing of the states to generate the entangled state. Okay. After this, we're gonna pump a ring resonator and explore the formation of new signals we use in far-wave mixing. Okay. And the quantum frequency of the entangled photons generated in a four-port micro-ring resonator, and using the far-wave mixing geometry. Okay. Oops. Let's see. Okay. Sorry. Okay, I'm having some problems here. Oh, sorry. Oops. In the four-wave mixing, have the pump of two frequencies, frequency 1 and frequency 2, and you're gonna generate two new frequencies at F3 and F4. Okay, so we need a phase matching condition, and the idea here is to have these two new frequencies that we call signal and idler in high and low frequencies compared to the pump frequency. And the idea is to exploring this geometry using the entangled photons to go to the limit of the number of operation, of the number of particles operation the system. So we hope that with this configuration of very low number of photons, we can increase very much the precision of the system. So in this configuration here, let's say, we're gonna explore the nonlinear effects of the fiber. So we expect to have a effect of this nonlinearity in the properties of the laser that is propagating the system. Okay. Let's see here. I can show you here the couple of equations that we have to solve to follow this problem. The problem is that in the four-wave mixing effect, we have a possibility of drain energy from the pump to the signal to both signals of Idler and signals, and use this two frequencies in the operation of the device. Okay. What the other point here that I have to emphasize is that this is a new configuration of a gyroscope. So we expect to have problems with, for example, the use of the detectors, for example. And the other point, the important point here is the possibility to explore nonlinear effects on the fibers. Because in these fibers, we can have Raman effect, we can have mixing, we can have generation of new frequencies that can interfere in the gyroscope operation. But the main objective is to have this effect in high precision. I mean, in the higher precision device, considering all these aspects. Thank you.
Thank you very much. Paper is now open for questions.
Hi, this is Carl Williams. People have long talked about the benefit of using entanglement to basically get beyond the Heisenberg limit. But of course, one of the prices you pay is signal to noise because of the number of entangled pairs and everything else. Can you actually talk about the potential payoff and how you're going to compensate for reduced signal to noise that comes from the total number of photons that you have in your system?
Oh yes, this is a problem really. Well, our idea here is first of all obtain the states, and that will be a master. This we're gonna pump the ring laser to generate the far wave mixing, and after this generation, we have to be sure that we have the untangled states doing let's say autocorrelation and those techniques. The noise, it's going to be a problem, really. I think that the noise in this case, it's going to be the major problem for this kind of configuration. But to expect to controlling, for example, fiber polarization and fiber loss and other kind of effects, we can control this level of noise. So we hope that this is gonna be a good way to see the problem. I mean, to
Other questions for Professor Sambra? I believe we lost some audio there. So Professor Sambra, we may have turned your video off to try and save bandwidth. So please, panel, proceed with questions.
So I'll ask a second question. Again, can you expand a little on what you see as the defense application relevance and whether you believe that given the signal to noise issue that this will actually be lead to something of value?
Oh, oh yes, yeah. I mean, we believe that, as I said, the noise it's gonna be our big, because work with low number of photons is probably it's gonna be a limitation of the operation of the device. But we hope that we can control. I mean, we can try to control these effects, and controlling the operation of the device and exploring the nonlinearity of the fibers. I think that we can have a chance to overcome this limitation a bit.
This is Matt Squires. Oftentimes fiber optic gyros are limited by the dispersion in the fibers. Can you comment on the dispersion? And
oh yes. Okay. Well, I mean, we're gonna try. I mean, different. I mean, possibilities of fibers. One of them is the polarization maintained fibers, of course, in trying to use photon polarization as a good thing for our side. And the dispersion, it's another problem. I mean, we have to choose very carefully the frequency of operation of the device, and of course the fibers, the dispersion, the minimum dispersion of the fibers. So we have to look for special fibers for this, in this case, even considering dispersion, which is very, I mean, it's a fundamental problem. And the other point is the polarization. I think that in this case here, we should work with polarization preserving fibers, because this is a good effect that could help. I mean, the efficiency of the device. So we have to choose different kind of fibers, and even there is some special fibers that we have dispersion decrease of or profiles that we can also use for test this kind of effects in this device. We can find in the market already dispersion decreasing and dispersion increasing fibers that we're gonna test. I mean, certainly, because I mean, this is a very important effect.
Thank you very much, Professor Sambra. We're out of time, so we'll need to move on to our next paper. Thank you.
Thank you.
I'd now like to introduce Peter Brereton from the United States Naval Academy. Please unmute yourself for a mic check, and when you're ready to begin, click the Start Presentation button on your screen to begin your 10-minute presentation.
Hi, can you hear me?
Yes, loud and clear.
All right, great. Okay, good morning. I am Peter Brereton. I'm an assistant professor at the United States Naval Academy, and I'm thrilled to be able to present some work that we're proposing as a joint effort between the United States Naval Academy Physics Department in Maryland and the Johns Hopkins Applied Physics Lab. And so I'd like to kind of emphasize 2 points of our motivation. One is the physics here. We're looking at really the fundamental interaction of a new or a newer solid state defect, which I'll go into detail here in a bit. But instead of looking at the single defect level and focusing on the quantum properties of the single quantum defect, we're going to be looking at the other end of the spectrum, and we'd like to look at the highly dense ensemble in which interactions between individual defects becomes important. The other thing I'd like to emphasize here is the institution at which most of this research is being done now and is being proposed to host, and that's the United States Naval Academy. We are one of the Department of Defense's premier service academies. We're undergraduate only. However, like our sister academies, we have a relatively significant research impact to the broader DoD enterprise. For instance, Naval Academy in fiscal year 19 was able to bring in $14 million in external research funding, and that goes directly to our research programs in close collaboration with Navy Research Lab and other DoD facilities, but our undergraduates are hands-on. So the broader impact of this program has some significant workforce development impacts. So I'd like to talk now about the defect that we're interested in, and I thank David and Marcus for presenting their work with the nitrogen vacancy diamond defect in diamond, because that's the canonical solid state qubit. In this work, we're going to focus on a relatively recently interesting, at least from the quantum metrology standpoint, defect, and that's the silicon vacancy in hexagonal silicon carbide. And so, like diamond, this is a point defect which lies deep within the band gap of a wide band gap semiconductor, and this leads to room temperature spin coherence in excess right now of on the order of 100 microseconds, which is relatively good in the solid state. Like diamond, the silicon vacancy in silicon carbide exhibits optical readout and initialization through an optical pumping process. And like diamond, the qubit states, which are the spin Zeeman split spin substates of the ground or the excited state, can be controlled by external microwave photons. But unlike diamond, silicon carbide has some particular material advantages. One is clearly cost and scalability. Silicon carbide is already well entrenched in the broader electric device fabrication industry, both in the defense and on the civilian side. Also, the silicon defect has emissions. It has emission in the near infrared, around 915 nanometers, which brings it closer to telecom-friendly windows. Additionally, kind of the energy structure that you see here for the silicon defect is unique. Whereas diamond exhibits, as we've seen, the spin 1 ground state with zero field splitting, silicon carbide exhibits a spin 3/2 ground state and excited state, and so that yields a richer manifold of anti-crossings and kind of a bigger space from which to apply magnetometry and external magnetic field interactions. And so, like diamond, theoretical work and kind of a flurry of experimental work have shown that the silicon defect has significant implications for quantum metrology, temperature sensing, strain sensing. But that's really focused for the most part at the single defect level. And the single defect level has technological implications for scalability. It requires significant fabrication. And in the case of silicon carbide, the single defect suffers from low optical brightness. So the way we're going to approach that and kind of bridge that gap is we're going to look on the opposite end of the scale. And so we're going to look at potentially the super radiant mode. And super radiance is old physics, as old as atomic physics is, and basically is the kind of the spontaneous collective optical mode that develops when quantum emitters are in a dense ensemble, essentially within a wavelength of each other. And what we see with super radiance and atomic ensembles is the hallmarks are pulsing with the intensity of scales nonlinearly with a number of defects and modification of the emission lifetime. But it's largely unexplored in the solid state, or at least in the solid state when we're talking about quantum emitters. And this is because of various reasons. So we became interested in this based on a demonstration at GILA in atomic ensembles of a super radiant laser. And this is a super radiant atomic ensemble in a bad or a leaky cavity. And what the GILA group were able to show is this novel laser, based on where the phase reservoir exists within the collective optical mode and is not contained by photons interacting with the cavity, can achieve orders of magnitude greater spectral resolution in the emission based on the quantum limit of a conventional laser. And this really got us thinking. The direct analog to this high spectral resolution is coupling that optical radiation to a magnetic sensitive atomic transition showed direct analogs to sensitivity benefits for quantum magnetometry. But this was in an atomic ensemble with the associated infrastructure related with that, and really could be miniaturized, or we could see it being miniaturized if you bring it down to the solid state. And there have been a few proof of principle experiments in diamond, strictly NVs and nanodiamonds, that show hints of this super radiant lasing capability, but it has not been explored in silicon carbide. So our proposal really looks to bridge that gap and show that super radiant coupling between defects within a dense ensemble. So there's really three phases. Much of this work has been started in one capacity or another, but the first is just generation of these high defect density samples. And we're doing that already now, both in-house at the Naval Academy through proton irradiation, but also in collaboration with NIST, looking at high fluence neutron irradiation, as well as commercial electron radiation. And so generating those defects and then working with our partners at APL to engineer those defects, really looking at the effects of annealing on defect generation and defect density. And the second key there is characterizing how this defect coupling affects the coherence time and the magnetic sensitivity of these samples. And we've already started some work, which is shown in our poster here, on our proton irradiated samples, which show clear indication of coherence time effects and Rabi damping based on density. And so in parallel, Seth Rittenhouse is going to lead our theoretical modeling. He's already started working with Sam Carter at Navy Research Lab and one of our students to start doing some ab initio master equation modeling of this unique bad cavity quantum optical system. And so if you have time, I'd love for you to look through the capabilities we have at the Naval Academy, which I lay out in the poster, and I won't go through here, but essentially we have a very unique experimental suite that is different from most primary undergraduate institutions and enables us to get this characterization done. So I think I'll just close by, this is a fundamental physics investigation. We're really looking at a new platform that is really relatively unexplored in the quantum sensing space, but shows great promise. It has great promise for all the DoD benefits that have been mentioned. Solid state sensors minimize your size, weight, power, and cost, if we're looking at silicon carbide, and has applications in a broad range of DoD and space navigation systems. And also we have a very strong component of workforce development. I say kind of tongue in cheek that we're educating the next chief of naval research, but we really are, and exposing them to the quantum technology, I think, is really critical. And our partners at Navy Research Lab, UMBC, are training the next generation of postdocs and researchers. And I'll close there, and I'm happy to answer any questions you may have.
Thank you very much. Paper is now open for questions.
So this is
go ahead.
So this is Mitari. I'm really curious to find out how you plan to quantify the coherence properties and the dependence of this SIC in terms of your super radiance. I'm not sure that came across very well to my understanding.
Yeah, so great question. So I mean, this is scoped really for a primary PUI, primary undergraduate institution, and so the tools I'm using are standard coherence measurements. So time resolved optically detected magnetic resonance. We've already have preliminary results we just published, looking at the density dependence of that coherence time for proton irradiated samples, which give us a very sharp defect density gradient through the bulk of the sample. But these are all relatively standard techniques, microwave, and we're essentially measuring the fluorescence as a function of time resolved microwave pulses.
Hello, Peter. This is Carl Williams. I assume just follow on a little bit on the superradiate laser piece. I assume you were talking about the experiment by James Thompson and in the bad cavity and everything else. And one of the things that comes out of that is, of course, it is an amazing demonstration and everything else. But of course, the counterpoint is there's no power, which means there's no signal. So tell me how you overcome that.
Yes, good question. And so we're scoping this program here really to get over the first hurdle, which is the demonstration of superradiance. We have hints of superradiance or defect coupling from our proton studies. Proton irradiation, we think, has its limitations. So that's a great question, and we're not addressing in this particular program, but absolutely that is one of the limitations of this this low photon number approach to magnetometry.
So I'll ask a second question that's really quite different. And again, on your magnetometer, can you talk about the potential sensitivity that the magnetometer might be able to demonstrate and compare it to what is currently possible in other solid state magnetometers?
Right. So right now, the state of the art for the nitrogen vacancy superradiance that we're seeing just about a year and a half ago is on the order of, we're talking 100 to 200 picotesla per square root hertz, which is well above the current limits we see from SURF and other technologies. We are hoping to get some theoretical information on where that lower bound could be, and there's indications from the JILA work looking at the atomic ensemble that could be below the picotesla per square root hertz.
So is there any, I guess, do you have any benchmark from your theoretical model for the 3/2 spins in comparison to what you expect for the magnetometer?
There are benchmarks for the single defect, and they're on the order of what you see from single defects with pulse protection on the nitrogen vacancy. I don't have any benchmarks for the coupled ensemble. I expect, due to the line width issues, it's probably going to be significantly higher than the single defect level.
Any more questions?
So you had mentioned that because of the different spin coupling, that it was a more rich system. Does that add additional complexity, or does it really add more sensing modalities?
So I think the answer is it does both. I mean, it was really only 5 or 6 years ago that we determined the spin 3/2 definitively. So we're still looking at those level anti-crossings, which appear to be the best kind of bistable for your detection capabilities. We also have indication of nuclear hyperfine noise, and we have a separate program working with Sam Carter looking at isotopically purified silicon carbide, which will be exciting, and to try to get a handle on how much of a boost we can get from some of these more complex anti-crossings.
Thanks.
Thank you very much. We'll end it right there. So thank you, Professor Burton. We appreciate your talk very much. We are now going to welcome Mr. Anthony J. Picenti, Oneida County Executive, which is the county that Rome, New York and the Information Directorate sits in. Anthony is an amazing supporter of AFRL and the Information Directorate and the Innovari Advancement Center, and the stand-up of it would not be possible without the county executive support. So I hope you enjoy his talk during the break. We'll be back in 10 minutes. Thank you.
Hi, I'm Oneida County Executive Anthony Picenti. I want to welcome you and hope you're enjoying the competition today. We're very excited here in Oneida County to showcase Innovari, the facility that has been built along with our partnership with Rome Lab the Griffiths Institute, and all that we've been doing in Oneida County in terms of quantum and in terms of technology is really a great opportunity for us to showcase and to be a part of this great competition. It's really exciting what we've been able to do up at Griffiths over the last several years. Griffiths, as you know, has been a part of our history in terms of the military and research, and certainly Rome Labs work over the years has led to so many different areas of intelligence, cybersecurity, and has played a major part in the national security of our country. So it's fitting that we're here again, and just across the street, just literally over the fence, Innovare has opened up. And this is the first of many, we hope, competitions that will take place in this facility. We've been a leader in technology in Oneida County. We continue to do that each and every day, as we have with this facility, but as Rome Lab has in its past, and as Griffiths has been the hallmark of that type of technology. Just down the road, more investment has taken place all around us that involves so many new aspects of what our community, our economy is becoming here in Oneida County. Cree is building just miles down the road a $1.2 billion fab with 200 millimeter wafers. Cree, as you may know, is a leader in the industry in electric vehicles and LED lighting. And we're really excited about their opening in the next couple of years. We're also building in the city of Utica a new regional state-of-the-art hospital, which will bring to fruition all of the technology that is necessary in today's need for better healthcare. We only know too well in dealing with the COVID crisis what we have in front of us. Also, many other investments are taking place. Our work with drones at Griffiths International Airport, the UAS test site, one of only 7 in the United States, and the New York test site, as we refer to it, is key to the development of UAS systems as we expand our technology capabilities over the years. So we look forward to what comes out of Innovare, not just today, but for years to come. We want to be the leader in quantum, in all that is leading in cybersecurity as we have been, in UAS technology, in electric vehicle research and development, in healthcare, and all of the other aspects that we have been focusing on as a region and as a county. I'm proud of what we've accomplished. I'm proud to have you here with us today, whether it's virtually or whether it's in person. And hopefully, in the months to come, we'll have more in-person capabilities as we move through this crisis. But for the time being, thank you for being here. Thank you for being part of this exciting, really landmark competition that will lead us into the future and to so many other possibilities that can happen right here in Oneida County. Thank you for what you've done. Thank you for what you continue to do. Let us make Rome and Oneida County the quantum runway for development at Griffiths International Airport. Thanks for all you do, and please stay safe.
The program will resume in about 1 minute.
Welcome back from our break. Let's roll right into our next set of pitches. Our next finalist in sensing is Spiros Gallus from SUNY Polytechnic Institute. Please unmute yourself for a mic check. When you're ready to begin, Spiros, please click the Start Presentation button on your screen and your 10-minute presentation will begin.
Can you hear me?
Yes, very good.
Okay, let me start. All right. Good morning, everyone, and thank you for attending this very intriguing virtual event today. I'm very excited to present my group's research proposal today on the design, development, and fabrication of novel solid-state single ions for quantum plasmonic sensing. So I'm going to start off with the research motivation, the vision, if you like, behind our research proposal, which is to demonstrate on-demand integration of erbium ions that emit at a technologically important wavelength of 1540 nanometer in nanophotonic structures. And these structures are composed of an array of ultra-thin nanowires, which are effectively coupled to plasmonic nanocavities, as you can see on the left and the right-hand side of this figure. We will then leverage these devices to study their light-matter interactions and then engage these two concepts in order to realize a scalable on-chip platform for quantum sensing. So what I've just described, and I think to make it a little bit more digestible for you, is illustrated in this cartoon, the main panel, where you can see that the single photon emitter, depicted as the red sphere, can act as an isolated quantum system. For example, it can interact with an external electromagnetic field at nanometric proximity, and this interaction can cause a detuning between the emitter and the cavity, which can result in the modulation of its photoluminescence. So we can use these kind of interactions to establish quantum sensing for electric, magnetic field, strain, and temperature. Moving forward to the second panel, here the question is, what is the technological and also scientific, if you like, gap that we're trying to fill with this proposal? So recent research efforts towards the development of a scalable solid-state quantum devices, such as quantum sensors, single photon source, if you like, have been hindered by the lack of available fab-compatible material platforms for one, and by the need for high sensitivity and high spontaneous emission rate, which both require the accurate placement of single emitters in the device. So what we propose here in order to address these challenges is a deterministic integration of erbium ions in fab-compatible silicon carbide nanowires, and also into the nano-sized mode volume of plasmonic cavities, which can substantially enhance the spontaneous emission rate of erbium ions. So somebody may say here, let me scroll down. So somebody may say here, okay, this sounds very promising, but what is the innovation that you bring on the table which can make this happen? So let me address this by saying we have recently demonstrated in nanophotonics state-of-the-art high accuracy placement, less than 10 nanometer, of erbium ions in defect-free silicon carbide nanowires. These two demonstrations are key building blocks towards the development of next generation of scalable on-chip quantum devices, which will require the proper engineering of the single emitters, and also will require the minimization, if not reduction, of defect densities in these devices. This becomes even more important. Let me scroll down. If you consider the challenges which are associated with the integration of, please give me a second, of single emitters into optical resonators, including plasmonic nanocavities. For example, efficient coupling to these devices requires the accurate engineering of both the position and also orientation of these emitters. So let me click on this figure. So this can be seen in this figure where our numerical calculations as predicted, as expected, show that the parcel factor decreases substantially in figure B here, with increasing distance between the emitter and the metal. And the same applies for the orientation of the emitter in figure BC, with respect to the cavity. Here 0 degrees corresponds to the direction parallel to the length to the axis of the nanowire. So how are we planning to tackle these two challenges? For one, the nanometer scale proximity between the emitter and the cavity can be satisfied, can be met due to the ultra-thin dimensionality of the proposed nanowires, which is less than 10 nanometer. And this is well within our reach of nanofabrication strategies. Now, as far as the orientation is concerned, we can take advantage of the anisotropic dimensionality of our nanowires, where the width of the nanowires is much smaller with respect to the emission wavelength of erbium ions, 1540 nanometer again, and that results in an anisotropic absorption and emission behavior for the erbium ions. Let me show you the next figure. So this is presented in the last figure in this panel, where we have demonstrated preferential polarization emission from the nanowires, again, due to the anisotropic dimensionality of the nanowires, in contrast to the expected isotropic emission behavior when erbium ions are implanted in bulk thin films, which is the bottom part of this figure. Now, I would like to slightly switch gears and move into the two major tasks associated with our proposal. So in task one, as already mentioned, we plan to demonstrate deterministic placement of erbium in silicon carbide nanowires by leveraging our scalable and powerful fabrication strategies recently developed in my lab, and also by taking advantage of our unique capabilities at SUNY Poly, which includes our ion implantation technology. We have successfully demonstrated integration of an ensemble of erbium ions into ultra-thin nanowires, 10 nanometer. And another key property of these nanophotonic structures is that they exhibit an absorption cross-section for erbium ions, which is 2 orders of magnitude larger than typical benchmark values in erbium-doped bulk materials. So this is another important photophysical property which was enabled by our novel nanofabrication and defect density, reduction of defect density, and also device design. We will then experimentally, if you scroll down, we will experimentally measure, characterize these nanostructures by means of photoluminescence spectroscopy, and also by underbalancing measurements using our single photon microscope system, which is equipped with state-of-the-art superconducting nanowire detectors. In parallel, we plan to investigate the emission properties of erbium as a function of the local environment by means of electron paramagnetic resonance. Now, regarding task 2, here we aim to investigate the light-matter interaction in these hybrid nanowire-based plasmon devices using our integrated methodology, which includes both numerical calculations and modeling, and also the fabrication of corresponding prototypical devices in an iterative manner, with the vision, the goal, if you like, to demonstrate distinguished electric and magnetic field enhancement. It is worth highlighting here that the parameters used in these simulations and modelings, including the results I'm presenting today, are well within our reach of our nanofabrication strategies and tolerance. So to this end, here I'm presenting in this figure our numerical calculations for one of our device design, where you can see that the maxima and the electric field enhancements are well separated in the cavity. As a matter of fact, if you look at the right-hand side, the top panel, this separation is more than 120 nanometers. So, and this is another manifestation, if you like, evidence of the feasibility of our proposed tasks. To this end, distinguishable electric and magnetic field enhancements can be used as atomic scale probes for quantum sensing of electric and magnetic fields. So in conclusion, instead of a long epilogue, if you like, I'd like to say that ultimately this research proposal aims to revolutionize the development of scalable on-chip quantum sensing and also on-chip biological sensing, considering that the emission of erbium is in the near infrared region of the electromagnetic spectrum, which is well positioned for biological applications. And with that, I would like to thank you all for your attention. Thank you very much.
Thank you. Paper is now open for 5 minutes of questions.
Hi, this is Carl Williams. Let me ask a quick question. So can you expand a little on some of the defense applications that this technology would have and might have?
Yes, let me, first of all, I mean, this could be used as for magnetometry. So that would be one thing that can be used. And primarily, in all honesty, here the primary motivation of this proposal is to be able to develop, which I believe we don't have something like that currently, a technology which is going to enable the development of on-chip scalable platforms. So this can be used and minimize any kind of future device from dimension perspective. Now, in terms of an actual defense-related application, again, as long as we do care about any kind of measurement of the magnetic and electric fields, then this device could be, again, be applicable.
So this is Mitari. I'm just thinking about what your like post-implantation annealing process would be like, because it's really tough to do ion implantation, and very few fab labs can do this well to potentially remove damage. So how is the facility there able to handle that even at SUNY?
Yeah, this is a good question, and I think this is one of the I believe one of the key properties that we have demonstrated with this novel nanofabrication. Number one, there is a lot of complexity in terms of explaining, but just because of the ultra thin dimension of the nanowires, this allows for low passivation, if you like, and erbium activation temperatures, therefore diminishing any kind of erbium ion diffusivity. That's number one. And number two, just because we use certain sacrificial layers, let me put it that way, again, damage on the actual sample is minimized. And this was demonstrated through again, the benchmark value that I mentioned about the absorption cross-section, which is enhanced by 2 orders of magnitude with respect to regular typical values in erbium doped quantum materials. And by time resolved for the luminescence measurements, where we did not see any kind of change in the lifetimes between high and very low and cryogenic temperatures. If you look here in the in this figure, you can see, and maybe zooming in on this, you can see here that we put this sacrificial layer, and basically the ultra thin nanowire is works as a template for the on-demand placement of erbium ions. Then the rest of the material is actually removed, and you end up with this structure. So to answer again your question, it's a combination of a holistic nanofabrication approach which utilizes, sacrificial layers and minimizing damage. And because of the low temperatures that we use, we also can reduce significantly diffusivity of erbium ions, which may change the position of the implanted ion, and so on and so forth. And again, this is not a top-down traditional edge approach. The nanowires are defect-free just because they're self-aligned during the nanofabrication. So any kind of top-down dry edge is not present in this hybrid nanofabrication approach.
I'm assuming that's how you deal with erbium clustering with your separation there, and potentially.
Correct.
I see. And thermal quenching issues, perhaps? No.
Not really. No whatsoever. That's another, I would say, beauty of the proposed and demonstrated work. I mean, I have a link in our recent paper in Nanophotonics where we elaborate more on some of your very good questions. But no, we did not see any kind of temperature quenching or even concentration quenching by the bar implantation.
Thank you very much. We'll end it right there. So once again, thank you, Professor Gallus. Our next paper will be Gurudev from the University of Pittsburgh. Please unmute yourself for a mic check. And when you're ready to begin, click the Start Presentation button on your screen, and this will start your 10-minute presentation.
Hi, can you hear me?
Yes.
Okay.
Perfect.
All right. Let me just check. See if I can start the presentation here. Okay. All right. Hi, I'm Gurudev Dutt, and I'm at the University of Pittsburgh in the Department of Physics, and I want to thank the organizers and the judges for giving me this opportunity to talk about our work. The motivation for our work has already been sort of covered in this session, but I just wanted to mention that there are several reasons to improve magnetic sensing, specifically for defense applications in a GPS poor or GPS denied environment. By sensing, for example, anomalies in the crustal magnetic field that are caused by magnetized rocks in the crust and in the earth. This can be a useful technique for measuring position. And the magnitude of this field is much smaller than the Earth's magnetic field. So we need high precision and accuracy mapping using a robust and stable and portable sensor. Typical, for example, geophysical superconducting and NMR magnetometers seem to be somewhat bulky, and so we are always on the lookout for technologies and ideas that will make this possible. So the sensor that we are working with, which has also been covered in this session earlier, is the nitrogen vacancy center in Diamond. So I won't go over the details too much since we already heard about it, but this is an atomic scale defect in the diamond lattice, and the energy levels are such that with the spin 1 system in the ground state and through optical pumping and optical readout methods, we are able to measure the spin state of the NV center. It has a very wide range of operation conditions. And because of the long coherence times, even at room temperature, it has a high sensitivity. The vector response was mentioned in a couple of earlier talks as well. And it has high potential bandwidths that could be useful for some applications, and especially for sensing NMR type of signals. And then effectively, we are also in the broader sort of scheme of things, when you have a solid state system, in the end, we can move towards the swap, the good regions of the swap for defense applications. We can miniaturize, and we have a greater density that is possible to fit into a smaller volume. And also, I think something that's very interesting and is recently being explored is the stronger interactions between the quantum bits. So there are a few key problems still, some of which are unique to NV centers and some of which are sort of common for all quantum sensors. And so what I'll talk about is the first problem here, which I've highlighted, which is that the sensitivity and which is limited, and the scaling with the time and the number of spins. So what I mean by that is that quantum sensing with diamond, I'm just showing you the typical Ramsey scheme that is used for quantum sensing with diamond. And the basic principle of this DC magnetometry is that you prepare the spin, for example, along the North Pole, apply a pi/2 pulse to rotate it into the equator of the block vector of the block sphere, and then allow it to process under the action of a magnetic field, for example. And this magnetic field causes a phase to be accumulated on the spin, which is then measured by the final pi/2 pulse and the optical readout. And the result of this measurement, which is say a 0 or 1, will then allow us to estimate through a probability distribution the original phase phi that was accumulated. And because this is a quantum measurement, the standard quantum limit due to quantum projection noise of the spin measurements gives us a typical inverse square root scaling with time and n, the number of spins. So even, for example, if we increase the number of spins by a lot, which brings with it some other problems, but even assuming we solve those problems, there is still the limit of the 1 over square root of n. As an example, we show here the Ramsey fringes for a single spin measurement, and you can see that the scaling of the minimum detectable magnetic field is limited by the 1 over square root of t scaling, and so that's a common problem for many quantum sensors. I should also mention that much better sensitivities can be achieved than for DC magnetometry with AC magnetometry, where we can lock in to a certain signal which we are trying to detect, for example, an AC magnetic signal, and then by again using dynamical decoupling pulse sequences, this allows for AC magnetometry, and also with that increases the bandwidth, and also, of course, because of the dynamical decoupling sequence for the quantum bits, it increases their coherence time, and that also allows for better sensitivity. But one question we would like to explore is, can we do better than the standard quantum limit? And this is, of course, an interesting problem that has been studied in many different situations. Sorry. And particularly what we want to do in this research over the next year is to take advantage of two things that our group has done in the past. One is we have pioneered phase estimation algorithms for measuring the quantum phase, that is to measure the magnetic field. I'll talk about that in the next slide. But also we have worked with quantum memory. So For example, here I will go over this pretty quickly. There are references to our earlier work where we have shown that nuclear spins that are nearby to the NV center can be polarized and manipulated. This shows, for example, the nuclear free precession signal at room temperature. So that's of a single nuclear spin. So we have that kind of ability to measure even the precession from a single nuclear spin. And then we can carry out more operations between the quantum bits, that is between the NV center and the nuclear spins. We can carry out quantum logic operations. And these quantum logic operations allow us to achieve extremely high, for example, spectral resolution. Here we are detecting the free precession from two slightly different from two slightly separated nuclear spins that are different in their hyperfine interaction. And that allows us to measure, for example, the presence of the second nuclear spin. And so this nuclear memory or quantum memory what we're going to do is put it together with another thing that we have done, which is novel quantum algorithms. So first of all, the quantum memory, as I said, is a resource for the quantum sensing because it can greatly increase the sensitivity due to long coherence times of the sensor. And there are quantum logic circuits and pulse sequences that have already been established in the literature to do this. And then in addition, we have in our group carried out quantum algorithms, which are sort of like when you think about in quantum information, we have the quantum Fourier transform, for example, to do a better phase estimation. And that quantum Fourier transform can be adapted in the form of an adaptive and other kinds of algorithms that we can use with feedback or feed forward in different situations to carry out better estimation of the phase. And by doing this with one qubit, where basically we trade off time with the number of operations that we have to do, so we simply refresh the qubit each time and carry out the measurements again, we are able to demonstrate sub-short noise scaling with the time. And what we have shown in our simulations is that by using this and other kinds of feedback methods, we can further increase both the sensitivity and the dynamic range. And now we want to put this together with the quantum memory that I talked about. We want to implement these phase estimation algorithms now with the quantum memory to further enhance the sensitivity while maintaining a high dynamic range for the measurements. So to conclude, I want to conclude by saying that we think that implementing these quantum phase estimation algorithms with quantum memory is a promising path to increase the sensitivity and the dynamic range. We want to, of course, train graduate students and undergraduate students in these fundamental quantum science and technologies. And finally, we have some other ideas in future work for exploring these kinds of quantum logic and higher order quantum correlations for improving the performance of the quantum sensors. I'll stop there.
Thank you very much. Paper is now open for 5 minutes of questions.
Good morning, this is Yvette Weber. Could you explain what you believe the DoD applications are to your research?
Well, I think that the improving quantum sensors in general is important criterion. And I think already in earlier talks, people were mentioning that diamond quantum sensors are already being employed for these kinds of magnetic sensing and for improving the magnetometry and therefore for potentially for the GPS poor navigation situations.
Hi, this is Carl Williams. So let me ask a quick question. You know, you mentioned early on that you were trying to get improvement beyond the single quantum limit, and I understand how phase estimation algorithms work. I don't understand how this actually gets beyond the single quantum limit because there's no real entanglement or anything else that gives you one-over n scaling. So can you expand upon that just a little bit?
Sure. Well, I mean, kind of, I would ask the question back to you, which is we know the quantum Fourier transform normally is expected to have quantum entanglement, but in spite of that, by using it is well known that instead of performing like quantum logic operations, you can simply carry out measurements and feed forward to carry out the same kind of phase estimation algorithm. And so the idea here, I don't know, I'm not able to control the screen anymore, but the idea is that by taking advantage of the resources, we are able to like feed forward the system, and thereby like the resource in this case is the number of operations times the time of the operation, right? And so what we are doing is we are achieving better than the 1 over square root of n scaling of those resources by taking advantage of this feed forward mechanism. So we are essentially replacing entanglement by measurement and feed forward, as is done in a lot of measurement based, for example, quantum computation schemes.
I had a question. This is Lali.
Yes, hi.
Hi. As you mentioned, there's a lot of work going on in the NV frequency area. So where do you think that your work actually has an advantage? You mentioned the quantum algorithms. Are these something unique to your work that would give a special advantage to what you're trying to do, or is there something else?
I think that is our main advantage, that we have demonstrated these quantum algorithms already with 1 qubit, and now we want to implement it with 2 or higher number of qubits to show that we can indeed improve the scaling and the dynamic range. I should mention that our scheme are already shown, for example, typical Ramsey or other schemes are very limited in their dynamic range. You have to sit right on the correct point in the fringe to get and to beat down the short noise, for example. Whereas with our scheme, we have already demonstrated that our scheme has a very good sensitivity over a very wide dynamic range. So that would be another advantage of our schemes.
Thank you.
So, I mean, it's nice to see the theoretical aspect of this, but the experimental component is a whole lot challenging because you're assuming a perfect environment in the theory. But if you look at the many assemble, at least to get the kind of sensitivity we want for magnetometers, for sure, you need quote unquote an ensemble for the NVs to do this. But when you have this ensemble, you're going to have this spin to spin interaction that is going to cause a lot of noise, even though the algorithm is trying to clean that. But in reality, when it comes to the practicalities, it's still going to be a real challenge to address that. So do you have any, I guess maybe a simulation showing your field sensitivity to distance, if you want to put in a real device?
Great question. So, okay, so let me break it up into 2 sorts of separate issues. The first is the proposal that I am talking about is simply to understand the limits of quantum sensing in the first part, which is how do we use this new resource, which is the quantum memory, as a resource for the quantum sensing. And I think this has not been deeply explored. And I'm saying that by using quantum algorithms with the quantum memory, we hope to explore these limits of quantum sensing. The second part of your question is, what about the correlations that are caused? For example, if you increase the number of NVs or the number of nuclear spins. And I think this is a very interesting question. I think that, for example, I'll refer to, for example, work that has been done in Misha Lukin's group, where they take many, many NV spins and they drive them. And I mentioned this briefly in my outlook, which is that by driving and using this driven dissipative dynamics, and by exploring these higher order quantum correlations, it's possible to see very nonlinear and interesting patterns of behavior for the quantum system. And so
we'll have to end it there, Professor Dutt. We're about a minute over. So thank you very much. Appreciate your time today.
Thank you.
We'll move on to our next pitch, which is our final pitch in the sensing track. And this pitch will be given by Professor Paul Kwiat from the University of Illinois at Urbana-Champaign. Please unmute yourself for a mic check. And when you're ready to begin, click the Start Presentation button on your screen to begin your 10-minute presentation.
Great. Can you hear me?
Yes, we can, Paul.
Excellent. Okay, I've clicked it. There we go. Okay, so I'd like to thank everyone and say good morning. Thanks for the opportunity to pitch our proposal. This is actually a project that started several months ago, theoretically, with some of my students, Spencer Johnson, Colin Lualdi, and Christina Meyer. And our objective, our goal, is to be able to combine our expertise at creating high fidelity entangled photons with methods of quantum interferometry and also frequency entanglement in order to deliver a novel quantum enhanced optical delay measurement capability that improves on current state-of-the-art systems by nearly 2 orders of magnitude. This will allow attosecond level measurements that are robust to noise, loss, and dispersion. Okay, so of course, people have used classical interference techniques and interferometry for measurements for a long time. The basic idea is that we take an incident beam and we split it into 2 paths and we combine them on a beam splitter. And if we change the relative delay or the relative phase of those 2 paths, then we'll see fringes in the intensity at the output detectors. And from the slope of those fringes, we can get precise information about the relative path, phase, and time delays of those 2 paths. So this, of course, is used in many different applications, from optical coherence tomography, also laser ring gyroscopes, in long baseline interferometric astronomy, and most recently in gravity wave detection. So there's no question that this is a very useful measurement technique, but it does have some disadvantages. So in particular, this classical interference is susceptible to differential loss in the 2 paths, and also to background noise. And also, if one has a broadband source and there's dispersion, unbalanced dispersion in the 2 arms, all of those will reduce the visibility, the contrast of the fringes, and that will reduce then the measurement precision that you can get with this sort of a system. So in contrast, we could look at quantum interference, and the most common example of that in quantum optics is the Hongo-Mandel interferometer, where I take 2 photons and I mix them, I put them into 2 input ports of a beam splitter, and I ask, what do I see at the 2 detectors at the output? And what we see depends on whether or not those photons are indistinguishable or distinguishable. So if they're distinguishable, for example, if they arrive at the beam splitter at different times, then they act independently. There are 4 different outcomes and they all have the same probability. On the other hand, if the 2 photons are indistinguishable from each other and they arrive at, for example, they arrive at the same time, then they'll tend to bunch together. Effectively, there is a quantum interference effect that suppresses the possibility that 1 photon will go to each detector. So if I now think about scanning the relative delay of those 2 photons, when they arrive separately, I will get coincidences. When they arrive at the same time, those coincidences are suppressed. And that leads to this dip, so-called Hongo-Mandel dip. And it's the width of this dip that can give fairly high time resolution, and the width of that dip is determined by the inverse bandwidth of the photons. Okay, so there are a number of advantages to this sort of quantum interference. First of all, it does not depend on the phase, relative phase of the photons coming into the beam splitter. It's also resilient to background noise because we're doing a coincidence measurement, so that's able to exclude a lot of background. It turns out it's also robust to differential path loss because the interfering processes both experience the same differential path loss, so it doesn't affect the visibility. And finally, it is immune to group velocity dispersion, or more precisely to odd orders of group velocity dispersion. And I'd like to point out that actually you have been funding this research for a very long time, because in fact, when I was a graduate student, I was funded by the ONR on a project that first demonstrated this dispersion cancellation effect. Okay, so the Hongo-Mandel interference has a number of advantages, as I've shown. It does have some disadvantages, though, because to achieve the very high resolution, a very narrow Hongo-Mandel dip, you need extremely large bandwidth photons. And also, because we're only getting the information from the overall shape of the dip, we get relatively limited information per photon. So what we'd like to ask then is, can we come up with a hybrid system that can combine the best features of these classical and quantum interference to get something that's better? And the answer, of course, is yes. And so the idea, this was realized a couple of years ago, is that if we do a Hongo-Mandel interference with frequency entangled photons, then something interesting happens. So by frequency entangled, I mean that I have 2 photons, each of which could be one of 2 colors, but we don't know which is which. And if I then take those 2 photons and combine them on a beam splitter, we can then calculate what we'll see. And we'll get the same sort of envelope that gave the Hongo-Mandel dip, this exponential factor here, and that's determined just by the bandwidth of the individual spectral components, but then that's modulated by fringes at the beat frequency, the difference frequency of these two frequencies that I have. Okay, so we could do a comparison of this against classical interference and show some of these improvements. So this is showing what happens if I change the transmission in one arm of an interferometer, and we see that the classical interference fringes wash out, whereas the quantum ones are maintained. Okay, this is showing if I put a background, classical background on, and in the classical case, the at large offset again washes out the fringe visibility, whereas the Hongo-Mandel, the quantum interference on the right, is basically immune to that. And then finally at the bottom, I show what happens if we just put a piece of glass in one arm of an interferometer. And again, the classical interference is washed out, whereas the quantum interference on the right is immune to this group velocity dispersion. Okay, so that was all theory. This, in fact, has been demonstrated a couple of years ago by Philip Walter's group in Vienna. And they were able to achieve a timing measurement resolution of about 640 attoseconds, corresponding to a path delay of about 190 nanometers by detecting 10,000 pairs of photons. And what limited them in their experiment was the maximum detuning they could get. The maximum separation in wavelength was about 37 nanometers, corresponding to about 17 terahertz. Okay, so what we can bring to this is some recent experiments that we've been doing for completely other purposes, where we generate entangled photons, polarization entangled photons that are very non-degenerate. So one of the photons is at 810 nanometers and the other one is at 1550 nanometers. And this corresponds to a frequency difference of greater than 1,000 terahertz. So this is just a measurement from our laboratory showing that, in fact, we can produce these highly entangled photons with better than 98% fidelity. And then if we take those photons and we send them through a polarizing beam splitter and a half-wave plate, it turns out that that converts the polarization entanglement into frequency entanglement. So we now have a very large detuning, more than 65 times what the previous experiment was able to achieve. And then we can combine those photons onto a beam splitter and look for these Hongo-Mandel fringes. We can change the path length either just by explicitly changing the path length in one arm, for example, pulling out this prism, or what we would prefer is to use this nano-fabricated substrate, which has regions of different thickness and also different opacity so that we can explicitly explore the resistance to loss. Okay, so there are some challenges to make this work. So first of all, of course, we need high quality energy entanglement. And as I've said, we can get that from our high quality polarization entangled source. We need a system that can simultaneously support both of these wavelengths. And so we'll be doing this using free space optics initially to facilitate that. Since we're going to claim that we have an extremely precise measurement capability, we want to be able to verify that. So we'd like to do that using a nano-fabricated substrate that we can verify using other measurement techniques. And if someone wants to ask about this last contribution, I'll talk about that in the questions. Okay, so we've done theoretical modeling showing what we can expect as we change the relative detuning of the photons. And by going to photons that are much more detuned than the previous experiment, we see that we get very high frequency fringes. And from those, we can then estimate that we should be able to get a time resolution below 10 attoseconds, again, with about 10,000 photon pairs detected. And given that we have a source that can produce more than 100 million pairs per second, that means we should be able to get that sort of resolution in less than a millisecond. And again, this represents a nearly 2 order of magnitude improvement over the previous capability. Okay, so why should we care about that? Well, I've already indicated that there's a number of benefits in terms of dispersion resistance and robustness against loss, but I think maybe from the perspective of the military, the most interesting of these might be the resilience to noise. So in particular, you could imagine doing a stealth measurement where we have our entangled photons in the presence of a large background of photons, so it's basically impossible for someone else to detect that. I'll also say that from an information perspective, the system saturates the so-called Kramer-Rao bound, so these are optimal measurements. You get the most amount of information you could per photon. And so we could think about a number of different applications from differential ranging to precision tomography, also optical coherence tomography. as another application that could be of interest for medical diagnostics. And I've indicated some other questions at the bottom, but I think at this point I'll stop and ask you for questions that you may have specific to this. Thank you very much for your attention.
Thank you. Paper is now open for 5 minutes of questions.
I had a question. This is Lali. Am I unmuted?
You're unmuted. You're a little quiet though.
Oh, really? Okay, maybe I need to work on, never mind. If you can hear me, I'll speak a little louder. So
yeah, I'm good. I'm good. Yep.
Okay. One question I had was, you are part of the new Quantum Leap Challenge funded by NSF, and there's a lot going on in the US in this. And so do you see this work that you're proposing here connecting or being synergistic with other work that's being funded by other agencies? Or how do you plan to share information, and do you plan to help other areas?
Yeah, that's a great question. So yes, we're also part of the new DOE Center, QNext, and some other things. So I'll say that this work in particular is not funded by anyone at the moment, although the source, for example, the non-degenerate polarization entangled source was part of a NASA project that we have, eventually trying to do quantum communication from space. And so that's where that connection is. I certainly think that these kind of modalities could be of interest to a number of different agencies. But as I say, this is not actually currently funded by anyone at all.
Thank you.
So Paul, this is Carl. So can you talk about the fundamental limit of using this type of entanglement? I mean, again, it seems like that there has to be, again, you say it doesn't violate the Rao bounds or the Kramer-Rao bounds, but what is the real limitation of doing this and spreading the frequencies out even farther?
Right, so that's a good question. Some of it is going to be dominated by how broad of a bandwidth you can get phase matching on your down conversion. Of course, you're never going to get so the way those down conversion photons are created is we take one pump photon and we split it into two. So the maximum frequency difference you could ever get between those two photons will be basically the energy of the pump photons that you deal with. So you could imagine doing this with higher energy pump photons, and then you could imagine one photon being in the radio and the other one in the optical. No one has done any experiments of those sorts as far as I know, and one would have to think about how you would actually do the measurement to do single photon detection of those microwave or radio wave photons. But in principle, you'll be limited by the bandwidth of the pump, I guess. Not the bandwidth, but the frequency of the pump that you can use, and whatever down conversion crystals you can come up with.
So this is Matari. You talked about improving the Homey resolution. What exactly is gained by that improvement? I'm not sure that's clear.
Yeah, well, so initially in a Hongo mandala, you don't have any kind of fringes at all. So you're limited only by the width of those, the width of that peak. And that width might be, say, 100 femtoseconds. Sorry, that width might be quite a long distance. So we're getting a gain of many orders of magnitude, a couple orders of magnitude in the resolution. So let's say you wanted to look at some faraway device that was vibrating, but it's only vibrating on the order of a couple of nanometers. So if you do a Hongo mandala measurement, a normal one, you never will detect that. It absolutely will be buried in the width of this dip. Whereas here you'd be able to detect that, and you'd be able to detect it in a stealthy way because you're not using a bright signal that's bouncing off of something.
This is Matt Squires. I am wondering how difficult is it to use this laser? Is it one of a kind in the world, or is it fairly straightforward?
Yeah, the laser that we're using at the moment is a frequency doubled YAG laser, basically. So it's not anything particularly amazing. And then the down conversion crystal is just a periodically pulled wave, and not waveguide, but periodically pulled bulk crystal at the moment. But there's lots of ways to get the polarization entanglement, and we've worked with waveguide sources and also some other modalities for that. So I wouldn't say that any of this is particular state of the art in terms of the components that go into it. As far as I know, no one has this quality of non-degenerate polarization entanglement that we have. but the materials themselves are not particularly fancy.
Okay, with that, we will draw this paper to a close. Thank you, Professor Kwiat, again, for a great talk.
Thank you.
This draws to an end, actually, our whole sensing session. So now going to move into a break, and the break will last. We're making a slight adjustment here. The break is going to last until 10:40. This will allow our folks to be able to visit the virtual posters or to go to the coffees and concepts. So 10:40. If you are interested in those events, please go to the main event page and you can click on the links. We had some great feedback yesterday from Coffee and Concepts. So let me just tell you a little bit more about that and remind folks what that is. So one of the best parts about attending these events is meeting new people and making connections. So this is a chance to do this virtually. Coffees and Concepts is a worldwide gathering where you'll mix with other attendees from around the globe into smaller breakout rooms to meet and chat about all things quantum. So I encourage you to take advantage of that or go look at more of the posters. We'll see everyone back here at 10:40 for the start of communications. Thank you.
Our program will resume in 2 minutes.
Welcome back. I hope everyone had a chance to either go look at the iPosters or go to the coffees and concepts. And it's a great new way of doing things in terms of the coffee and concepts. So hopefully some new connections were made through that. Now let's transition to our last set of pitches, which will be in the communications area. If you did not join us for the earlier pitches, let me just quickly review how things work. All pitches will be 10 minutes long, followed by 5 minutes of questions and answers from the judges. We will be showing your virtual iPoster to support each pitch. If you are unable to navigate your own poster, we will move through the poster for you. When you're ready, you will hit the start button on the screen, which will start the 10-minute timer for the duration of your talk. The timer will turn yellow for a 2-minute warning, and at 30 seconds, it will turn red. There will be a prompt that pops up in the middle of the screen at the end of the 10 minutes, and that's when the judges will be able to start their 5 minutes of question and answer. After every so often, we'll be taking a 10-minute break. Let me now turn and introduce our panel of judges for the communication session. Dr. Grace Metcalf, Air Force Office of Scientific Research. Dr. Frederick Fatimi, United States Army Research Laboratory. Colonel Tim Lawrence, Air Force Research Laboratory, Information Directorate. Dr. Joel Moser, Chief Scientist, United States Space Force. Dr. Bindu Nair, Office of the Secretary of Defense. And with that, let's roll into our first pitch, which will be given by John Bartholomew from the University of Sydney. Please unmute yourself for a mic check. And then when you're ready to begin, click the Start Presentation button on your screen to start the presentation.
Hello, is my audio coming through okay?
You're a little quiet, so just speak a little louder. but we
Okay,
can't
will
hear
do.
you.
Okay, great. Well, thanks very much, and thanks to the organisers for giving us the opportunity to pitch our project at this great initiative. The objective of our project is to engineer and optimise a missing link to enable us to build quantum networks and the quantum internet. And so what this missing link is, or this component, is an adapter which allows us to connect between the optical regime and the microwave regime at the quantum level. And so in doing so, what we want to be able to do is to connect quantum computers based on superconducting circuit technology held at cryogenic temperatures with optical fiber networks that allow distribution of quantum entanglement at room temperature. And so the immediate consequence of this type of device is that it allows superconducting qubits to form entangled connections beyond the confines of extreme low temperatures of dilution refrigerators. But our team are interested in these types of quantum interconnects to go beyond this, but to form a quantum optical hub that allows diverse quantum technologies to connect with each other through this optical network. And so such a quantum internet will leverage those diverse quantum technologies and apply them for the tasks at which they're best suited. It will also allow quantum networks to grow beyond simple point-to-point connections to much more sophisticated networks. But to do this requires a suite of devices. We need to be able to generate that entanglement. We need to be able to store quantum states and in memories and synchronize different parts of that network. We also need to be able to process information and correct for errors that are unavoidable in non-ideal networks. Finally, we also need to be able to convert quantum information between those very different operating regimes. And so towards this goal, our project seeks to realize a hybrid entangled photon pair source. And so this single component aims to combine three capabilities of those other technologies into one device. Our entangled photon pair source will generate two photons, one in the optical regime to connect with fiber optic networks, and the other in the microwave regime to connect with superconducting qubit technology. This project continues a 4-year collaboration between myself and Professor Andre Ferrone at the California Institute of Technology. For this project, my team at the University of Sydney in the newly established Quantum Integration Lab will lead the protocol development and optimization. And Andre's team at Caltech will lead the device demonstration, leveraging the hardware platforms that we've developed for microwave to optical conversion. And I've shown an example of one of these devices here, which is an on-chip nanophotonic platform that allows us to couple rare earth atoms in crystals to both optical and microwave modes. The main impact of this research direction is to be able to merge two very powerful quantum technology platforms, those being superconducting circuit platforms for quantum computing and photonic quantum networks for distributing quantum entanglement. And so the advantage for quantum computing is that these photonic quantum technologies allow the quantum computers to be able to modularize their systems, to create bigger quantum computers based on linking through optical fiber technology, individual processors, and thereby freeing superconducting circuit technologies from the confines of a single dilution refrigerator. In terms of the networking side of things, quantum optical networks can now plug into one of the most powerful quantum computing platforms that we have today to enhance error correction and entanglement distribution to scale up those quantum information networks and also secure communication networks. The way that we're looking to approach this problem is to center our project on ensembles of rare earth atoms in crystals. And so in the next few minutes, I'll take you through some of the aspects of those rare earth materials, some of the devices that have been realized to date, and how that provides a foundation for our innovation, which we're pitching today. So the rare earth atoms reside in the lanthanide series of the periodic table, and they're distinguished from other atoms by a unique electronic structure. And so when we utilize these materials for quantum information technology, we utilize the 4F electrons. And these electrons reside close to the nucleus and are shielded from external perturbations by filled outer 5s and 5p electrons. And so this inherently provides a degree of environmental protection. The consequence is if you take crystals containing the elements erbium or ytterbium, and you cool these crystals down to cryogenic temperatures, then they become some of the most stable quantum systems in the solid state. In addition to their stability, these quantum systems also have a number of degrees of freedom, which allow a great basis for multi-system compatibility. We can interface with photonic quantum technologies through the optical interface, and for erbium, this operates at a wavelength in the telecommunications C-band. We can integrate with microwave technologies by connecting technologies through the electron spin degree of freedom. And we also have access to the nuclear spin degree of freedom, which we can use for long-term quantum memories. And so using this platform, a number of important technologies have been developed for quantum networking. In the last 2 years, our team has been working on microwave to optical transduction using these rare earth ion platforms. And this is where we're directly transducing or converting between the microwave and optical regime. And one way of doing this is by inputting a microwave photon connected to the electron spin degree of freedom and mapping that to an optical photon by connecting these two transitions with a strong optical pump. And you can see here in the lower right, one of the on-chip devices that we've created, which harnesses low-loss silicon photonics and superconducting microwave resonators, all fabricated on a single rare earth ion platform. The advantage of our hybrid entangled photon source compared to the transducer technology is that no matter how you try and realize a transducer, whether that's through rare earths or electro-optomechanical or electro-optic techniques, you need to provide a strong optical pump to bridge the energy gap between the microwave and the optical regime. And that strong optical pump is incompatible with superconducting, high-performance superconducting circuits. In our hybrid source, what we are able to do to disconnect the microwave circuit, the superconducting circuit, from the optical components in time. And so by separating those two components, we are able to have greater freedom in designing the devices for high efficiency and low noise. And so we're going to utilize that experience in pairing up the microwave and optical regimes, but also generate that entanglement. And we can do that by using ensembles of rare earth atoms and rephasing an initial spontaneous emission event. So if I have an ensemble of atoms, which are all in their excited state, and one of those atoms decays, releasing a photon, then it's not possible to tell which ion released the photon. And so this photon becomes entangled with the ensemble, and the ensemble is in a macroscopic entangled state, this Dicker state, which is all the combinations of the ions being in the excited state except for one. And so just like in spin technology or in photon echo technology, we can rephase that initial coherence by inverting the ensemble. So applying a pulse to this two-level system, we can rephase the ensemble, which then generates a second photon entangled with the first. And this has been demonstrated in the all-optical regime, but we're going to take it to this highly non-degenerate regime by inverting on an electron spin transition to generate our initial microwave photon, then mapping that coherence down to a long-lived nuclear spin transition to store it as a quantum memory. And then when we want to recall the optical photon, we can excite this optical transition to then release that second photon. And although I've only drawn one photon in both cases, because we're using ensembles, this is inherently a multi-mode process. So we can generate multiple photon pairs in the time domain. The challenges in doing this are mainly to create high efficiency sources, to reduce the noise, and to make them compatible with the technologies that we're trying to partner with. But our experience in making high Q optical and microwave resonators gives us a great basis for extracting those photons efficiently. And our ability to control ion atom-atom interactions and atom-phonon interactions in these materials allow us to reduce the possible population of noise modes. And so in this project, we're going to demonstrate the basis of this technology, but then use it as a stepping stone to a broader quantum optical networks for connected quantum technologies. Thank you.
Thank you very much. The paper is now open for 5 minutes of questions from our judges.
Hey, John, great briefing. I understand this is fundamental research, but I'm curious about what the challenges for large-scale production of these hybrid sources might be. You talked about efficiency, but are there other technical challenges to making this a reality?
Yeah, that's a great question. So one of the major challenges for rare earth ion technology at the moment is to spatially control where those atoms are in the crystal. So most of our work to date has been using crystals that incorporate rare earth ions during the growth, and therefore they're stochastically spread throughout the lattice. So one challenge in scaling up these technologies, whether that be quantum memory or the hybrid sources that we're proposing here, is to be able to define where those ensembles are in space, because this allows us to get better coupling to resonators, but also eliminate some of those noise channels that I talked about.
Can you hear me? This is Frederick Fatimi.
Yes, I can hear.
Okay, good. Yeah, I'm curious about the efficiency of this process and how deterministic the integral pair generation would be.
Yeah, great question. So the efficiency is limited by the ensemble collective coupling. And so the more ions that you have, the better chance that you have of rephasing that initially generated photon event. So the challenge in realizing this at high efficiency is getting into a regime where that initial inversion event doesn't cause lasing or mazing on that microwave transition, but it gives you enough collective coupling to efficiently rephase that technology. And so in the optical domain, people have achieved efficiencies of a few percent. But in moving to this hybrid technology, there are some advantages and some disadvantages in doing that. So that's one of the key aspects that we're really looking to nail down in this technology. But our resonators should be good enough, we think, to push up to high efficiencies.
Okay, thanks.
Hey, John, Tim Lawrence here. Just had a quick question on what's Caltech's role? I read through the proposal, but it wasn't quite clear about how you're, collaborating with them and what they can do to help you in your research.
Yeah, so the Andre's team at Caltech are experts in fabricating these devices. And so in a previous role, I was in Andre's team, and so we collaborated together quite closely. And so my role in the process is really to help design the protocol and make the theoretical proposals and optimize the device. And Andre's team are the experts in actually fabricating the devices and can make progress straight away using some of the existing technology that we've developed for transducers.
John, this is Grace. Thank you for your nice talk. You mentioned something about how you disconnect the superconducting circuit components with the optical components. Could you expand on that and also discuss how you would incorporate superconducting qubits onto this rare earth system? Thank you.
Yeah, so the first part of your question, the way that we can disconnect these two parts of the device is in the time domain. And so in the transducer, you have to run both the microwave and the optical part of your circuit together. In this source, what we can do is to generate, for example, that initial microwave photon and then store the information for a period of time, allowing us to move then onto the optical part of the circuit. And so the superconducting circuit is never having to operate closely after a strong optical excitation to the system. In terms of moving forward and incorporating qubit technologies in this platform, that's one open question and one that we're really interested to explore. We know that the loss tangent of the materials that we use is very low. So there is some possibility of actually incorporating superconducting qubits directly onto these materials, but that would require significant advances in being able to control where our active ions live in space, because they'd be a huge loss mechanism. Alternatively, there's other thin film and thin film technologies that could be employed to try and do all of this on a silicon platform. But again, they're longer term visions.
And with that, we will need to end there as we are out of time. Thank you, Professor Bartholomew.
Thank you.
Our next talk will be given by Alex Hyatt from Technion, Israel Institute of Technology. Please unmute yourself for a mic check. When you're ready to begin, you will start the Start Presentation button on your screen to begin your 10-minute presentation.
Hello, can you hear me?
Yes, loud and clear. Thank you.
Okay, so I'm Alex Hyatt from the Technion in Israel. I'd like to thank you, the organizers and the judges, for this opportunity to take part in this excellent and exciting event. I want to present our work on high temperature superconducting photon detectors. So photon detectors are key technology in quantum information processing, and especially in quantum communications. And the three main factors limiting the performance of the detectors are the dark count rate, or the number of false detection per second. The second factor is the time and resolution, determined mainly by the jitter of the effect of the detector that limits the quantum channel speed. And the third is the detection bandwidth, or the range of wavelengths where the detector has high efficiency. And these factors depend on the kind of channel used. For example, in free space quantum communication, like this one between two islands, short wavelength photon can be used, detectable by silicon avalanche photodiodes, or APDs, that has high quantum efficiency and low dark count rate, less than 100 per second. However, the jitter of these detectors on a nanosecond scale still limits the operating rate to less than gigahertz. And in more practical fiber-based quantum communication channels now being deployed around the world, these problems become even more severe, because for fiber communication, longer wavelength telecom range photons must be used close to 1.5 microns. And for these InGaAs-based APDs are used typically with much higher dark count rates, more than 100,000 per second, which requires operating them in gated mode. And together with the effect of afterpulsing, this limits the speed of the fiber-based quantum channels to around a megaqubit per second. And this is tens or maybe hundreds of thousands of times slower than classical fiber communication. And bridging this gap between quantum and classical fiber-based channels will make quantum communication over fibers truly practical. And many of these difficulties have been addressed by employing the newly developed technology of superconductor nanowire-based detectors, which use superconducting wire that is biased slightly below critical current density. And when a photon is absorbed in a nanowire, it creates a local non-superconducting spot by heating the nanowire. And this creates a local resistive region for a moment that shows up as a pulse, as a voltage pulse on the output. And because these detectors are based on heating, they have very broad detection bandwidth, because no specific energy level transitions are required, and photons can be detected well into the mid-infrared. They have extremely low dark counts, less than 10⁻³ per second, and excellent time and resolution approaching the picosecond range. And the main problem, or the major problem of employing these detectors in practical quantum communication is the need for extremely low temperatures for the existing systems using low temperature conventional superconductors. And these temperatures below 10 Kelvin can be obtained only with expensive and bulky cryogenic systems, which essentially limit the use of these detectors to scientific research labs. So in our approach, we're aiming to push this technology of nanowire-based detectors to temperatures an order of magnitude higher than the existing ones by employing the recently discovered family of high TC materials. And because these materials require much less cooling, cheaper, more compact and portable devices can be used to cool these systems. For example, like this 6-volt battery-based 80 Kelvin cooler by Recor, a company here in Israel, an hour drive from here, so that we can have pocket-sized superconducting nanowire-based photon detector. So this is a very promising direction of research, and the reason it hasn't been developed so far is probably because these materials have a very complex phase diagram, and they need a specific level of doping, and chemical etching or other processing can compromise this doping level, therefore making these devices lose their superconducting abilities. So we avoid this problem by, instead of chemical etching, using our selective epitaxial growth system approach, where we deposit the superconductor as the last step in the process so that no chemical etching is needed. And we start from a STO substrate on which the superconductor can grow. We cover it with a layer of silicon nitride on which the superconductor doesn't grow. Then we etch narrow trenches exposing the original substrate. And when we deposit the superconductor, it grows only inside the trenches surrounded by insulating layers. And then we have nanowire forming without any need of chemical etching and not risking losing the superconductivity. And by this approach, we grew nanowires with transition temperature as high as 90 Kelvin with a reasonably high critical current density. And these nanowires allowed us to demonstrate the first photodetectors based on high TC nanowires operating actually at temperatures close to the critical temperature of high TC materials above 80 Kelvin. And as we go closer to the critical current density, we see that the photo response increases at a temperature an order of magnitude higher than typical temperatures of previously used devices. And when we study this systematically, we see that indeed, as the current density and the temperature approach the critical values, the response is strongly enhanced. And we see that we get the optimal response at the temperature of close to 87.5 Kelvin, which is well above the 80 Kelvin temperature provided by this pocket-sized cooler by Recor. And in our research plan, we have two main directions. The first one is making these devices faster by designing and implementing proper RF readout circuitry. And the second part is making them more efficient by reducing the width and the thickness of the wires towards single photon detection. And our team for this project is based on two research groups. First is my group at the electrical engineering department that specializes in the design and characterization of these devices by electrical transport measurements and optical measurements with all the necessary equipment. And the second group is the group of Amit Kanigel in the physics department, who are experts in the materials themselves, the high TC materials, including characterization with ARPAs and other sophisticated tools, and in various growth methods such as pulse laser deposition used in this project, and the rest of the fabrication like nanoscale patterning we do at the Technion nanofabrication facilities. So to summarize, I think that this approach of taking superconducting nanowire detector technology from 8 Kelvin to 80 Kelvin will make them truly practical and available in everyday devices and widespread in both industry and the government use. And this will enable to take fiber-based quantum communication channels to the speeds of classical fiber communication. Thank you for your attention.
Thank you very much. Paper is now open for questions.
Sorry, this is Frederick Katimi. I've had difficulty with the video, so you may have shown this already, but what is the temporal response that you would expect and the jitter that you expect?
So what I expect is close to what we have in low TC materials, which is roughly single picoseconds to tens of picoseconds. That would be the optimal operation. And we're working on getting there. We're still not there because there are some electrical engineering issues like high impedance of the high TC materials that needs to be matched to the transmission lines and so on. But this is something that can be done in principle.
And are there any potential opportunities for photon number resolving that working at higher temperature for some reason permits?
The photon number resolving can be done, for example, by having several of these detectors in series. That's something that has been done with low TC materials.
Okay. Thanks.
Yeah, Alex, great talk. I wonder if you could talk a little bit more about the challenges you'll face in scaling down to single photon detector sizes. Is there particular technical challenges to do that? And then if you do achieve that, what the challenges might be to scaling up the fabrication of practical devices at those thin, narrow nanowires?
Right. The difficulty is, like you're saying, is indeed the fabrication, because it's these materials are not metallic, and both growth and patterning are completely different. And getting to single photon detection efficiency, it depends on how narrow and thin we can make our nanowires. And we should be somewhere around a few nanometers thick and a few tens of nanometers wide. We still have an order of magnitude to go on those. Right. Oh, and you say the future applications, when we get the single photon, I see a whole spectrum of applications, for example, making infrared cameras with an array of these detectors that can act as pixels. So there are an endless spectrum of applications.
Yeah, Tim Lawrence, just have a quick question. I mean, great work. I love your team. Just curious, who are potential other sponsors of this research other than the team here that you're pitching to? Because I know Technion is a great university in Israel, and you're pretty well connected. And I was skimming through here that I know you've done some work with Germany. So just interesting in other collaborators that you've been working with.
Collaborators. So we on superconductors, we work with various teams in the US, but that would be in low TC end of the superconductors. You asked about sponsors. So this research was sponsored by, it would be kind of the Israeli version of DARPA for 2 years. And it got us so far, which is great, but still needs some work. Germany, we work again on low TC materials. There are some groups that might be in Europe, in Asia, Singapore, China. So it depends on where this project takes us.
We have time for one more short question, if anyone has any more questions. If not, let's end it there. Thank you very much, Professor Hyatt, for joining us today.
Thank you.
Next up is Ilan Palm from the Weizmann Institute of Science. Please unmute yourself for a mic check. When you're ready to begin, click the Start Presentation button on your screen to begin your 10-minute presentation.
All right. Okay. Can you hear me?
Yes, we can.
And
Please just speak up a little bit.
all right. I cannot start my video, but okay, fair enough. So, right. Okay, so I'll start. How can I start? Start my video.
We will control your mouse for you. Just let us know when and where you want to click.
All right, so could you start my video, please? Or you cannot start my video, I don't know. Yeah, okay. It doesn't start anyway. No. Right, okay, so thank you very much. Please return to the main board. Okay, thank you. Right, so my name is Ilan Palm. I'm happy to present to you this new project titled Transition Metal Ions in Crystals as Quantum Spin Photon Interfaces for Optical Quantum Communications. I'm proposing this project together with Ofer Furstenberg, both of us from the Weizmann Institute of Science in Israel. So could you please click the author information? The author information on the bottom. No, the author information on the bottom, please. Right, that one. Okay, thank you very much. So Ofer Furstenberg and myself have many years of experience in quantum optics with material systems ranging from hot and ultra cold atomic gases to the solid state. Notable expertise of Professor Furstenberg include nonlinear quantum optics with Rydberg atoms towards the realization of deterministic photonic quantum gates, quantum memories with extremely long lifetimes, studies of phase transitions and critical behavior in spin systems, and atomic sensors such as this atom interferometer on the right. Could you please scroll down? Okay, furthermore, yeah. Myself, I have much relevant experience with developing broadband noise-free quantum memories, studying quantum thermodynamics with envy centers, exploring the propagation of entangled photons in complex systems, and investigating quantum systems based on quantum dot excitons. Okay, return to the main panel and click on the motivation panel, the top right panel. Thank you. So our objective in this project is to create a solid state node of a quantum network that works at high temperatures. Quantum network is composed of 3 ingredients: anchored qubits on the nodes, flying qubits on the vertices, and coherent coupling between them. For the anchored qubits, solid state defect spins like the famous envy center have been shown to stay coherent even at room temperature. For flying qubits, telecom photons are the best, as they can travel for tens of miles in optical fibers without considerable loss. However, in order to have coherent coupling between telecom photons and spins, we need a component that we denote as the polarized lambda system. Could you scroll down and click on the figure, please? Yes. In such a system, there is an additional excited state connected optically to the two ground spin states, preferably in the telecom band. And these optical transitions couple to two orthogonal polarizations. Therefore, both the amplitude and the phase of each leg are controlled by the polarization of the signal light. This directly links the polarization information carried by the photons to the state of the spins. With a polarized lambda system at hand, we will be able to harness the entire quantum optics toolbox that is now extremely developed after decades of studies in atomic vapors for quantum communication and information processing with solid state emitters. These applications include, for example, selective optical pumping employing polarized light, complete optical spin control using single short pulses, noise-free storage and retrieval of broadband quantum light, and most importantly, spin photon polarization entanglement. Please close the figure. Unfortunately, to date, such coherent coupling between solid state spins and photons has only been achieved at liquid helium temperatures. Okay, go to the main figure and open the next panel, please. The main challenge. Yes. The reason for that is that the physical mechanism behind spin-photon coupling is the spin-orbit interaction, which is predominantly weak in those systems. The limit on the operation temperature is set when the decoherence rate of the optical line exceeds the rate of the spin-orbit coupling. Please click on the figure. No, the one, yes, right, that's that one. Yeah. Please scroll down. No? Oh, it's a different figure. Right, okay. So I missed one figure. Sorry about that. I probably replaced the wrong figure at some point. But the point here was to explain that when you have is to explain how can you have a polarized lambda system connecting spins to light. And the point is that light itself cannot change the spin. It can only change the orbital part of the electron. It cannot change the spin. That's the main point. And in order to connect or couple light to spin, you need the spin-orbit coupling. This interaction mixes the states and separates them by twice the interaction rate, and could thus create two polarized lambda systems. However, we want to work only with one of those. And in order to do that, its optical transition has to be energetically isolated from that of the other lambda system. This means that the separation between them, which is the spin-orbit interaction rate, should be larger than the width, which is the optical decoherence rate. That's the reason we basically want to have strong spin orbit for this. Okay, so please close this. In existing systems, like in Diamond Envy Center, the spin orbit coupling is on the order of a few gigahertz, and therefore, to get coherent spin photon interface, one has to work at liquid helium temperatures, where the optical decoherence is sub-gigahertz. Okay, so please open the proposed solution panel. Our solution to this problem is to use solid state defects containing transition metal ions. These defects were much less studied in the context of quantum optics than other systems. And in fact, as you will see, this is somewhat an uncharted territory. As the confined electrons would now be d electrons, the spin orbit coupling can be orders of magnitude larger than in systems containing p electrons, such as the NV center. As we want to maintain the stable ground state spin, we choose systems with either 2 electrons or 2 holes in the outer shell, that is D2 or D8 configurations. The ground state manifold of such systems will be a spin triplet sharing the same orbital. And that, like in the NV center, that ensures the stability of the ground state spin. It turns out that there are quite a few of these systems, and many of those also have optical transitions near or at the telecom band. We give here 3 examples for these systems, of which we already have samples. These are nickel in diamond and in magnesia, and niobium in gallium arsenide. In these systems, the energy difference between the lowest transition and the next one is on the order of a few terahertz and even more. Right, so please go to the figure. How much time do I have? Oh, I see, sorry.
Well, due to the technical difficulties, please feel free to take 2 to 3 extra minutes.
Okay, thank you very much. Okay, so please go back to the main panel and click on the figure to the lower right. Yes, okay. So in the figure, we see some measured spectra from the literature. We can see that for the nickel centers on the left and center, the different lines are resolved even at 77 Kelvin. For niobium and gallium arsenide, the line is completely isolated. There is only one line, basically, and it splits in magnetic field into 3 lines due to the splitting of the 3 ground states. The existence of these 3 lines shows that the excited state is linked to all 3 ground states. This is exactly what we want. Okay, go back. Okay, go to the integrated devices panel. Before concluding with the research plan, let me mention that we have in our lab the infrastructure for femtosecond laser writing of optical waveguides in the bulk. We plan to apply it in this project for fabricating small devices, embedding the transition metal defect centers in structured waveguides, and by this to further increase the light spin interaction. These waveguides could be naturally coupled to optical fibers for the creation of an all-fiber device. Go to the research plan panel, please. Yes. Our research plan for the year is as follows. First, we shall produce and characterize samples containing these defects. For the production, we either buy crystals already containing the defects or ion implant them in pristine crystals. Optical characterization is to be done with standard fluorescence spectroscopy and microscopy methods. Here, there's an example of a spectrum recently took of magnesia sample containing nickel. One can see the sharp 0 phonon line at 1250 nanometers, limited here by the spectrometer resolution. Of course, further characterization is required to measure the actual width and the optical decoherence time. Next, we will measure the spin decoherence time using optically detected magnetic resonance. Once we will have characterized the coherence times of the system, we will use short pulses on ensembles of these defects and demonstrate all optical spin control and light storage, such as in this example, if you scroll down, from our recent work using rubidium vapor.
And we will need to end it right there and open up for questions. Thank you.
Sorry about that. Okay, thank you.
If I may, thank you for the talk and thank you for the approach. If I understand what you're trying to do, you're coupling efficiently. You're trying to couple to practical telecom wavelengths, which is great.
Yes.
And you are doing it via specific choice of transition metal alloys, which have properties you want, high stability and state transitions in the IR regime. Can you help us understand what other methods are out there for people are looking at for efficient coupling to practical telecom wavelengths, and help us help me a little bit more understand where the sort of unique spot that you're finding is, and that perhaps can't be used by other techniques that are out there that are being tried.
Okay, so most other techniques basically couple the spins to visible wavelengths, because these are the systems that exist, and then apply some kind of nonlinear crystal to convert the wavelength from the visible to the telecom. The issue with that is that it has limited efficiency, and it also requires another bulky apparatus that complicates the system. And here we just want to completely avoid the need for this conversion.
Hi, thank you again for your very interesting proposal. My question for you is, how do you determine which transition metal and which host material you look at? Do you have something that's guiding you?
Yes. So as I said, for the transition metal, what we want to have is this ground triplet state. So D8 and D2 configuration give us that. And for the host materials, what we prefer is non-magnetic hosts, like for instance, diamond, and magnesium is mostly non-magnetic. So the ground state spins would not be so much interfered by the magnetic noise from the nuclei. However, for example, gallium arsenide has nuclear spins. Both gallium and arsenic has nuclear spins, and but that could be mitigated by dynamical decoupling methods. And of course, the advantage of gallium arsenide, of using gallium arsenide, is that it's technologically mature. So the fabrication of devices will be easier in the future. But basically, those are the criteria. We basically want to balance the noise and the ease of production.
We have time for one or two more questions for the panel, if there are any questions.
Yeah, so Tim Lawrence here. You're pretty junior in the field, so just wondering your motivation to work, because I've seen your academic attributes and it's very, I'll just say, noteworthy. So what's your motivation to pursue this type of science right now? Just curious.
Well, first of all, it's interesting. And it's interesting because I think it offers a possible solution to a problem that is still standing after many years of research in this field. The connecting spins coherently connecting spins to photons at high temperature is an unsolved problem. And I think we have an idea here that is definitely worth pursuing.
Nope, that's a great answer. Thank you.
Thank you very much. We will end it right there. Thank you again to Professor Palm. Apologize for the technical difficulties, but thank you for sticking with it. We will now move on, and I'd like to welcome Dr. Sutyavalu Paparao, also better known as Pops, from New York Creates, who will speak during the short 10-minute break. Thank you very much.
by POPs for short. I'm the VP for research at NY Creates. We at NY Creates are fortunate to be partners with AFRL Rome on many fronts relating to quantum technologies, from photonic quantum computing to superconducting devices. My colleagues and I believe firmly that we need to develop scalable quantum technologies from the get-go so that it is able to help society and this nation that much faster. How is this to be made possible? It is made possible by using state-of-the-art equipment and processes and advanced materials that we have available at Albany and Rochester. With our colleagues at AFRL and at other points in the United States, we are working on Josephson junctions and superconducting nanowire structures for applications ranging from superconducting optoelectronics for neuromorphic computing to SNSPD, superconducting nanowire single photon detectors, fluxonium qubits. We're working with AFRL's Mike Fanto on photonic quantum computing and a few other topics. I am very glad to be talking with you during the Quantum UTech Accelerator. I wish each one of you success on your endeavors. Thank you.
Our program will return in 30 seconds.
Welcome back. Up next in the communications track is Tobias Kippenberg from the Swiss Federal Institute of Technology. Please unmute yourself for a mic check. When you're ready to begin, please click the Start Presentation button on your screen, and that will start your 10-minute presentation.
Okay, good. I hope you can hear me.
Loud and clear. Great.
Very good. Okay, I press start here. Let's see. Okay, yeah, so it's a pleasure to present our views and vision on microwave to optical conversion of quantum states with bulk acoustic resonators coupled to indicator photonics. And so my name is Tobias Kippenberg. I work at the Swiss Federal Institute of Technology, and we're a group interested in quantum measurements and photonics. So let me start out by, again, motivating the subject that we like to propose, and that is the address the challenge of quantum coherent microwave to optical conversion. So over the last decade, there has been spectacular progress in superconducting quantum computing. And this has become the leading contender, okay, for quantum computing. And over the last years, we've seen massive progress in the ability to scale large areas of qubits into functional quantum processors that can even perform tasks that are on classical computers orders of magnitudes more difficult. And this is to realize what was called quantum supremacy. Now, the leading contender for superconducting quantum computing are superconducting qubits, which typically are held at very low temperatures, in this case, millikelvin temperatures, to freeze out any residual thermal motion and allow the quantum properties to be explored. Now, one key challenge in these experiments, and in particular in the future of superconducting quantum computing, is to interconnect different quantum computers. And for interconnection, what is needed is a quantum coherent interface. And quantum coherent implies that if you have a superposition of a microwave single photon state, that you can convert this into a superposition in a separate, physically distinct dilution refrigerator. And this requires a quantum coherent microwave link. Now, these are not yet realized. And one interesting approach to achieve that technological problem is to make an interconverter that converts a microwave quantum state of the microwave field into an optical quantum state. And so these converters would allow, on the one hand, to connect different nodes of quantum computers, but also serve a very interesting classical problem. These devices would allow, to replace the many coaxial cables that are used presently in superconducting quantum circuits, to interrogate with the quantum bits. And here's an image of the IBM quantum processor. And as you can see, there's many classical drive circuitry that connects the outer world at room temperature to the superconducting qubits. And each of these microwave line has a certain heat flux, about 10 milliwatt per line, that can be dramatically reduced if it was replaced by optical fibers. But this necessitates, again, a way to convert microwave signals to optical ones that can be transported over fiber. And so what are the applications, therefore, of such microwave to optical converters? As mentioned, primarily they can be used for quantum information processing to connect physically distinct dilution refrigerators and quantum processors. They can also, in the classical realm, be used to create cryogenic interconnects, that is to say, replace coaxial cables with optical fibers and readout of microwave signals using optical means. And also, they can be used in other kind of classical and scientific applications, ranging from radio astronomy, single photon sources, to also quantum radar, where you combine the correlation properties of optical and microwave photons that are enabled by a quantum coherent microwave converter that can generate entangled microwave and photon pairs. So over the last years, it has been realized that there's a need for such quantum coherent microwave to optical transduction scheme. There's been a lot of interest, in particular also from other US agencies like IARPA and also the Air Force, the ARO. And generally, there's today a multitude of approaches that have been proposed. And I'm focusing here on approaches that are solid state and that use integrated photonics, integrated electrical devices. And one can distinguish on the physics level 3 different approaches. The first approach is to couple microwave photons to optical photons via radiation pressure and using megahertz mechanical oscillators as intermediaries. So this approach has been realized, for instance, in the group of Conrad Lind at NIST, and uses flexural modes of mechanical membranes coupled to optical cavities. Now, 2 other approaches that recently has received a lot of interest, are approaches based on cavity electro-optics and piezo optomechanics. And I would like to focus on the piezo optomechanical approach. So the piezo optomechanical approach that we are proposing, and it's a new approach to convert microwave to optical fields, will use 2 optical modes, in this case, created by 2 resonators that are near-field coupled, that are split. And these are very efficiently coupled to acoustic modes. And these acoustic modes we're focusing on are so-called H-bar modes, high overtone or bulk overtone modes that live, in the photonic stack. And we recently explored these acoustic modes jointly with a group of Sunil Bhav at Purdue to create a very efficient interface of H-bar mechanical modes and optical fields for efficient modulation. And so the scheme that we have is that we use an aluminum nitride transducer coupled to a silicon nitride resonator, via a acoustic dielectric layer that serves here as a buffer and the cladding for the oxide. So our approach, again, shown schematically here, can be embodied or explained physically in terms of 2 coupling constants. On the one hand, we have the coupling constant that allows us to efficiently excite acoustic modes. This is the electromechanical coupling constant. Here, the key advantage of using aluminum nitride is that it can be very high. So one can, with high fidelity, convert incoming microwave photon to acoustic energy stored in H-bar modes. And at the same time, okay, by using the strain optical coupling, so the fact that in acoustic modes create a refractive index modulation, we can then convert that mechanical energy into an optical photon, okay, by virtue of these two split resonances. So what's the advantage of this approach? Well, it uses well-established foundry processing of aluminum nitride. It uses photonic integrated circuits with very low loss based on silicon nitride. And it also uses very high frequency mechanical modes that are intrinsically in a quantum ground state at low temperatures. And on top of this, this approach itself also lends itself to classical applications such as LiDAR, which we recently explored. So very briefly, okay, what we're using is aluminum nitride. This is a commercial foundry level process. We've collaborated with a group of Sunil Bhav by sending our photonic wafers to his group for further processing. ALN is already used in many timing applications for oscillators, filters, chemical sensors. The quality factors of the gigahertz acoustic resonance can be high, up to 3000, giving us megahertz of bandwidth of transduction. And the advantage of our approach is that we can combine with this approach the very high quality factors of photonic integrated circuit based on silicon nitride and efficiently couple them to acoustic modes. And so the advantage here is that we combine both low loss integrated photonic circuits, but at the same time use electromechanics that is afforded by ALN, and again, as mentioned, a proven MEMS technology. Now, in terms of mode overlap, okay, one aspect that makes this approach very interesting is that we have very efficient coupling of incoming microwave to acoustic energy. There we have unity efficiency due to the efficiency impedance matching, whereas we have lower coupling from the mechanical mode to the optical mode, but this can be enhanced, okay, by pumping the cavity with photons. And so if one looks at the key figure of merit, which is the so-called cooperativity, then we've computed, okay, that we should achieve a unity cooperativity, which is required for faithful transduction of incoming microwave photons to optical photons. We can achieve this at 2 milliwatts of optical power, which is well within the handling capability of a refrigerator and also within the handling capability of the material that we use. So what material are we using? The material that we're using is silicon nitride. And in particular, we make use of very low loss silicon nitride as developed by my laboratory. And today in our lab, we have chips, photonic chips that have less than 0.2 dB per meter loss. And by coupling two of these rings together, we'll create a frequency landscape that is suitable for the conversion scheme that I've proposed that uses split rings coupled to an ALN H-bar mode. And so if we look at the outlook of this approach, so we expect, first of all, with this approach to launch into a new direction of microwave to optical conversion that uses the H-bar modes, ubiquitously used in MEMS, but not yet for this purpose of microwave to optical conversion. So it's a new approach for microwave to optical conversion. We also believe that this is an interesting approach for quantum acoustodynamics, so for controlling the quantum states of the H-bar. And we believe that this scheme itself not only lends itself for addressing the question of how to interconvert microwave quantum states to optical quantum states, but we also believe there's an interesting application of these very efficient transducers based on ALN for classical operations or applications such as modulators, LiDAR, or high-speed interconnects. And this work that we propose is based on extensive experience we have gained in a collaboration with Sunil Bhav at Purdue, with whom we have established and explored this hybrid platform, and which we now like to use for the purpose of microwave to optical quantum state conversion. Thank you very much for your attention.
Thank you. Paper is now open for 5 minutes of questions.
Hey, this is Joel Mosier. Great presentation. Appreciated that a lot. And this is a little bit of an aside, but you mentioned some of the other classical applications of this, and I was particularly interested in your statement about use of this for radio astronomy. I wonder if you could talk a little bit more about what it brings to that application versus currently available technologies.
Yeah, the reason I brought up, I appreciate the question I brought radio astronomy is that in radio astronomy, you have M-kits, which are devices that can detect single microwave photons. And so this is important for experiments that explore, for instance, cosmic background radiation. And generally, detecting a single microwave photon is a task that is very challenging and can, at the moment, only achieved with M-kit technology. And so this is an approach where we would do the following. We could convert a microwave state, a thermal state, or a quantum state into an optical photon and perform the entire detection in the optical domain. And so in that sense, these transducers could also be used in applications for radio astronomers, where they look at the G2 function of microwave fields by converting to the optical domain and then performing the detection of single photons just with single photon detectors. So it's another approach, okay, to replace in certain applications the M-kits that exist already today.
Hey, Tobias, this is Grace. Very nice presentation, thank you. I think maybe I might have missed this, but can you maybe repeat I know you talked about the current state of the art. Could you talk about what your expected performance would be, transduction performance would be compared to the current state of art? And then my second part of the question is, what are your main noise source challenges and how you would mitigate those?
Yeah. So you have a twofold question. So I've refrained from putting a table in with the comparison, even though we have that. I think to date, I would say the state of the art right now in microwave to optical conversion, I would say the most advanced experiments are in the optomechanical domain and also in the domain that uses lithium niobate for direct transduction. And if I focus on the comparison with lithium niobate, there has been spectacular progress recently by a number of groups in the US, Marco Loncar's group, also at Yale, there's been very nice work from Hong Tang. At the moment, they cannot reach yet a cooperativity of unity. This is one of the challenges. And why not? Because if you use a material like lithium niobate for resonators, then presently the quality factors are lower than what we can achieve in silicon nitride. And so the unique, we think, advantage could be here to explore these very, very low losses that we have in a silicon nitride platform. And so even if we take our current estimates of a G of 400 Hertz, which is similar to what electro-optic couplings have achieved, due to the higher quality factor at present, we get a unity cooperativity of at 2 milliwatts. And we believe we can easily handle this amount of power in our silicon nitride circuits because there is no pyroelectric effect. We're using a pure dielectric. And this is also an advantage which we see over the direct electro-optic approach. The total conversion efficiency end will be limited just by how well we can couple to a bus waveguide. And we have shown that we can overcouple this strongly. So the output efficiency to the optical field can be close to, certainly larger than 50%, close to unity, in fact, if you overcouple. The microwave input line coupling to the mechanics, that is a unity transfer. That is because K squared Q is larger than unity for ALN transducers. So in that case, we will only be limited by how efficiently we can overcouple to the bus waveguide. If that answered the question.
Yes, so you compare to the lithium niobate
Yeah.
systems. Can you maybe say something about the optomechanical systems?
Yeah, absolutely. So optomechanics has also been widely explored. And here I would say the big advantage that we see is twofold. The first big advantage is the ALN technology we have right now can very efficiently convert an incoming microwave photon to an acoustic H-bar mode, which is not always the case for optomechanical approaches. If you use, for instance, nanoscale mechanical modes as in photonic crystals, then the impedance matching with the external microwave field or the IDT might not be perfect. So this is one advantage we have in this approach. And the second advantage that we see is that we use very high frequency mechanical modes. In this case, the H bars will be 5 gigahertz. So at 4 Kelvin, we'll already freeze out a significant portion, okay, of the thermal noise. At millikelvin, they're in the ground state. And this is not the case for megahertz mechanical oscillators. So if you have a megahertz mechanical oscillator as intermediary, there you have the additional challenge that the thermal state of the mechanics is actually highly excited even at millikelvin temperature. So, so we believe that gigahertz is useful to mitigate the thermal noises. And the aluminum nitride.
Thank you very much. We're going to have to end it there because we're slightly over. So thank you very much, Tobias.
Thank you.
Next up is Paul Helgen from Simon Fraser University. Please unmute yourself for a mic check. When you're ready to begin, please click the Start Presentation button on your screen, and this will begin your 10-minute presentation.
Hi, can you hear me?
Yes.
Okay, great. There we go. So hello, my name is Paul Haljan from Simon Fraser University in Canada. And thank you for the opportunity to present this idea for a wideband ion-based sensor for measuring electric field noise and motional decoherence in an ion trap. This idea is or builds on work that we're doing at Simon Fraser University towards towards precision control of vibrational modes, ion crystals and ion traps, and using those for measuring motional decoherence. We'd like to extend these techniques to advanced ion traps and cryogenic temperatures, hopefully using the facilities at the new Innovari Center. So I'll start here to give a brief overview of electric field noise in trapped ion quantum computers. So this can be an actual trapped ion quantum information processor or a local node in a network. The local quantum gates between ions are implemented using the collective vibrational motion of the ion string. Uncontrolled electric field, ambient electric fields, so electric field noise can lead to motional drifts in those vibrational modes. Phase noise can lead to decoherence. Ultimately, these lead to gate infidelities. Electric field noise as well can have other effects. So if you, for example, consider QCCD architecture for an ion trap quantum information processor, the ion trap information is transmitted across the processor by actually physically moving the ions, which makes use of the motion. When we consider the range of electric field bandwidth, or voltage bandwidth, that's of interest when considering the motion in the ion trap, it ranges really from DC through to the tens of megahertz. It corresponds to the RF Paul trap frequency, capital Omega. So in terms of electric field noise sources that can have detrimental effects, drifts and phase noise can be due to technical noise on the electrode voltages, fluctuating patch potentials due to charging or surface contaminants on the electrodes. In terms of heating at the motional modes used for entanglement, for example, this can again be due to technical noise or also well-known but still not completely understood anomalous heating due to electric field noise densities that are well above Johnson noise levels. So in order to understand the various noise sources within the ion trap, of course, it's interesting to consider the frequency spectrum. And some frequency studies have been done, but they typically focus on ranges of frequency that are close around the motional frequencies within an order of magnitude. So the idea here for this proposal is an in situ measurement that allows wideband measurement of frequencies essentially down to the DC level. So to give some background for the technique, let me start and tell you very briefly about the linear zigzag transition in ion traps, central to this idea. So in a typical linear Paul trap, strong transverse confinement will cause the ions to line up in a string. If you weaken the transverse confinement, change the trap aspect ratio, the ion crystal undergoes a phase transition from 1D linear to 2D zigzag. And what's important for this proposal is to understand that you consider the motional modes around the critical point of this transition, in particular the lowest lying transverse mode, the so-called zigzag mode here. It undergoes a very rapid change from high frequency all the way down to essentially DC, and then rebounds. So this is actual data taken in our lab. Now, while the zigzag mode is less sensitive than the center of mass mode, which is typically used for measuring electric field noise, it has this convenient feature that this rapid change of frequency, which we can control, allows for a wideband sensor. So to give you some idea of things that we've done in the lab to measure trap potential noise using the zigzag mode, show you a couple examples. The first one being drifts. And so if we park somewhere here close to the critical point and measure the zigzag frequency, this sharp feature in that steep slope allows us to read out with good sensitivity trap frequency drifts. So measure or monitor in time changes or fluctuations in the zigzag mode. And from the slope, we can infer fluctuations in the trap frequency. And the slope gives us a gain sensitivity of up to 50 for this particular situation of 4 ions. And what that means is that even before we time average, we can detect fluctuations extending down to the order of a few parts per million. So we've used techniques like this and measurements to optimize our trap stability down to these very low levels. So this was drifts. Let me tell you a little bit about measuring higher frequency noise, so essentially leading to phase noise on motional modes. And we can measure these by considering Ramsey measurements on the zigzag mode. So in particular, we make a sample measurement of making a Ramsey coherence measurement at a particular zigzag frequency, and we can extract the coherence decay. And by scanning the zigzag frequency, we can get a plot of the decay rate you see in the lower left here versus that frequency. This is preliminary work, but the essential idea of what we want to do is correct for the sensitivity of this measurement and thereby infer the underlying noise. You can see a sample plot over here on the right affecting the zigzag mode, in particular fluctuating electric fields in the trap. So the ideas for this proposal are twofold. First one is we'd like to extend these techniques that we've done at room temperature and in simple linear traps to advanced ion traps of interest to quantum information technology. So taking advantage, hopefully, of AFRL expertise in operating, for example, Sandia HOA2 traps, and also extending these measurements into the cryogenic regime. So the cryogenic, making cryogenic measurements of heating and studying temperature sensitivity is not new. This has been done before. What's new is this particular measurement technique. So the outcome, the main outcome for this type of measurement in experiments is ultimately really to extract spectral dependence of noise and use that to contribute to noise modeling and ultimately noise mitigation in ion traps. The second part of this proposal is a little more speculative and fundamental in nature. The idea is to make use of the cryogenic environment or cryogenic ion trap to explore a new kind of Schrodinger cat superposition state of static ion crystal structures. And the basic idea that's been proposed a number of years ago, Alec Retzker, is that as you cross this linear zigzag transition, the wave function associated with the zigzag mode goes from a single well to a double well, and that leads to a splitting like an interferometer of the wave function. And the superposition states that are created essentially are Schrodinger cat states. They're superpositions of two structures, zig and zag, which are very different from other Schrodinger cat states that have been created in ions that involve motional superpositions of motional modes. Here we're talking about superpositions of static ion structures. With different expected decoherence mechanisms. So we'd like to make use of tighter ion traps in this proposal and higher quality factor of RF trap resonator to push down the decoherence causing noise sources close to the critical point, with the idea of hopefully being able to observe these superposition states. Can they be formed? Can they persist in the environment of the ion trap? And ultimately, can we control this double well potential sufficiently, perhaps perform kind of type of interferometry, for example, to measure nonlinear electric fields causing biases in this potential and their fluctuations. So again, tying back to studying electric field noise and decoherence. So in conclusion, our aim is to really use this technique for wideband electric field noise assessment, motional decoherence in the ion trap, to provide some new perspectives on ion trap motional decoherence and contribute to a deeper and broader understanding. Thank you for your attention.
Thank you very much. Paper is now open for questions.
Hi, Paul, my name is Bindu Nair, and I really was interested in that last little bit that you talked about, the possibility of that quantum superposition of the two ground state wave functions. So if we can, if we push on that a little bit, how does that work within the context of the main proposal that you're trying to push forward, like, you know, understanding the stability of the trap potentials to noise, that kind of stuff? Do you sort of think of these as like one project? And maybe you can just talk a little bit about how you might be able to explore that.
Yes, they are tied together in the sense that you can use these superpositions to investigate decoherence within the ion trap. And ultimately, so again, we typically would expect the decoherence mechanisms within are causing these wave functions really to decohere, to be due to electric field noise. And within our current experiment, actually, we are able to measure decoherence close to the critical point, and it's too large to really be able to look at tunneling coherence effects within this double well. So by pushing to this cryogenic environment, on a fundamental side, I'm interested just to see if these states can be created. But on the technical side, it really ties back ultimately to assessing electric field noise and really pushing the limits of decoherence in ion traps, which are have a long history of doing so for being a clean environment.
Hey, Paul, this is Grace. Thank you for a really nice talk. I had a couple of questions. One was, do you have a current collaboration with Sandia? And if not, how would you propose to have access to some of these new advanced ion traps? And well, I'll just do one at a time.
So I currently don't have an existing collaboration with Sandia to access some of these traps. I certainly have the capability to work with some intermediate gold on alumina traps that we can use for you know, something that's closer to a what are used in quantum computing applications today. But I'm particularly interested in doing these experiments, if possible, at Innovari Center, just because I think it can move the project forward faster and become relevant faster, just because of the expertise in operating those traps already, which can really make the project happen quickly.
So unless somebody else has a question, my second question is, could you say a little bit about how your work compares to some other work on noise spectrum analysis?
So most of the work that I'm familiar with is really from the ion trap community, and so specifically dealing with ion traps. So the kinds of experiments that are standardly done and that we do as well, measuring this center of mass mode, have been done widely with single ions, and there's been temperature measurements. There's been a great deal of measurements that looking at cleaning of the electrodes and the outcome of heating. So there's a huge body of literature around that. In fact, I have a reference in my poster to a review of that from the Innsbruck group. This particular project I see as one particular niche actually that fits in, that hasn't been done before, to really explore a wider frequency range. And so by exploring a wider frequency range, we'll capture, we'll capture noise sources, both technical, due to voltages applied to the electrodes, through to other noise sources relating, for example, to fluctuating patch potentials, sort of all in one go. And I think that it, in terms of a convenient in situ measurement, it has some benefits from that to really contribute to that wider body, something that
Thank you very much. Thank you very much, Professor Haljan. We'll end there as we're out of time. Thank you once again. Next up is Alp Sipahigiel from UC Berkeley. Please unmute yourself for a mic check. Sounds like we're good. When you're ready to begin, click the Start Presentation button on your screen, and you can then begin your presentation.
All right. Hi, everyone. Thank you for the invitation. I'm Alp Sipahigiel. I'm a new assistant professor at UC Berkeley and the Lawrence Berkeley National Laboratory. And I want to present you our ideas on developing quantum memories for superconducting quantum networks. This proposal is a collaboration with Professor Ming Wu's group at Berkeley Electrical Engineering, and Ming is an expert on MEMS and photonic nanosystems. So Tobias and John gave really nice introductions motivating us for trying to connect different superconducting qubits in some optical communication network. I'm just going to repeat some of these points. So when we look at different architectures for quantum communication, what we see is that these protocols require us to combine small quantum computers that can exchange quantum information over long distances via optical photons. And traditionally, our community has studied systems like trapped ions or neutral atoms or color centers. But recently, there's been a tremendous amount of progress with superconducting quantum circuits. And therefore, a natural question is to see if we can leverage advances in superconducting quantum computation and use these systems for applications in quantum communication. So the vision we have looks something like the following, where we have quantum communication nodes, where at each node we have a quantum processor that's made out of superconducting qubits. And then we're going to connect these superconducting qubits over long distances by realizing transducers that can convert microwave photons to the optical domain. And in addition to this transducer, we also need to realize quantum memories that can store quantum information for extended periods of time while we're communicating across these different nodes. And as I mentioned, the main advantage here is that it really makes this architecture makes use of advances in quantum computation based on superconducting circuits. And in terms of realizing this vision, there are two major open challenges, and I'm going to want to discuss both of them briefly now. The first one is related to realizing efficient and low noise transducers that can convert quantum signals from microwave frequencies to the optical domain. And in the last year, when I was a postdoc in Oscar Painter's group at Caltech, we developed a new device platform that can integrate superconducting qubits, piezoelectric transducers, and optomechanical crystals to convert a superconducting qubit excitation to an optical photon. So in this experiment from last year, we converted the qubit excitation to a mechanical excitation using aluminum nitride piezoelectric transducers. And then we came up with a design that combines this piezoelectric transducer with an optomechanical transducer to convert the phonon to an optical photon. So when we combined all of these ingredients together, we were able to show the first demonstration of optical photon generation from a superconducting qubit. So at the moment, the efficiencies are in the range of 10 to the minus 5, but this was a first experiment, and it's a really exciting development, which is a great motivation to explore quantum memories that we can develop for this device platform. So in this pitch, what I want to focus on is not this transduction work. I'd be happy to take more questions on that in the Q&A session if you're interested. But what I want to do is to focus on developing new types of quantum memories that are compatible with this hybrid quantum network architecture. And the system that I'm interested in is using acoustic nanomechanical systems as quantum memories. So the current practice for realizing quantum memories for superconducting circuits can use things like planar superconducting qubits or microwave resonators, but these systems have a typical coherence time of about 300 microseconds or so. These 300 microseconds can be sufficient for quantum computation because when we're doing quantum computing, we compare the coherence time to the gate time, and the gates can be really fast for quantum computation. But when we're interested in quantum communication, we're interested in sending optical signals over thousands of miles, and there's some propagation delay at the level of tens of milliseconds. So our quantum memories in this architecture need to have coherence times beyond tens of milliseconds. So we need a new type of memory. And then secondly, this is perhaps a bit of a technical point, but superconducting qubits and microwave resonators are very sensitive to optical fields. So if you shine a laser, if you have an optical transducer nearby, what we found in our experiments is that the superconducting qubits will rapidly lose their coherence. So this is a major challenge for integrating all these components together. So one of the solutions that I'm really excited about, it makes use of nanomechanical systems to address both of these challenges. So the systems that I'm interested in are of the following form, where we start with a silicon on insulator substrate and we use e-beam lithography and dry etching steps to pattern suspended membranes that look of the following form. So at the center, you're seeing a nanomechanical resonator that's at high frequency at 5 gigahertz. And then in order to increase the lifetime of these phonons, these mechanical excitations in these nanomechanical resonators, we isolate this mechanical resonator from the environment using these acoustic shield structures. So these acoustic shields are structures where we pattern the membrane in such a way that we engineer the phonon dispersion, and we can create a complete acoustic band gap from 3 to 6 gigahertz. So what this means is that if we have a mechanical resonator here, it's surrounded by these mirrors that don't transmit phonons between 3 and 6 gigahertz. And this allows us to realize acoustic modes with extremely long phonon lifetimes. And a second point I want to highlight is that these devices, as a quantum memory, they're very compact. So the entire structure here is about 20 micrometers inside. And when you compare that to a superconducting resonator, that's about a few millimeters in typical dimensions. And when we studied mechanical resonators that are being protected by these acoustic band gaps, we found that these mechanical resonators can have extremely long lifetimes in the range of about 1 second. This corresponds to a quality factor of about 40 billion. So this is a really interesting number and makes it a very interesting system for exploring as a quantum memory. So in the proposed work, what we want to do is address some of the remaining open challenges. So I've told you that the lifetimes of these systems are very long. So the T1 is about 1 second, but the coherence time, the T2 star coherence of the system is limited to about 100 microsecond or so. And if you're kind of familiar with solid state devices, you probably are realizing that this is a very large gap between the T1 and the T2 star. And what we're interested in doing here is to see if we can push the T2 star, the coherence time, closer to the T1 limit. And in order to do that, we're going to use a new set of tools and new types of devices to first understand the microscopic dephasing mechanisms and then use this understanding to advance coherence in the system. So I want to quickly give a description of our current understanding of dephasing in these structures. So at low temperatures, I'm talking about dilution-rich temperatures that are compatible with superconducting qubits. The main dissipation and dephasing occurs via the interaction of mechanical modes with two-level systems. These two-level systems are atomic scale defects. They can interact with mechanics, they can interact with superconducting qubits, and they cause dissipation by phonon emission. So these are, you can think of these as acoustic quantum emitters that radiate phonons into the bulk of the substrate. So the main idea we want to pursue in this research program is to engineer the properties of these two-level systems. So far, they have been treated as a black box. And what we want to do here is actually to engineer their emission properties by embedding them inside acoustic bandgap media where phonon radiation is forbidden. So in the proposed experiments, what we want to do is to develop a device platform where we're going to develop superconducting electromechanical devices on acoustic bandgap media. So we're going to, in the first year, we're going to develop a fabrication process to do that at UC Berkeley's shared nanofabrication facilities. And we're going to characterize these devices where we're going to be able to probe the properties of individual TLSs coupled to high impedance superconducting circuits. So this will be done in our low temperature microwave spectroscopy lab. And the expected outcome here is to observe and make the first set of direct measurements on TLS properties. So our goal is to enhance the lifetime of these two-level systems by acoustic engineering and by suppressing phonon radiation using these engineered acoustic structures, and then use that understanding to improve properties of mechanical quantum systems. And then more broadly speaking, the same kind of a very similar dissipation and decoherence mechanism is also relevant for the dissipation of superconducting qubits. So if we can directly observe and engineer the properties of two-level systems by controlling their acoustic environment, then we could also come up with new recipes to improve the coherence and dissipation properties of superconducting qubits as well. Thank you so much for your attention.
Thank you. Paper is now open for 5 minutes of questions.
Yeah, Mr. Olmoja, thanks for the great presentation. Can you talk a little bit more about the efficiency and then the noise and error characteristics of these nanomechanical resonators?
Right. So if we don't do anything, if we just nanomechanical resonator B by itself, then the noise is very low. This is a very high frequency mechanical oscillator. It's at 5 gigahertz. And at the temperatures we're operating, the thermal noise is negligible. It's very, very small. So that's good news. And when we couple to these mechanical oscillators from the superconducting qubit side, this is also a very low noise process because superconducting qubits are very low energy systems. There isn't a lot of energy. Everything is very cold. And when you swap from a superconducting qubit to mechanics, you don't introduce much noise. So this is also a very low noise process. And the efficiency there is close to 1. So it's something in our last experiment was about 75% or so. And this can easily come. There are other experiments that brought this closer to 90, above 90%. However, the problematic part is phonon to optical photon conversion. So there we're using a parametric process. And in this case, we were very gentle. We shined in only about a microwatt of laser power. And this still causes some heating of the mechanical resonator because we are talking about adding only one thermal excitation into the system. And these are very small systems. So that's actually, in my view, is one of the biggest open challenges. When you shine in a laser, what happens? And actually, in this reference that I mentioned at the beginning, that was the biggest obstacle. So if we just cranked up the laser power, we could get to very high efficiencies, but that adds a lot of noise. So this was a demonstration where we had to balance efficiency and noise and demonstrate this optical photon generation for the first time. So noise is extremely important and comes into effect mostly on the optics side.
We have time for 1 or 2 more questions. If anyone has any further questions for Al.
This is Frederick Fatimi. It was a very interesting talk. I'm curious what you think is the sort of most challenging or riskiest part of this proposal?
So one thing we know is that we are going to get an improvement in TLS lifetimes. That I feel very confident about, but we don't, this is new, these are new effects. So this is a new regime that we're not familiar with. So one thing that I'm not sure, and I don't think anyone knows, is whether that improvement will be 2 orders of magnitude, 4 orders of magnitude. What are the higher order processes once we suppress the dominant dissipation effect? So those are the kinds of questions which are open. So it's the risk is in the amount of improvement we'll get. So I'm sure we'll have a significant improvement, but I don't know how many orders of magnitude it will be.
Thanks.
Any further questions from the panel?
I'll ask a question. Thank you for your presentation. I was wondering how your approach couples with the different types of superconducting qubits. For example, some of the newer 3D qubits.
Right. So the traditional approach tries to minimize the effect of two-level systems, and that's one of the driving forces for going to three-dimensional geometries. And when you go to these three-dimensional cavities or kind of bigger superconducting qubits, you're going to more bulky systems where the number and density of effective density of two-level systems is reduced, because these two-level systems live in surfaces, and when you have an empty cavity, there's not that much surface. So the motivation for this is something else. So here what we want to do is, okay, we want to make compact qubits, and when you make compact qubits, you have a lot of surfaces. And the approach we're taking here is, okay, when we do that, there's going to be a higher density of two-level systems, and can we instead use acoustic engineering to engineer the properties of TLSs instead of trying to get rid of them? So this is complementary, and if it works, and I'm sure it could also be adapted by most qubit approaches.
Thank you very much. We will end it there. Again, thank you, Alp, for a great presentation.
Thank you.
Up next is Marco Longcar from Harvard University. Please unmute yourself for a mic check. When you're ready to begin, please click the Start Presentation button on your screen, and your 10-minute clock will begin.
You guys can hear me?
Yes.
Perfect. Excellent. Thank you so much for the introduction and for giving me this opportunity to participate in this exciting event. So I'd like to tell you a little bit about our plans for development of photonics platform that could enable many interesting functionalities that were discussed during the last 2 days. And in particular, then I would like to focus what we would like to do with this platform. To step back a little bit, kind of to take a zoom out, view what my lab, and as well as many labs around the world, especially those participating in this event, are focused on is building this sort of distributed network of quantum gizmos, quantum computers, quantum sensors, precision clocks, and so on and so forth that are connected with coherent quantum optical networks. So that's something several people have already mentioned today. In particular, in our lab, we are focusing on building quantum repeaters and quantum transducers. In fact, we have started the STTR program on quantum transduction with Rigetti, funded by FRL. But what is common to all of these things is really that information will be carried between different nodes of such a quantum network using photons. And in order to do this in efficient and scalable fashion, integrated quantum photonics developments are needed, or rather integrated photonic development that can enable quantum functionality that are needed. And this is actually not an easy task because quantum is basically, requirements of quantum are a lot more stringent, I would say, than of classical communication. For example, you need to have ultra low loss optical waveguides that can operate in visible and telecom wavelength range. You need strong nonlinearities so that you can connect these visible and telecom photons. You need also very high extinction ratio filters to separate strong pump fields that are used, let's say, to excite quantum memories from single photons emitted by these quantum memories. You often need to actually do spectral and temporal engineering of photons to match bandwidths of different quantum emitters of different type of single photons. And often you need to send information in different way using very fast switches and routers. So kind of we are implementing one such vision. So this is like a cartoon of a hybrid quantum system that will allow all of this functionality. And this is something we just recently started working on with Dirk Engeland at MIT. We're combining diamond memories with integrated photonic platform that could have all of these characteristics. And so while there has been tremendous progress in integrated silicon and silicon nitride photonics for classical communication, and some of the pioneers and leaders in this field have presented in this workshop today. For example, Tobias was talking about some of these spectacular silicon nitride devices. There are some problems. And for example, silicon, which is kind of the workhorse of telecommunication and datacom industry today, it has high loss, and more importantly, does not support low loss switches, which are very important for quantum applications. Silicon nitride, on the other hand, can have ultra low loss, but it's slow because you can only use thermal effect. So I like to point out classical photonics platform or conventional photonics platform that you use give you two choices: slow or lossy. And another problem or challenge, perhaps, for classical the current applications, current implementation of quantum photonics is they either use polarization or path encoding, and both require rather complex circuits. The polarization is really hard to implement on chip, so you need to double the size of the chip pretty much. And path encoding scales up unfavorably, basically, because for each qubit you need essentially a directional coupler, two waveguides, and so on and so forth. So we believe that materials with strong second order nonlinearity, and lithium niobate is one particular example of such system, are actually very promising for quantum applications. And in fact, actually, lithium niobate in particular has been used in quantum optics for years, decades, I dare to say, as a source of entangled photon pairs, as a frequency converter, as well as lithium niobate modulators are kind of the workhorse of this kind of frequency domain quantum computing, photonic quantum computing approaches that have been recently proposed by Oak Ridge National Lab and Purdue, for example. But lithium niobate is long considered impossible to integrate because lithium niobate is a very difficult material. And so a few years ago, we started looking into this problem. Okay, so it seems this may have frozen. Okay, here we go. We started looking into this problem, and we figured out ways to make ultra low loss integrated lithium niobate photonic devices and use them to make filters of various sorts. We have used them to make frequency converters, supercontinuous sources, which are also we are currently exploring in the context of atomic clockwork with vector atomics, for example. We have demonstrated very fast electro-optic modulators, as well as demonstrated different types of frequency comps that could be of interest for frequency domain quantum communication and computation that I'll briefly mention. I want to point out all of these demonstrations and all of these activities are found in classical domain, but as we perfected the platform and also demonstrated that this is actually a scalable platform that's already being commercialized by a startup from our lab, we now believe that actually the platform is ready to be pushed really into quantum limit, which, as I mentioned, is a lot more demanding. So what we want to do in this program, we would like to essentially demonstrate quantum communication that's using frequency domain qubit encoding instead of polarization encoding to demonstrate quantum key distribution. And this was just a starting point. This is something we thought we could do within 1 year time frame of this program. But as I mentioned, the platform itself has many other potential applications that I'm also briefly touch upon. So in classical conventional BB84 protocol, essentially, transmitter uses polarization state of photon to encode information, and especially uses two different bases, horizontal, vertical, and diagonal bases, and ILS chooses this random basis, sends quantum information to Bob, who then also chooses a basis at random, does measurement, and then later compares his choices with Alice's choices or conventional communication channel. And so what we would like to do really is to see what are the advantages of going into frequency domain. We believe this is going to be a more robust approach. And especially in frequency domain, using frequency encoding of a qubit, essentially qubit is encoded in two frequency bins. We need one communication channel, one spatial mode, and one polarization mode. So essentially this allows also frequency as well as polarization multiplexing down the road. But critical component that's missing is beam splitter in frequency domain. So beam splitters or polarization rotators in context of polarization encoding do exist. These are just wave plates. For path encoding qubit, these beam splitters, as we don't know them, spatial beam splitters, like on-chip directional couplers, off-chip, they would be your bulky beam splitter, crystalline-based beam splitters. So they're used essentially to change, kind of take a qubit, let's say, that's defined a vertical polarization, put it in the superposition state of vertical and horizontal. In this case, qubit is in one waveguide, and then after this beam splitter, you can go again in superposition of being in both waveguides. In frequency domain, we need something that essentially takes qubit from one frequency bin and frequency one and puts the superposition of two frequency bins. And we have developed such a device using photonic molecule concept. Basically, this is a device. It's lithium niobate ring resonators that are coupled, and we draw in microwave signals. And by controlling the strength of microwave signal that is coming down these gray lines, basically what happens, we can actually take photon from one color and map and move it entirely to another frequency bin, change its color essentially entirely. Or if we dial down microwave signal, we can actually put in a superposition of these two different frequency bins. And we have demonstrated this already in classical domain. We were able to demonstrate 99% frequency shifting efficiency, as well as for particular power, like this in the middle, we also demonstrate we can do actually the superposition state demonstration. And so really what we would like to do in this program is essentially use analysis and use this photonic molecule where we would just control microwave signal. And this is microwave signal we would apply shown at the bottom here. And these microwave signal will take single photons from one frequency bin and put it either in superposition state. This would be our diagonal basis, or shift it from one bin to another, which is our horizontal vertical basis. And so here's the detailed plan of action. Basically, the biggest thing is really to test these devices in the quantum domain and see how they perform in this context, and then demonstrate kind of high-rate communication protocol using this. And kind of, again, going back, our vision is that this platform would enable not only this particular activity, but also really many other activities. And it's energetic of many ongoing activities that we have in quantum domain, including frequency quantum domain, photonic computing, as well as some quantum transduction that's currently supported by ARO and AFRL. And finally, I think the biggest outcome of this effort will be quantum smart workforce, as it has been mentioned. And we already actually have activities in that domain, including promoting the
Thank you very much, Professor Lonkar. We need to cut you off right there and move to our 5 minutes of questions.
Hey, this is Joel Mosier, great presentation. I think you mentioned it on one of your charts, but I wonder if you could explore a little bit more about what your expectations for qubit crosstalk might be. I know you're going to try to characterize it, but what do you expect?
Yeah, so that's a wonderful question. So we have actually, this is kind of one of the things that we really want to check. So based on classical, maybe it's better to show it here, based on classical demonstration. So we have 99% conversion efficiency at the moment, which means 99% of photons of one frequency end up going to another frequency. And that 1% is actually part of this is lost, and part of this is just remains in the original frequency bin. So based on that, I guess, suppression, if you will, this unwanted signal is on the order of 20 dB. We think this can be better, in particular by further engineering, as Tobias mentioned already, for example, coupling between ring resonator and the waveguide by optimizing microwave power delivery, yeah, essentially characterizing this thing with single photon sources is going to be really true demonstration of how good this is. But at least it's a better than 20 dB efficiency at the moment, which is probably not ideal for a quantum protocol.
Time for a few more questions from the panel.
Well, if nobody else is going to ask one, I'll ask another one. Can you talk a little bit about the fabrication or problems or issues related to the thin film, the GFLN devices?
The lost, I mean, yeah. So that's something we actually spent probably a good 6-7 years trying to figure out how. We started the project 6-7 years ago. It took us maybe 2-3 years to figure out how to etch lithium niobate properly. And what is really good is that actually we are using standard fabrication tools, standard fabrication recipes that are just uber optimized. And I like to kind of point out, I mean, a lot of this has to do with our ability to tolerate rather large pain in a clean room. And we kind of characterize every step of the process very carefully. And the biggest issue in lithium niobate is really redeposition, right? So when you etch lithium niobate, you get a lot of material that you're removing away gets deposited in some sort of compound that needs to be removed. And so how to deal with this was actually kind of big trick. What's nice that since then, actually many groups around the world have already demonstrated ability to kind of reproduce these results, which is very good. So at Stanford, Yale was mentioned earlier, Rochester, and there's actually a bunch of people in China now that kind of followed up. And so it's, yeah, the platform works now.
So I was wondering whether, first of all, great presentation, thank you. And I thoroughly enjoy this frequency domain entanglement concept. It's really very cool. I know it's very early in the game, but I wondered if you had thought about at all about integration into other parts of quantum systems in general.
Yes, that's actually, so we started looking at this frequency domain quantum processing from the point of view of computing first. And there was some really nice theoretical and experimental work by Oak Ridge and Purdue, where they basically demonstrated using this discrete components modulator, they can demonstrate really nice quantum computing protocols. The main problem is the insertion loss of these devices is really bad. Every time you go on off discrete modulator, you lose 3 dB, so the depth of the quantum circuit is very shallow. So we wanted to bring these things all on chip using essentially the same material platform. And then once you have this quantum computer, then you start thinking, okay, well, if I'm already working in frequency domain, then I might as well communicate in frequency domain, right? So that's why we kind of started looking into this communication protocol that leverages frequency as well, as proposed here. And then I guess, since we have also ability to go, let's say if you want to connect it to sensors, since lithium niobate is nonlinear and periodically pole lithium niobate is used to change the color of, let's say, NV emitted photon to telecom, we can also integrate this with quantum sensors. Issue there will be bandwidth, which is what I mentioned also, which is also why we need these fast modulators and spectral shapers, I would say, to adjust all these different bandwidths of different quantum systems so they can talk amongst themselves. I think lithium niobate is a good platform for that.
Thank you very much. We'll end it right there. And once again, thank you, Professor Alarnkar, for a great talk. We will now hear from Dr. Eden Figueroa, Associate Professor, Department of Physics and Astronomy at Stony Brook University. He will speak during this short break and will return right after the conclusion of this video. Thank you.
Hello, everybody. My name is Eden Figueroa, and I'm a professor at Stony Brook University and also a joint appointment at Brookhaven National Labs. I would like to kindly thank AFRL for the opportunity to advertise our work today in this wonderful conference. Today, thanks to the opportunity, I would like to tell you a little bit of our work towards developing a New York-wide center, which has as a goal to develop a scalable hybrid quantum internet that covers everything from Long Island all the way to Buffalo. So in order to motivate why this is a very important topic, I would like to then discuss some of the documents that have been published recently coming from the federal government, in particular, a document from the White House that is called the Strategic Vision for America's Quantum Network, that basically tells us the necessity to start developing a very comprehensive program with regards to interconnecting different quantum networks across states. So this seems to be a very, very important issue, and also the Department of Energy, through the Quantum Internet Blueprint Workshop, told us already what is the roadmap towards achieving a quantum internet that connects, across many states in the nation. So then the question that we want to address here is how we can solve this question in the state of New York. And in order to gain some credibility, I want to show you here very briefly our recent results in what is the Long Island Quantum Network that already connects with quantum channels, the quantum labs in Stony Brook University and Brookhaven National Labs. So then very briefly, and this just happened a few weeks ago, we have achieved what to our knowledge is the longest quantum communication experiment in the United States, covering a total distance of 140 kilometers. So then what we want to do is use the blueprint that we have used on Long Island to do this network, and then apply it to the state of New York by forging lots of partnerships with different universities and national labs across the state. So basically what we want to address is basically look into what are the concepts that we need to develop in order to get to a quantum internet prototype. And this is what you see here in these slides, right? What we want to focus in our proposal is to do hybrid technology development that uses the technology that many of our partners have, and then ask ourselves the question, how is that we gonna do to connect it? And then the second question that we want to address is to start creating an infrastructure of fiber opticals that are already deployed between labs among our partners, so then we can start building a first prototype of this quantum internet. And then, you know, together with developments in the theoretical areas of quantum algorithms and sensing, then we can start using these applications for building this prototype here in the state of New York. So this effort that we're discussing today, you know, it has almost 2 years in the making, and is basically a merge of different ideas between different teams across the state of New York. So it's basically 3 main ideas. One that was a conceptualization grant from National Science Foundation from last year that is basically led by the team on Long Island. There is a second conceptualization grant that is led by the team in SUNY Buffalo that is materials oriented. And then there was an application for a full QLCI center from the University of Rochester. So then basically we put together the best people of these efforts, and then how then we merge in this New York-wide effort that is our Quantum Leap Challenge Institute for Scalable Hybrid Quantum Internet, right? And here you see a little bit of the concept of the science that we want to do in this center, right? So actually we did a comprehensive search of all the technology that our partners across New York are providing, and we put it here in this concept of what a hybrid quantum network should look like, and then basically how all the components that are needed, such as qubit, transaction devices, entanglement sources, and quantum memory, should then be placed together into this hybrid quantum network. And then the main question that we would like to address is how do you connect all of these different technologies so then you can form a heterogeneous quantum network prototype. And this is what we have here in this slide. Here you see that by grouping all these different technologies in terms of the energy scale in which they operate, that basically defines the main research challenge that we want to tackle, which is making them, all of them work across the board in the same energy band. That could be, for example, in the telecom, or it can also be in the visible if you would like to do communication in free space. And as you can see here, it does look like many of the technologies that we already have available are already working more or less in the same energy scale. The only thing that we need to do is to hone down to then make that energy scale where they work narrower and narrower, so then they can really talk to each other. And then of course, the other part that is very important is to develop transaction across energy scales that is gonna make quantum processing systems, for example, using superconducting devices or chiral materials to then work with these visible quantum networks. This is actually the slide that I will everybody to keep in their mind. This is the concept of this quantum internet that we would like to develop in New York. And then what we want to do is basically use the concept of quantum local area networks to develop 3 of them in different places of the state of New York. So then we have one test bed that is going to be located on Long Island that is going to be dedicated to communicate Stony Brook, Brookhaven National Labs, and the City College of New York. That will be the test bed A. There will be a second test bed, which will be located in upstate New York, connecting the city of Albany to Rome, New York, which is where this wonderful workshop is taking place. So then there we would like to explore how to connect hybrid systems such as the one that AFRL has that are, for example, ion and photonic based to the systems that are developed in SUNY Poly that are more silicon doped with ions, for example, erbium. And then there is a third test bed that it will connect then SUNY Buffalo, the University of Rochester, and Cornell University, that will be dedicated more to explore advanced quantum technology that is based on quantum materials, right? And then the idea is that putting this together with the efforts that we already have with the Department of Energy towards developing quantum repeaters, then we will be able to connect these 3 local quantum area networks into a larger quantum wide area network that then covers the majority of the academic institutions in the state of New York and national lab partners. And then, you know, that's a little bit of the dream that we want to do. This is where this QLCI proposal is going. And then just to finish, I want to give you an overview about the partnerships that we've been able to forge in the last 2 years. And then as you can see here, this proposal dedicated to the quantum internet is already collaborating, or it targets to collaborate some of the recently named quantum centers across the United States, either from the NSF or from the Department of Energy. We have a strong set of national lab partners, particularly the Air Force, the Air Force Laboratory. You know, they visited us on Long Island last year, and that was the beginning of wonderful conversations that then merged into this proposal. Of course, we have a strong partnership with Brookhaven National Labs and some other national labs. Something that is being developed thanks to one of the organizers of this workshop, Heather Hedge from SUNY Research Foundation. We're putting together a very strong industry council that basically puts together a lot of different private sector partners ranging from quantum startups to venture capital to mid-scale and large-scale companies that are specifically interested in the topic of quantum communication. And then on top of that, we have a very strong international board, which basically all the experts in the field of quantum communication giving us a feedback where to go with this. And, you know, just to finish this small presentation on this Quantum Challenge Institute proposal, I would like to say that this, what you see here in this slide, is basically the beginning of this concept that in order to build such a large quantum system, such as a quantum internet prototype, we can only do this if we can put together a synergistic collaboration between academia, the national labs, and the private sector. And then what we're trying to do here is basically a first version of this extremely long consortium dedicated to build this large quantum system. And then so with that, you know, if there are further questions, I will be very happy to receive your question by email. And I thank you very kind, the AFRL, for the opportunity to present this QLCI proposal. So thank you very much and keep enjoying this wonderful workshop.
Thank you very much, Professor Figueroa. Welcome back to our final portion of the communications track. Our first presenter is Shu Sun from Jilla in the University of Colorado Boulder. Please unmute yourself for a mic check. When you're ready to begin, click the Start Presentation button on your screen, and you can then begin your 10-minute presentation.
Hello, can you hear me?
Yes, loud and clear, thank you.
Great. All right, thank you very much. I would like to talk about our proposal on development of a multi-partied entangled photon source. Again, my name is Shu Sun. I am an associate fellow of Jilla and also an assistant professor at the physics department of the University of Colorado Boulder. Just to give you some background information, sources of multi-partied entangled photons are very important for many quantum communication and networking applications. One of their most important applications is to extend quantum networks from point-to-point communications to multi-node communications. Just to give you an example, we can consider a secret sharing problem where Alice has a key and she wants to share the information of the key with both Bob and Charlie, but she also wants to make sure that Bob and Charlie can only get the information when they work collaboratively. And the quantum secret sharing protocol requires the distribution of a 3-particle and in general an n-particle GHZ state among all the users. Another example I'd like to share with you. I have some problems. Okay. Sorry. Another example I would like to share with you is quantum anonymous transmission, where so if we consider only point-to-point communications, then the only message or the only information that we want to protect is the messages being transmitted from the sender to the receiver. But once you start to consider like multi-node communications in a network, then not only just the messages, but also the identity of the sender and receiver of each specific message can reveal very important information. And to protect those information, we have quantum anonymous transmission protocols. And these protocols again requires the distribution of a GHZ state in general. And in general, we can also not only just focus on GHZ state, but also you can consider like n photons that they are entangled arbitrarily. And this arbitrary entanglement structure can be represented by a graph. So if for some specifically designed graph state, such as a tree state or a repeater graph state, they are useful resources for building these one-way quantum repeaters. And those quantum repeaters can offer much higher communication rates than traditional quantum repeaters based on quantum memories. Therefore, generating this multi-photon entangled state is in general also useful for long-distance quantum communications. So there is a lot of latency. So since the multi-party entangled photon generation are so important, why we don't have them now? Apparently, experimentally generating this n-photon entangled state are extremely difficult because we don't really have a good way to introduce photon-photon interactions. So previously, a previous attempt to generate these photons are all based on some probabilistic processes and post-selections. As an example, if you look at previous attempts to generate the GHZ state, if you look at this table, people are only able to approach about 10 photons, and the success probability is extremely low in the order of 10 to the minus 12. And the coincidence, the success rate is very low as well, in the order of 1 per hour. And this low rate is essentially practically useless in like experimentally testing any quantum communication or networking protocols. I would like to mention that generating arbitrary entangled state could only be more difficult. There it requires some probabilistic fusion gates, and these fusion gates requires essentially like very perfect single photon sources, many of them, as well as very fast feed forward. So our current technologies do not support the realization of these protocols. So our experimental idea is based on like a deterministic approach to generate these multi-party entangled photons. This original protocol is proposed by Littner and Rodolph. We start with a single quantum emitter, and it has a spin degree of freedom. If we prepare the spin initially in a superposition, excite them coherently, and wait for the spontaneous emission, then you will emit a photon that is entangled with a spin. By repeating this process for n times, of course, you can generate an n-particle GHZ state. And this protocol can be slightly modified to generate an arbitrary one-dimensional entangled photon state. And there has been some previous preliminary demonstrations of this protocol with up to 5-photon GHZ state. Unfortunately, the 5-photon GHZ state success rate is even lower than the previous SPDC-based probabilistic approach because their system has a very poor collection efficiency. Another limitation is fundamentally associated with this idea. which only allows us to generate one-dimensional entangled photons. And as I mentioned, there are a lot of other useful states, but photons has to be entangled in a two-dimensional structure. So experimentally, to overcome the first challenge, which is the poor collection efficiency, we would like to couple the quantum emitter with an optical cavity. So the coupling between the quantum emitter with an optical cavity allows the emitter to predominantly emit photons into the single cavity mode, and therefore facilitate the efficient collection of photons. Cavity also offers some other advantages, which I don't really have time to go into details. I just want to share with you our experimental platform, which will be again based on those semiconductor quantum dots. The reason is because those quantum dots are, to date, they are the best single photon sources known so far. They have very high quantum efficiency. They are the brightest single photon sources. They can emit photons with very high purity and indistinguishability. The indium oxide quantum dots also has a spin half system, which we know how to coherently manipulate them with very high fidelity. And for the cavity, we will couple those quantum dots to nano optical cavity based on photonic crystals. We have many years experiences working with these devices. And we routinely get cavity Q factor that is larger than 10,000 and very small mode volume, and we can achieve very high Purcell factor with these systems. And just to quickly show you some previous results that we have, using these systems, we have been able to show like deterministic interactions between a single quantum dot spin and a single photon, and using the single quantum dot spin to mediate deterministic interactions between different photons. And we even realized a single photon switch and a transistor based on these devices. And the important thing that I want to make a point here is that all the control techniques, all the pulse sequences you see here can be directly applicable, applied to the proposed entangled photon generation experiments that we want to do here. We also want to slightly change our device by coupling by developing a tapered fiber coupling system. And previously, people have demonstrated this coupling scheme using both diamond and silicon nitride devices. And it shows like very large collection efficiency, which is very important for like N photon entangled state generation. We have some preliminary design simulations. Most importantly, based on this design simulation and estimation of realistic parameters, we estimate that we can have 5 photon GHZ state with megahertz rate, 12 photon GHZ state with 10 kilohertz rate, which would be a 6 orders of magnitude improvement over the previous experiments. We even are able to approach 20 photon GHZ state. So those capabilities will allow us to start experimentally prove many interesting quantum many-node communication protocols that are previously not available to experimentally test. So because of the time limit, I just want to say that we also have some ideas about how to extend our scheme to generate two-dimensional graph entangled photon state. And I'll just show the outcome, expected outcome, and broader impact for your view. Thank you very much.
Thank you. Perfect timing. Paper is now open for questions.
I'll start. This is Grace Metcalf.
Go ahead, Grace.
Okay. Maybe you could, thank you for your presentation. It was very interesting. Maybe you could tell us a little about what you're looking for in terms of what can you explore with your 1D generation of GHZ states?
Yeah, that's a great question. So I think traditionally people have focused, when people generate entangled photons, most of the work have focused on entangled photon pair generations. So there is really a lack of capabilities to generate like GHZ state, and all the previous experiments like gives really low rate, which is practically useless. So once we are able to generate GHZ state with a relatively high rate, we can test a lot of interesting protocols. One example is what I just shared, the quantum secret sharing example, which requires a distribution of GHZ state and measurement and doing correlations. It's sort of like a QKD experiments, but expanded to N users. And it requires, like, it has new capabilities where basically the key has to be shared among the N-1 users, and these N-1 users has to work collaboratively in order to get the information of the key, and therefore use a key to, for example, open a safe box that the first user has. So there are many other protocols like quantum anonymous transmission that we can start to experimentally explore with our capabilities.
So is there a minimum rate that you need to test these different protocols?
So in general, even if you have like a rate of like 1 photon per hour, you can test them, but it's just practically impossible. So like there is not a fundamental rate requirement on like what rate it's required to test these communication protocols. But I think like at least a kilohertz rate, or maybe if you really have patience, like hertz rate is required to test these communication protocols for at least for proof of concept demonstrations.
So maybe I can ask, and you may have said this and I just missed it, which is how long do you think you'd be able to store the photons?
That's a very good question. So for most of the protocols we are interested in, we don't really need to store the photons. It's like a QK, if you are exploring a QKD experiments, you don't really need to store the photon. You distribute the photon and you immediately detect them. So I think for the first few demonstrations of, if we are able to develop this capability to generate GHZ state, for example, we will start looking at protocols that working with photons in this way. And of course, for some other protocols, it may require you to distribute GHZ state that are actually stored in a quantum memory. And there you do need to develop again spin photon interface, and depending on what memory you use, it decides like how long you can store the photon. And actually, as a matter of fact, the quantum dot is also carries a spin. So you can use the same system to build the spin photon quantum memory. Although they are not the best quantum memory at the market, their coherence time is in the order of like millisecond. So you may want to start thinking about coupling these photons to either some color centers, nuclear spins, or so not superconducting qubit. I'm thinking like trapped ions and etc. Yeah.
Any further questions? We have time for one short question if there are any more.
This is Frederick Fatimi. I also enjoyed that talk. In the white paper, you mentioned the possibility of exploring non-Markovian dynamics. What aspect of that would you be able to explore with the system? Super radiance or something, or what?
Yeah, that would be a great question. The reason that we are interested in non-Markovian system is in order to extend our scheme to 2D, we actually recently have a theory protocol where we kind of show that if you add a delayed feedback, and then once you emit the photon, you scatter the photon back to the emitter again, then that is a way to create like 2D entangled photon structure. And we actually in our theory paper, recent theory paper, we show we can generate like tree state and repeater graph state, which would be very useful for optical quantum repeaters. And our fiber system, that our proposed fiber network system, would be ideal to implement a long delayed feedback. But that requires a lot of new device design, etc. So the preliminary first thing we can start working on in the first year is trying to see, once we have a system like this, whether we can start to see some non-Markovian emission system, because there is a memory caused by the delay line. So it can interfere with whatever the quantum emitter is emitting. So once we are able to see that, that would be a good milestone for us to pursue our next goal, which is trying to generate these 2D entangled states.
Thank you.
Hi, Thomas, are you on? Can you do it?
Yeah, I'm here. So should I begin? It seems like there's some technical difficulty somewhere in the system.
Yep, we're taking care of that, but if you want to get going, I'm going to share my screen with you. You can take over and start your presentation.
Okay, great.
You should have access.
Okay, so here we go. Okay, hello, everyone. I'm Tom Purdy from the University of Pittsburgh. I'm having trouble. There we go. Sorry, thank you. I'm Tom Purdy from the University of Pittsburgh. I'm here pitching with my with my collaborator Michael Harridge, also from the University of Pittsburgh. I thought I'd tell you a little bit about our team to begin with. So my lab focuses on cavity optomechanics. We study the quantum limits of displacement sensing. We've also done a lot of work on electro-optomechanical transducers for microwave to optical frequency conversion, as well as optomechanical metrology, for instance, primary thermometry with optomechanical systems. My co-PI, Michael Harridge, is an expert at superconducting microwave parametric amplifiers, reading out qubits at quantum limits and beyond, building high dynamic range frequency transducers and amplifiers, as well as superconducting qubits. Let's see. And today we're pitching an idea that combines our expertise, that is to create microwave to optical transducers to take superconducting qubit signals out of dilution refrigerators and put them into fiber optic networks. So we use a mechanical intermediary. There's been a lot of different talks already in this session about different ways to make this microwave optical transducer with the big goal is to making, entangling superconducting qubits in different dilution refrigerators and allowing access over a long distance for fiber optic communication between for superconducting quantum information systems. So our shorter term goals are to make a mechanical quantum memory for our superconducting qubit, as well as just to, in the very short term, to make efficient transduction between microwave optical and mechanical systems. So Our transduction scheme is slightly different than what you've seen before. What we have is a superconducting qubit, and we'd like to couple it to a very much lower frequency piezomechanical resonator. So think about 6 gigahertz qubit, 100 megahertz piezomechanical resonator. To bridge this gap in frequency, the Hayduk lab has these superconducting mixing elements. So they're termed superconducting nonlinear asymmetric inductive elements, or snails. So basically, it's a strongly parametrically pumped three-wave mixing element that allows us to effectively convert signals from the microwave domain into radio frequency phonons. And we can bridge this gap with very, very low added noise and very high efficiency with strong parametric pumping. There's several advantages to our technique of using this nonlinear mixing intermediary. First and foremost, it allows us a much greater range of mechanical resonators to access. Rather than if I have a 6 gigahertz qubit and I want it to talk to a piezomechanical device, I don't have to have that device be at 6 gigahertz. I can make a range of frequencies from tens of megahertz up to gigahertz. The second thing is that because this is parametrically pumped, we can use a strong parametrically pump to greatly enhance the overall interaction strength. So our two systems that we want to talk to each other need only be very weakly coupled, and we can parametrically pump this to increase the interaction strength to make fast swapping rates. The overall interaction, everything is far off resonance from each other, and we can do parametric pumping protocols that don't require us to go through some lossy, put a lot of population in lossy intermediate states, and that creates that helps with the efficiency and noise in our system. It's very flexible. We can turn off and on the interaction. Generally, piezoelectrics, it's hard to turn off, but here it allows us a lot of flexibility. And it also, we think our mechanical resonators at lower frequencies are going to be very good quantum storage, very good places to store quantum information. And I have a little bit more about this if I can get to the next slide here. Okay, so this figure here really tells us where do you want to be in order to store quantum information for a long time in a mechanical degree of freedom. So on the vertical axis, we have the quantum state lifetime for mechanical system, and on the horizontal axis, we have mechanical frequency and temperature. Of course, we want to go to low temperature to minimize thermal decoherence. But in a nutshell, what this graph is telling us is that if we can use this parametric transducer to really gear down our mechanical frequency, we can actually do much better. Say for the same mechanical quality factor, if we can gear down our mechanical frequency by a factor of 10 or 100, we make that many oscillations that much slower, and our net storage lifetime increases. So we like to go to lower frequencies for longer storage times. So what kind of mechanical devices are we interested in coupling to superconducting qubits and optomechanical systems? We can slowly get this graph to scroll up. Here we go. Sorry, I'm having some trouble with the latency of this of the system, but hopefully we can get a picture of up here soon of some low frequency mechanical resonators that are based on high tensile stress suspended silicon nitride films. I'm having trouble controlling this here, but up at the top of the screen, we have suspended strings and silicon nitride membranes or drums that have very high mechanical quality factor. In our lab, we've demonstrated Qs on the order of 10 to the 8. The best devices have Qs of 10 to the 9, and we think through optimizing the geometry and materials, as well as going to very low dilution refrigerator temperatures, we can exceed those Qs as well. And so the figure of merit here for a Q of 10 to the 9 for these low frequency resonators means we have about a 1 second quantum state lifetime. So that would be a very nice storage element for quantum information. We've also developed a new optomechanical coupling technique to couple to these mechanical resonators. We take a tapered optical fiber and put that near the dielectric that makes up our mechanical resonator, and the evanescent field from the fiber interacts with the mechanical degree of freedom. This is actually interesting because it allows us to take information from superconducting qubits. We're going to use our parametric transducer to turn it into mechanical excitations. Those mechanical excitations actually get encoded as polarization rotation on our light. So we can send we can encode our quantum information as polarization rotation, which is a really good degree of freedom to use for long distance quantum communication. So if we can get to here we go. Unfortunately, it's a little small, but we're also considering RF bulk acoustic wave resonators and surface acoustic wave resonators. For the frequencies we care about in sort of 100 megahertz range, we're now talking about acoustic wavelengths on the order of tens of microns. So that makes the fabrication of these devices much simpler. We can use simple optical lithography. We can think about flip chip bonding and an electrode chip on top of our device to control this and couple piezo mechanically. We don't have to worry too much about alignment tolerances at the tens of micron scale. We think we can get strong piezo mechanical coupling. Down here on the bottom is a very cartoonish schematic of what our piezo mechanical device might look like. We have some electrodes on a chip that's suspended above a piezoelectric device, and those electrodes are coupled to some large scale antennas that we use to talk to our microwave nonlinear elements and ultimately to our microwave qubit. So we can take this device and put it into a superconducting microwave cavity, and I'll show you a picture of that in a minute. And we're more thinking about sort of microphotonic technology to do the optomechanical coupling, because now we've got tens of micron scale mechanical resonators. And I like microphotonics because at very cold temperatures, nanophotonics has smaller scale photonic structures. Nanophotonic structures have problems with generating a lot of heat in a very small volume. And the great part of this is that we have a very modular system then that as long as we can couple an antenna to our piezo mechanical resonator, we can put it into a device like we see here from the Hatridge lab, which is a waveguide, a microwave waveguide coupled to one of these superconducting nonlinear elements with a bunch of optical cavities surrounding it. And this is a demonstration from the Hatridge lab where they're able to swap photons between two different frequency, spatially distant microwave cavities via this nonlinear mixing element. So if we scroll down here, we can see that what they're able to do is couple a 5 gigahertz photon in one cavity and swap it into a 7 gigahertz photon in another cavity and back. They can do that with sub-microstem scales with very high fidelity. What we're doing, what we're proposing here is to replace one of these microwave cavities with a much higher Q, lower frequency piezoelectric element and use the same sort of nonlinear, highly pumped parametric microwave interaction to achieve strong swapping and eventually storage and then eventually conversion to optomechanics. So in the short term, we'll spend some time developing RF piezo-mechanical resonators and try and demonstrate this snail-mediated microwave to optical coupling and characterize how well the system works.
All right, thank you very much. I think the audio and video issues are fixed on our end, so the paper is now open for questions.
Hi, Thomas. This is Grace. Thank you for a very nice presentation. It was a little quick for me, so I might have missed a few parts. So maybe I can ask you, could you maybe describe what your role is in this project versus Michael's?
Yeah, so Michael has this platform that's able to couple between different electrical systems, and my role is to develop the piezo optomechanical system that is going to be coupled to his existing technology.
Hey, Tom, this is Joel Moser. You mentioned in your white paper that future iterations of the experiment would extend to second time range of seconds for storage times. Can you talk about what the sort of the path to that is? What are the challenges to get there?
Yeah, so we've got several different mechanical technologies. I think all of them can reach this sort of Q of a billion, which is, you know, a 1 second lifetime. We've demonstrated very high Qs in these suspended silicon nitride structures. And there, I think that the optomechanics is well worked out. We've done a lot of optomechanical coupling to these devices. There, I think the challenge is creating a piezoelectric coupling without reducing the quality factor. We've done some designs and simulations. We've done some thinking about things like bimorph structures and also piezoelectric transducers that are not suspended but are sort of at the end of our at the edges of our device. And those have all their technical challenges. In terms of the bulk and surface acoustic wave resonators, those are have demonstrated high quality factors. For instance, in quartz, there have been Q of a billion bulk acoustic wave resonators, things like that, and that's somewhat of a materials challenge. But I think that's somewhat worked out. You can, these devices are pretty simple, so you can use very nice materials without having to worry too much about complicated fabrication techniques. There, I think we have to work a little harder on the optomechanical coupling to ultimately make those devices do the entire conversion step. But just as a memory, bulk acoustic or surface acoustic wave resonators, sort of more macroscopic piezoelectric material may be a very most promising route. So again, these devices are all a lot bigger than, say, we saw a nanomechanical device that was truly submicron in all dimensions, where these two-level systems play a much larger role. Here with a little bit larger scale, tens of microns devices, we think we can get to the higher Qs and keep the T1 and T2 times high.
Time for one more question. We have it. Okay, if not, let's thank Professor Purdy for a great talk, and we will move on to our final presentation. Our final presenter is Professor Britton Plord from Syracuse University. Please unmute your microphone, Britton, for a mic check, and then when you're ready to begin, click the Start Presentation button, and this will begin your 10-minute presentation.
Yes, okay, so can you hear me?
Yes, great.
Super. Let me click Start here. Okay, great. So I am Britton Plord from Syracuse University, and I'm excited to be able to talk to you today about my proposal for a project to develop superconducting metamaterial ring resonators. This idea for ring resonators builds on some other recent work in my lab on metamaterials and superconducting qubits. So our main objective for these ring resonators is to provide a novel pathway for communication between multiple qubits. This approach could also be a route to implementing quantum memory, and these structures could serve as a compact processing node of a distributed quantum network. So let's start with this first panel on the left here. Let me see if I can get it open. Oops. There we go. So circuit quantum electrodynamics, or circuit QED, has been enormously successful as an architecture for building quantum processors with superconducting circuits. So in this scheme, the Josephson-based qubits behave like artificial atoms, so here, and these are then coupled to linear microwave resonators like this coax line here on my schematic that play the role of optical cavities in the case of cavity QED with real atoms. So the resonators in circuit QED are used for qubit readout and also for coupling multiple qubits together for generating entanglement. This approach has been adopted by the majority of superconducting qubit labs around the world, including the large industrial quantum computing teams, as shown in these images that I'm scrolling by here from devices at Google and IBM. Of course, these images are already a few years out of date, with more recent devices from both places having 50 or more qubits. But this makes the point that these chips contain many of these resonators, which are the hairpin shaped structures that you can see here in the Google picture and down here in the IBM picture. You can also see in these images that the conventional planar transmission line structures that form these resonators in a state-of-the-art approach are physically large and occupy a significant footprint on a chip. Also, for these planar structures, we generally only have one resonant mode per resonator that is capable of interacting strongly with a qubit. So this poses limitations in that it is difficult to make compact resonators capable of coupling a large number of qubits, and it is challenging to make a high density of resonant modes for forming a quantum memory or making compact processing nodes. So in the next panel, let me try to go to that here. Okay, so before we discuss metamaterials and ring resonators, let's look a bit more at conventional transmission line resonators. So for a transmission line, like the coax in this schematic here, the resonant modes are set by the boundary conditions at the ends, which determine the standing wave patterns, very similar to just vibrations on a guitar string. For a resonator formed from a transmission line with conventional dispersion, there'll be harmonic modes at integer multiples of the fundamental resonant frequency. The transmission lines that are used most typically in circuit QED are formed not from coax lines, but from coplanar waveguide structures. And the length required for targeting resonances that are compatible with typical qubit frequencies, which are typically in the range of, say, 4 to 10 gigahertz, is set by the wave speed on the coplanar waveguide, which itself is related to the substrate dielectric and the device geometry, and is roughly 50% of the speed of light. So the typical coplanar waveguide resonator for circuit QED devices ends up being quite long, say in the range of 5 to 10 millimeters. So if I go to the next panel, is there some way to make resonators for circuit QED systems that are more compact? And in particular, can we adopt techniques from the photonics community? So in the optical regime, there are quite impressive and compact microfabricated ring resonators, as shown in this image here. That's from an article by Kari Vahala at Caltech. And these beautiful ring resonators achieve extremely high quality factors in a quite small footprint of the order of 100 microns or so. So what about simply carrying this idea over and to circuit quantum electrodynamics to try to make microwave ring resonators from coplanar waveguide transmission lines? So to make such a device, like say in this image here, which is a little bit small, sorry, if we wanted it to resonate with its fundamental at 5 gigahertz, would require a diameter of about 8.5 millimeters, which is huge and impractical, considering circuit QED chip sizes are typically around 5 to 10 millimeters on a side. Also, the resonances would still be harmonic. So the second mode would be up above any qubit frequencies and all the other ones further still. So instead, to make this feasible, we need an alternative to planar microwave resonators. And we need a way to be able to reduce the wave speed, and also be nice if we could tailor the wave dispersion properties to allow for increased mode density for interacting with qubits. Superconducting metamaterials give us a route to address these issues. So instead of distributed transmission lines like CPWs or coaxes, we can form the transmission line from lumped element inductors and capacitors. In that case, the wave speed is determined by the parameter values that we choose. So by using this configuration with series capacitors and inductors to ground, we can also make a transmission line with what's called left-handed dispersion, meaning that the mode frequency is a falling function of the wave number, which can make our structure capable of supporting many independent modes in a narrow frequency band. So if I go up to the next panel here. So my research group at Syracuse, we've done recent work on superconducting metamaterials for generating novel mode spectra and for coupling to superconducting qubits. And we've done this with planar lumped elements arranged in a one-dimensional linear configuration, like in this diagram here, with resonant modes around 5 gigahertz and above. And we've done this with thin film structures. In a paper we published last year with some collaborators in Germany, we were able to directly image the microwave fields in one of these devices, and we could show the unusual properties of this left-handed dispersion, namely as we go to higher frequencies, which I'm afraid are a little bit difficult to read here, but this is a low frequency and this is going to higher frequencies. The wavelength actually gets longer, which is a signature of this left-handedness. So in a more recent paper this summer, we showed that we could also couple one of these metamaterials to a transmon superconducting qubit and achieve strong coupling between the qubit and each metamaterial mode that the qubit passes through as we tune, that we could see with these vacuum Rabi splittings in the transmission spectrum for one of these devices. So let me go on now and talk about metamaterial ring resonators here in this panel. So in contrast to my earlier crude example of trying to make a microwave ring resonator from just a coplanar waveguide, we can make a much more compact ring resonator by forming a metamaterial transmission line into a loop like this diagram here. And for comparable circuit parameters to what we've done so far for our other metamaterial devices, a 24-cell ring with this layout, something like this here, with its lowest resonance near 8 gigahertz, could fit in just a 1.3 millimeter footprint. So more than a 30 times reduction in area from the sort of simple-minded coplanar waveguide approach. And because we're using a metamaterial with left-handed dispersion, we can get 6 modes between just 8 and 10 gigahertz in this case that can be used to strongly interact with a qubit, or even with multiple qubits. This is a plot here of the simulated dispersion relation for one of these here. So let me go to my last panel at the bottom. And so this lists some of our objectives for this project. So we'll plan to develop these metamaterial ring resonators first with finite element numerical simulations of the microwave field distributions, then fabricate these devices with superconducting thin films, following a similar process to what we've done in our earlier work on circuit QED metamaterials. We'll then plan to explore the coupling between superconducting qubits and these ring resonators. So here's a schematic here with 3 different transmon qubits shown in blue, coupled to one of these ring resonators. In this case, just to fit it on the screen, just 8 unit cells. So with this compact ring resonator, it'll be possible to capacitively couple qubits to different unit cells around the ring, and the qubits will couple strongly to modes that have a voltage antinode at the qubit location, and only weakly to modes, or not at all even, to modes that have a node at the qubit location. So we also plan to study more complex metamaterials with added series inductances, which allow us to compress the band structure even further. In this case, here's an example with some added series inductance that allows us to compress this so all 12 modes fit within just a span from about 7 gigahertz up to 11 gigahertz. So this work will have multiple potential impacts, both to the broader quantum information science community and to industry and government efforts in quantum information science. So our ring resonator scheme will allow for selective communication between qubits based on their location. And also, if we implement a flux modulated parametric sideband scheme, something that my group developed several years ago for other circuit QED systems, we can quickly swap excitations between qubits and ring resonator modes, and thus make a compact quantum memory. So some of the challenges are shown down here. Depending on the configuration of the ring resonators that we make, it could be somewhat challenging to ensure a well-defined ground in the center of the ring. But based on our prior experience, we expect that small wire bonds to that center will be sufficient for grounding at least the initial devices. In the future, we could go to more complex structures, say multi-chip modules, or through silicon vias to separate grounds on either a separate chip or on the backplane of the chip. So if our efforts to develop these metamaterial ring resonators are successful, this will seed future device structures with multiple rings on a chip for coupling multiple qubits to multiple modes and forming compact quantum memories and processing nodes in a small footprint for a distributed quantum network. So I'll stop there and thank you for your attention.
Thank you very much. Paper is now open for questions.
Yes, Tim Lawrence. I've seen other resonator ideas, out at Brookhaven National Lab in SUNY. So is your concept, what would the spacing be on a network with your resonator versus more state-of-the-art resonators that are out there? If that question makes sense.
It makes sense. And so the key difference here is this with this very unusual left-handed dispersion, the modes, let me see if I can open this panel here. So the modes get very compressed right at the band edge. So we can get a very high density of modes. And there we go, okay. So we get a very high density of modes that can be very, very close together. And that's something that's not possible with a system with conventional dispersion. So in any other type of resonator that's say made from a conventional transmission line, or such as like a 3-dimensional waveguide resonator.
Nope, understand, thank you.
Sure, thank you.
Hi, Brayton. Thank you for a really interesting talk. I was wondering if you could comment a little bit about how you think the performance of a qubit would change when it couples to one of these this metamaterial ring.
Great question. So we can borrow a lot from our recent work on just looking at qubits, or a single qubit for now, coupled to a linear metamaterial resonator like this here. And what we found, I didn't want to cram too much stuff onto the poster here, but what we found in this recent paper that's on the archive now was, we could tune the qubit, which is down here, over a wide range of frequencies. And what we could study was the qubit loss, basically measure the qubit T1 as a function of its frequency. And when the qubit was biased at low frequencies, in the band gap where there were no modes in the system, so basically down in here, T1 was quite long. It could be 20 microseconds. So not quite state of the art, but really pretty good for superconducting qubits. As we would tune it up into this forest of modes up here, as you might expect, the T1 would drop, and due to the Purcell effect. And we were able to map that out and see that T1 drop very quickly right at the center of a resonance and then recover in between resonances. So the attractive thing about this scheme is you could have all the qubits you're interested in operating down here in this band gap where lifetimes are long, but they could still interact dispersively with these modes up here. And using a sideband scheme, it's possible to parametrically swap excitations from qubits down in this band gap up into modes up here and still preserve a long lifetime for the qubits. Any other questions?
Any further questions from our panel? If not, I think we'll call this paper to an end. And I'd once again like to thank Professor Plourde for a great paper.
Thank you.
Thank you. We have now reached the end of our communications session. So as a reminder to the judges for the session, you will now move to a separate Zoom session with a separate link, and you will begin deliberations of your papers. As we wrap up, I sincerely want to thank all 36 of our top university teams from around the world that pitched their proposals to advance quantum enabling technologies in the areas of timing, sensing, communications, and computing over these past 2 days. The judges, as we move forward and figure out our top awardees, will certainly have their work cut out for them. Also, if you want to go back to any of the posters you've seen, feel free to peruse these posters, take a further look at them, dig into them a little more. These are linked on our main event website, so we encourage you all to do that right now. We hope that you'll tune back in tomorrow, as we are not even close to being done yet. Tomorrow we will announce the 18 pitch participants that will now be eligible to apply to the AFOS RBAA and walk away with a total of $1.35 million in seedling grants. We're very excited to make this announcement tomorrow. We're also extremely thrilled to hear from our keynote speakers, Dr. Will Roper, United States Air Force and United States Space Force Senior Acquisition Executive, and Dr. Neil deGrasse Tyson, American astrophysicist, cosmetologist, planetary scientist, author, and science communicator. We'll be back here tomorrow morning, beginning at 9 a.m. Eastern. We hope to see everyone then. Thank you very much.